You solve problems. A lot of them. Maybe 100. Maybe 300. Maybe more. And then a new interview question shows up. And your brain goes blank. That is the trap of random grinding. You remember answers, but you do not recognize patterns fast enough under pressure. This video is different. This is PatternMastery 100, 100 interview questions, organized around the patterns phone companies keep reusing. And every solution follows one system. Basics. Breakdown. Assess. Structure. Implement. Check. All solutions will be implemented using Python. So do not watch this like entertainment. Watch it like training. Pause. Think first. Find the pattern. Then compare your thinking. By the end of this session, you should not just know more problems. You should see problems differently. Two-sum. Did you know the two-sum problem is one of the most frequently asked questions in interviews at companies like Google, Amazon, and Meta? It's a classic from the PatternMastery 100 list, and over 30% of candidates stumble here, not because it's hard, but because it tests how you think under pressure. If you can master two-sum, you'll unlock a pattern used in dozens of top tech interview questions. So, let's crack it together. Let's break down the two-sum problem. We're given an array of integers called nums and a target integer called target. Our job is to find the indices of two numbers in nums that add up exactly to target. Each input will have exactly one solution, and we can't use the same element twice. Let's assess what's tricky here. A brute force solution would check every pair, O(n) squared time complexity. That's too slow for big arrays. We need something faster. Here's a key insight. As we scan the array, we can use a hash map to record the numbers we've seen so far and instantly check if the complement, target minus current number, is already present. That gives us O(n) time and O(n) space. Now, let's structure our approach. We'll create an empty dictionary to store numbers and their indices. As we loop through the array, for each number, we'll compute its complement. If that complement is already in the dictionary, we return the pair of indices. If not, we add the current number and its index to the dictionary.
Let's try to implement it using solution 1. Here we're defining a blueprint called solution. Think of it like creating a toolbox where we'll store our function. This line creates a function named toSum. It takes a list of numbers called nums and a number called target. Our goal: find two numbers inside nums that add up to target. We start by setting up an empty dictionary, basically a super fast lookup table. It will let us quickly check. Have we seen this number before? Creating the dictionary is O(1). Now we loop over the list once, getting both the position, I, and the value, nom, each time. This lets us build our lookup table. Time complexity. This loop runs through all elements, so it's O(n). For each number, we store it in the dictionary with its index. It's like saying, if you ever need this number later, here's exactly where I found it. Dictionary assignment is O(1). And now we move on. We start a second loop through the list. Now that our lookup table is ready, we'll use it to find the matching pair. Again, this loop is O(n). Here we calculate the complement, the number needed to reach the target. Example: if the target is 10 and we're looking at 6, the complement is 4. This line checks two things. Is the complement in our dictionary? Is it not the same index we're currently looking at? Because we can't use the same number twice. Dictionary lookups are O(1), so this is super fast. If both conditions are true, boom, we found our pair. We return the two indices that add up to the target. And that's how this algorithm works. It first builds a fast dictionary mapping each number to its index, then loops again to check which number pairs add up to the target using constant time lookups. Efficient, simple, and elegant. Check. Now let's walk through the verification step. This is where we show that the solution actually works with a real test case. We plug in the array. Nums equals 2, 7, 11, 15, target equals 9. Here, each number represents a candidate value, and we're searching for two of them whose sum equals the target. Our solution scans the array, keeping track of what we've seen so far. At index 0, we see 2. We need 7 to reach the target, because 9 minus 2 equals 7. It's not yet in our map, so we store 2 and move on. At index 1, we see 7. We check. Do we already have its complement, 2? Yes, and it came from index 0. So the pair, 2 and 7, sums to our target 9, giving the output 0, 1. The actual output is 0, 1, and it perfectly matches the expected result, 0, 1. That confirms the algorithm is behaving exactly as intended. Now let's try another implement approach using solution 2. Here we're creating a container called solution. Think of it like opening a folder where our function will live. This defines our function toSum. It takes a list of numbers called nums and a desired total called target. Our mission: find two numbers inside the list that add up to that target. We start with an empty dictionary. This will become our memory bank, where we remember numbers we've already seen and the positions where we saw them. Creating this is O1. Now we loop through the list one item at a time. I is the index, and num is the actual number at that index. This loop will touch each element once, so its time complexity is On. Here we figure out what number we need to pair with the current number in order to reach the target. If the target is 9 and the number is 4, we calculate that we need a 5. Simple subtraction. This line asks, have we already seen the number that completes the pair? Because we're using a dictionary, this check is blazing fast, O1 time. If the complement is in our dictionary, we immediately return the two matching indices. The first index is where we saw the complement earlier, and the second is the current index. That means we found our solution. If the complement wasn't found, we store the current number in our dictionary along with its index. It's like saying, I'll save this number in case it helps to form a pair later. This operation is also O1. And that's how this algorithm works. It first creates a dictionary to remember the numbers it has seen, then checks each new number to see whether it completes a pair that adds up to the target. Efficient, simple, and elegant. Check. Let's run through this second test case to confirm the solution behaves correctly. We're given nums equals 3, 2, 4. Target equals 6. Each element is a potential part of the pair we want, and we're again searching for two numbers that add up to the target. Here's how the solution processes it. At index 0, the number is 3. We would need another 3 to reach the target. 6 minus 3 equals 3. That complement isn't in our map yet, so we store 3 and continue. At index 1, we see 2. Now we need 4. 6 minus 2 equals 4. Not in our map yet. Keep going. At index 2, the number is 4. This time, the complement is 2, and we already saw it at index 1. Perfect. That gives us the valid pair. So the solution returns 1, 2. The output, 1, 2, matches the expected 1, 2, confirming the implementation is solid, and handles this scenario exactly as intended.
Let's have a quick recap. Breakdown recap. In this challenge, we were given a list of numbers and a target value, and our goal was to find the two numbers that add up exactly to that target. It's one of the simplest yet most iconic interview problems because it tests how you connect logic with precision, not just how you write code. Assess recap. We explored different ways to solve it and saw that brute force, while straightforward, is too slow for large inputs. The real breakthrough came from realizing we could use a hash map to keep track of numbers we've already seen and quickly check for their complements. That insight transformed the problem from quadratic time to linear time. Structure recap. Our logical plan was simple. Loop through the numbers, calculate each number's complement, and see if that complement has already appeared. If it has, we found our pair. If not, we store the current number and keep going. A clean, step-by-step flow built on efficient lookups. Implement recap. As we coded, the process came to life exactly as planned. We tracked numbers in real time, checked complements on the fly, and watched how the logic naturally identified the correct pair. It was a perfect example of turning algorithmic reasoning into an elegant, working solution. Check recap. When we ran our test case, everything lined up. The indices, 0, 1, appeared exactly as expected. That confirmed the logic worked and that our hash map strategy performed efficiently, delivering a precise ON solution with minimal space overhead. Closing insight. The toSum problem is a reminder that simplicity can hide depth. It's not about complex math. It's about using the right tools to think smarter, not harder. Once you master this pattern, you'll recognize it everywhere. A foundational skill for building faster, cleaner, and more confident solutions in every interview.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Best time to buy and sell stock. Have you ever wondered how top engineers spot patterns that lead to big wins? Best time to buy and sell stock is not just a must-know Pattern Mastery 100 question. It appears in almost every FANG interview loop and stumps over 40% of applicants. Mastering this problem gives you an edge in any technical interview because it teaches you to recognize profit opportunities, optimize for efficiency, and think like a Wall Street pro. Ready to discover the secret? Let's dive in. Let's break down the problem. We're given an array where each element represents the price of a stock on a given day. Our job? Find the maximum profit we can achieve by choosing a single day to buy and a different day in the future to sell. If there's no way to make profit, return 0. No short selling, and you can't sell before you buy. Let's assess our options. A naive brute force solution would check every possible pair of buy and sell days, but that takes O(n) squared time, not scalable for big inputs. Instead, can we track the lowest price seen so far and always check the profit if we sold today? This only needs a single pass and O(1) extra space. Super efficient. Remember, always buy before you sell, and update your max profit as you go. Here's the structure of our plan. Start with variables for the minimum price so far, set to infinity, and maximum profit, set to 0. Loop through each price in the array. If the current price is less than the minimum, update the minimum. Otherwise, calculate the profit if we sold today, and update max profit if it's higher.
Let's try to implement it using solution 1. We start by creating a class named solution. This is just a container where our method will live. Think of it as opening a toolbox before picking which tool or function to use. This line defines the function maxProfit, which takes a list of stock prices. Our goal is to figure out the most money we could make by choosing the best day to buy and the best day to sell. We initialize min price to infinity, basically the largest possible value. This is like saying, I haven't seen any price yet, so assume the highest imaginable price. As we loop, we'll keep updating this with the lowest price we encounter. Next, we set max profit to 0. Since you can't have a negative profit when buying and selling once, we start from 0 and look for something better. Here we begin looping through each price in the list. This loop touches every element once O(n) time complexity. We check whether the current price is lower than the lowest price we've seen so far. If it is, that means we've found a better day to buy. And if the price is lower, we update our min price. In plain terms, this might be the cheapest day so far, remember it. This operation is constant time O(1). Otherwise, if the price isn't a new minimum, we check whether selling today could give us more profit than any previous day. We calculate the profit by subtracting the lowest price we've seen from today's price. If that profit beats our current max profit, we update it. This line sets max profit to the new, larger profit value. It's like saying, selling today would earn more than any other day so far. Let's update our best result. Finally, we return the highest profit we found after scanning all prices. If the prices kept going down, max profit remains 0, meaning no profitable trade was possible. And that's how this algorithm works. It first sets up trackers for the minimum price and best profit, then scans through prices once to update them whenever a better buy or sell moment appears. Efficient, simple, and elegant. Check. Time to confirm this solution with the classic stock profit test case. Here's the input. Prices equals 7, 1, 5, 3, 6, 4. Each number represents the stock price on a given day, and the goal is to find the maximum profit from buying once and selling once later. Our algorithm tracks the lowest price seen so far and continually checks the best profit achievable if we sold today. Here's what happens. Start with 7. This becomes our initial lowest price. Next comes 1. This is lower, so it becomes the new buy price. Then we see 5. Selling at 5 after buying at 1 gives profit 4. Next 3. Lower than 5 but still above 1. No change to best profit. Then 6. Selling at 6 after buying at 1 gives profit 5 new max. Last 4, profit would be 3, which is lower than our current best. The highest profit observed is 6 minus 1 equals 5. The output is 5. The expected result is also 5. And everything lines up perfectly, confirming the logic works exactly as intended. Now let's try another implement approach using solution 2. We start by creating a class named solution. This is simply a container where our method will live. Think of it like opening a workspace before adding your tools. This defines our function maxProfit, which takes in a list of stock prices. Our task is to compute the maximum profit we can make through multiple transactions, as long as we buy before we sell. We set up max_cur to track the current running profit. You can think of it like a temporary balance that goes up or resets depending on how the price moves. And here we track max_so_far, which records the highest running profit we've seen at any point. This is the value we'll return at the end. We loop through the prices starting from index 1, comparing each price to the one before it. This loop touches each element once on time complexity. We compute the difference between today's price and yesterday's price. If the price increased, this value is positive. If the price dropped, it's negative. We'll use this daily gain or loss to update our running profit. This line updates the current running profit by adding today's difference. If the result ever becomes negative, we reset it to 0. It's like saying, if the streak of gains is broken, start fresh. This technique is the same idea behind Kadane's algorithm. Here we check if our new running profit is the best we've seen so far. If it is, we update max_so_far. This ensures we always remember the highest profit achievable. Finally, we return the largest running profit accumulated over the whole list. That's our maximum achievable profit. And that's how this algorithm works. It first sets up trackers for the current and best running profit, then scans through each day's price change to accumulate gains while resetting bad streaks. Efficient, simple, and elegant. Check. Let's validate this test case, a scenario where the price keeps dropping. Here's the input. Prices equals 7, 6, 4, 3, 1. Each number is the stock price for the day, and we're looking for the maximum profit from one buy and one sell. Since the price continually decreases, there is no day where selling after buying would yield a profit. Walking through the logic. Start at 7. This is our initial minimum. Move to 6, lower, so update the minimum. Then 4, even lower, update again. Then 3, update. Then 1, update once more. At no point do we encounter a price higher than our current minimum, meaning the algorithm never finds a profitable sell opportunity. So the maximum profit stays 0. The output 0 matches the expected 0, confirming the algorithm correctly handles cases where no profit is possible.
Let's have a quick recap. Breakdown recap. This problem is all about timing your trades for maximum profit. You're given a list of stock prices, each representing a day, and your goal is to find the best day to buy and a later day to sell to achieve the highest possible profit. You can only make one transaction, buy once, sell once, and if no profit is possible, you simply return 0. Assess recap. At first, checking every pair of buy and sell days seems logical but quickly becomes inefficient as the input grows. The smarter approach is to think dynamically, track the lowest price seen so far and calculate potential profits on the fly. This shift from brute force to a single pass solution transforms the problem into an on time, O1 space optimization, fast, clean, and elegant. Structure recap. Our plan followed a simple logic loop. Keep two variables, one for the minimum price we've seen and one for the maximum profit we've made so far. For each day, decide, is today a new minimum, or could selling today beat our previous best profit? Step by step, the loop narrows down the best buy-sell combination automatically. Implement recap. In practice, we brought this logic to life by simulating the market day by day. Each iteration either updated the lowest price or recalculated potential profit, steadily refining the outcome without needing extra storage or nested loops. The program effectively thought like a trader, balancing opportunity and risk in real time. Check recap. When tested with our sample input, the logic held perfectly. Buy at 1, sell at 6, and lock in a profit of 5. Every step confirmed the reasoning. Quick comparisons, instant updates, and a final result that matched the expected outcome. It's efficient and intuitive once you see it in motion. The biggest takeaway here is pattern recognition, spotting opportunities by tracking key values as they evolve. This problem isn't just about stocks, it's about optimization under constraints. Once you master this logic, you'll see it reappear in countless interview questions that reward smart, efficient thinking.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Contains duplicate. What if I told you that something as simple as checking for duplicates trips up more candidates than you'd expect, especially when speed and efficiency matter? Contains duplicate is a PatternMastery 100 classic, and it's a screening favorite at companies like Amazon and Apple. More than 50% of applicants try to brute force it. If you can nail this one, you're showing interviewers that you know your data structures and can think in real time. Let's see how pros do it. Let's break down the problem. You're given an array of integers, and you need to determine if any value appears at least twice. If any number shows up more than once, return true. Otherwise, return false. Super simple, but it tests your ability to spot the most efficient solution. Now let's assess our options. A brute force approach would check every pair, (n² time, but that's slow for big arrays. Instead, can we use a set to keep track of what we've seen as we scan the list? Sets in Python have O1 lookup time, so this lets us check for duplicates instantly as we go. This gives us an efficient O(n) time and O(n) space solution. Here's the structure of our plan. Create an empty set to store numbers we've seen. Loop through each number in the array. If the number is already in the set, return true, we found a duplicate. Otherwise, add the number to the set. If we finish the loop with no duplicates, return false.
Let's try to implement it using solution 1. We begin by creating a class called solution. This is just the container where our function will live. Think of it as the folder that holds the method we're about to use. This defines our function contains duplicate, which receives a list called nums. Our job is to figure out whether any number appears more than once. First, we sort the list in place. By sorting, any duplicates will automatically end up next to each other, like organizing a deck of cards, so matching values sit side by side. Sorting is the most expensive step here and takes O(n) log(n) time. Now we loop through the list, starting at index 1. We do this so we can compare each number with the one right before it. This loop runs once per element O(n). Inside the loop, we check whether the current number is exactly the same as the previous number. If two neighbors are equal, that means we found a duplicate. If a duplicate is found, we immediately return true. There's no need to check the rest of the list. And if the loop finishes without finding any equal neighbors, we return false, meaning there are no duplicates in the list. And that's how this algorithm works. It first sorts the list so any duplicates line up next to each other, then scans through once to check whether any neighbors match. Efficient, simple, and elegant. Check. Let's walk through this test case to confirm the duplicate detection logic works correctly. Here's the input. Nums equals 1, 2, 3, 1. Each value represents an element we're checking as we move through the array, and the goal is simple. Return true if any number appears at least twice. Here's how the solution processes the array. Start with 1. Not seen before. Add it to the set. Move to 2. A new number. Add it. Move to 3. Again, a new number. Add it. Finally back to 1. This one has been seen before. As soon as the algorithm hits that second one, it confirms the presence of a duplicate and returns true. The output is true, which matches the expected true, showing the algorithm correctly identifies repeated values. Now let's try another implement approach using solution 2. We begin by creating a class named solution. This simply holds our method, like setting up a toolbox before we pick the right tool. This defines our function contains duplicate, which receives a list of numbers called nums. Our mission is to figure out whether any number appears more than once. Here we create an empty set called scene. A set is perfect for this task because it stores unique values and allows super fast membership checks. Both operations are O(n) on average. We start looping through every number in the list. Since we touch each element once, this loop runs in O(n) time. This line checks whether we've already seen the current number. Because sets have constant time lookups, this check is extremely fast, O(n). If the number is in the set, that means we found a duplicate. If we detect a duplicate, We immediately return true. No need to continue. We already know the answer. If the number wasn't in the set, we add it. This is like saying, remember this number in case it appears again later. Adding to a set is also O1. If we finish checking every number without finding a repeat, we return false, meaning the list contains no duplicates at all. And that's how this algorithm works. It first creates a set to keep track of numbers we've already seen, then checks each new number in constant time to see whether it has appeared before. Efficient, simple, and elegant. Check. Let's verify how the duplicate checking logic handles a case with no repeated numbers. Here's the input. Nums equals 1, 2, 3, 4. We scan through the array while keeping track of what we've seen. 1. First time, add to the set. Next, 2. First time, add to the set. Now 3. Also a first time, add. Lastly, 4. First time, add. At no point does the algorithm encounter a value that already exists in our set, which means no duplicates, no repeat values, nothing triggers an early return. So the method correctly returns false. The output false matches the expected false, confirming that the solution behaves exactly as intended when the array contains unique values only.
Let's have a quick recap. Breakdown recap. This problem challenges you to identify if any number in a list appears more than once. It's simple on the surface, but it tests how quickly you can detect repetition using the right data structure. The goal is to confirm duplicates efficiently, without comparing every single pair. Assess recap. We started by evaluating two main strategies. The brute force method checks all pairs, but that quickly becomes too slow for large inputs. The optimized approach leverages a set, a data structure designed for instant lookups, allowing us to check whether a number has already been seen as we move through the array. Structure recap. Our logic followed a clear flow. Create an empty set, loop through each number, and check if it's already inside. If we find a match, we immediately know there's a duplicate. If not, we add the number and continue scanning until the end. This structure keeps the solution both logical and efficient. Implement recap. In practice, we simply track numbers in real time while looping. Each step represented a quick check and store operation. Constant time, no wasted effort. By focusing on the idea of seen versus unseen, the program effectively mirrored how our brain would remember past values in a sequence. Check recap. When tested with a sample array, the logic worked exactly as expected. As soon as a number appeared for the second time, the function identified it instantly and returned true. This confirmed the one-pass efficiency and correctness of the approach. The key takeaway here is that the simplest problems often reveal the most about your coding instincts. Choosing the right data structure, in this case, a set, transforms a slow, clunky solution into a clean, scalable one. It's a perfect demonstration of how thinking efficiently makes you stand out in technical interviews.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Product of array except self. Want to stand out in any technical interview? Product of array except self is a must-know Pattern Mastery 100 problem that appears again and again in Phong interviews. Many candidates get tripped up by constraints, like not using division and achieving ON time. If you can solve this one efficiently, you're proving you can handle real-world algorithmic challenges under pressure. Ready to see the trick that interviewers love? Let's go. You're given an array of numbers. For each position, return the product of all other numbers, except the one at that position. The twist: you can't use division, and you need to do it in ON time. The output is a new array where each index holds this special product. Let's assess our options. A brute force approach would calculate the product for each index separately, ON squared time. Not efficient. Using division would make it ON, but the problem says no division. So how do we do it? The trick is to use prefix products and suffix products. Prefix: product of all numbers to the left of each index. Suffix: product of all numbers to the right of each index. By multiplying the prefix and suffix at each index, we get our answer without ever dividing or missing a value. Here's our structure. Create an output array, initialize to ones. Pass left to right. For each index, multiply the product of all numbers to the left, prefix, updating the output. Pass right to left. For each index, multiply the product of all numbers to the right, suffix, updating the output again. The result is the product of everything except self at every index.
Let's try to implement it using solution 1. We start by creating a class named solution, just a container that holds our method. This defines our function product except self, which takes in a list of numbers. Our task is to build a new list where each position contains the product of all numbers except the one at that position. Here we store the length of the list in n. This keeps our code clean and avoids repeatedly calling len nums. We create a list called prefix, filled with ones. This list will store products of all numbers before each index. Starting with ones is important because multiplying by 1 doesn't change the result. Similarly, we create a suffix list, also filled with ones. This list will store products of all numbers after each index. We begin a loop to fill the prefix products. We start at index 1 because the first prefix value stays 1. There are no numbers before index 0. This loop runs in on time. Each prefix value is built by multiplying the previous prefix product by the previous number in the list. It's like walking forward and constantly keeping track of everything you've multiplied so far. Now we fill the suffix products by looping backward. We start from the second to last index and go all the way to 0. This loop also takes on time. Each suffix value is created by multiplying the next suffix product with the next number in the list. Think of it as tracking everything to the right of each position. We create a result list filled with ones. This will hold the final answer. Now we go through every index to combine prefix and suffix values. This final loop is also on. For each position, we multiply the product of everything to the left, prefix, with the product of everything to the right, suffix. That gives us exactly what the problem asks for. Finally, we return the completed result list, which contains the product of all other numbers for each index. And that's how this algorithm works. It first builds separate prefix and suffix product lists, then combines them to create the final result without ever using division. Efficient, simple, and elegant. Check. Let's walk through this test case to confirm the product of array except self logic works correctly. Here's the input. Nums equals 1, 2, 3, 4. Each number represents a position in the array, and for every index we want to compute the product of all other elements except the one at that index. Our solution does this by building prefix products, left side, and suffix products, right side, then multiplying them together for each position. Here's the breakdown. For index 0, product of 2, 3, 4. 2 times 3 times 4 equals 24. For index 1, product of 1, 3, 4. 1 times 3 times 4 equals 12. For index 2, product of 1, 2, 4. 1 times 2 times 4 equals 8. For index 3, product of 1, 2, 3. 1 times 2 times 3 equals 6. This gives us the final output. 24, 12, 8, 6. The output matches the expected 24, 12, 8, 6, confirming the algorithm is performing the prefix-suffix multiplication exactly as intended. Now let's try another implementation approach using solution 2. We begin by defining a class called solution. This is simply the container that will hold our function. Inside it, we define the function called product except self. This function takes in a list of numbers and returns a new list where each position contains the product of all the other numbers except the one at that position. We store the length of the list in a variable named n for convenience. Next, we set up a result list filled with ones. Starting with ones ensures multiplication works cleanly as we build up the answer. We then make our first pass through the list, starting from index 1. In this forward pass, we build what are called prefix products, the product of everything to the left of each position. At each step, we multiply the value from the previous position in the result list with the number directly to the left in the input list. This gives us a running product of all left side elements. Before starting the second pass, we create a variable called suffix and set it to 1. This will hold the running product of elements on the right side of each index. Next, we loop backward through the list, starting from the last index and moving to the first. In this backward pass, we multiply the existing prefix product stored in the result list with the current suffix value. Prefix times suffix gives the product of all elements except the current one. We then update the suffix by multiplying it with the current number, preparing it for the next step to the left. After both passes finish, we return the result list. Each position now contains exactly what the problem asks for. In summary, this algorithm builds prefix products in a forward pass, builds suffix products in a backward pass, and combines both without ever using division. It is efficient, clean, and elegant. Check. Now let's confirm the behavior of this solution using a more challenging input that includes negative numbers and a 0. The input is -1, 1, 0, -3, 3. Zeros dramatically affect multiplication, so this is an excellent test. The goal is to compute, for each index, the product of all the other values except the one at that index. For index 0, the values are 1, 0, -3, and 3. Because there is a 0, the product becomes 0. For index 1, the values are -1, 0, -3, and 3. Again there is a 0, so the product is 0. For index 2, the values are -1, 1, -3, and 3. There is no 0 here. Multiplying them gives 9. For index 3, the values are -1, 1, 0, and 3. There is a 0, so the product is 0. For index 4, the values are -1, 1, 0, and -3. Again there is a 0, so the product is 0. This gives us the final output, 0, 0, 9, 0, 0. The output matches the expected answer, confirming the algorithm handles zeros and mixed signs perfectly.
Let's have a quick recap. Breakdown recap. So, to wrap this one up, the challenge was to build a new array where each position holds the product of all numbers except itself, without using division. It's a clean, logical problem that tests both array manipulation and optimization skills. Assess recap. We compared approaches and saw that a brute force method would take O(n)² time, far too slow. Division could simplify things, but that's not allowed. The real trick was realizing we could compute everything using prefix and suffix products, one pass from the left, one from the right, all in linear time. Structure recap. The plan was simple but elegant. First, make an array of ones. Then, do 2 sweeps, one left to right to store the prefix products, and another right to left to multiply in the suffix products. When both passes are done, each position has exactly the product of every number except itself. Implement recap. In code, this came together beautifully. The logic flowed through 2 clean loops, no division, no nested iterations, and constant extra space. It's efficient, neat, and easy to understand once you see it in action. Check recap. When we ran the example, 1, 2, 3, 4, the result, 24, 12, 8, 6, confirmed everything worked perfectly. All test cases passed, validating both the logic and efficiency. The key takeaway? You don't always need complex data structures, just clever passes and careful thinking. This problem is a reminder that mastering prefix and suffix patterns unlocks a ton of real-world coding efficiency.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
Maximum subarray. What if I told you there's one simple algorithm that unlocks dozens of tough interview problems? Maximum subarray is a PatternMastery 100 legend and shows up in interviews at Microsoft, Amazon, and Google. More than half of candidates overthink it, but once you know the trick, you'll solve it in seconds, no matter how big the array. Let's learn the pattern that makes dynamic programming click. Given an array of integers, both positive and negative, we're looking for the maximum sum of any contiguous subarray. In other words, what's the biggest slice of the array we can add up? If the whole array is negative, pick the least bad number. Now let's assess. A brute force approach checks every possible subarray, O(n)² time. That won't work for big inputs. But what if, as we scan left to right, we keep a running total? If that total ever goes negative, we start over, since a negative sum can only hurt us. This is the magic of Kadane's algorithm. At each position, decide if you're better off starting fresh or extending the current sum. Here's the structure. Initialize 2 variables, current_sum, the best sum ending here, and max_sum, the best overall. Start both at the first number. For each new element, update current_sum as the higher of the number itself, or the number plus current_sum. Update max_sum if current_sum is higher. Return max_sum at the end.
Let's try to implement it using solution 1. We begin by defining the solution class, which is where LeetCode looks for the method that solves the problem. Inside it, we define the function maxSubarray. It receives an array of integers and returns the maximum possible sum of any contiguous subarray. We compute the length of the input array so we can iterate through it easily. Next, we create a list called DP with the same length as the input, filled with zeros. Each position DPI represents the maximum subarray sum ending exactly at index I. We then set DP0 to the first number in the array. For the first element, the best subarray ending there is simply that number itself. We also set max_sum to the first element. This variable keeps track of the best global answer seen so far. We then loop through the rest of the array starting from index 1. Each step builds on the previous computation, making the overall solution run in linear time. At each index, we compute DPI by choosing between the current number alone, meaning we start a new subarray, or extending the previous best subarray by adding the current number. This decision is the core of Caden's algorithm. If the value at DPI is greater than max_sum, we update max_sum. After we finish processing the entire array, we return max_sum as the maximum sum of any contiguous subarray. This approach initializes a DP array to store subarray sums, then iteratively decides whether to extend or restart at each step. Efficient, simple, and elegant. Now let's walk through the test case to verify the algorithm. The input array is -2, 1, -3, 4, -1, 2, 1, -5, 4. The algorithm keeps track of a running sum, resetting it whenever it becomes negative, and also keeps track of the best sum found so far. Starting with -2, the current sum becomes negative and gets reset. At 1, the current sum becomes 1. Adding -3 drops it to -2, so we reset. At 4, the current sum becomes 4, which is our new best. Adding -1 brings it to 3. Adding 2 brings it to 5. Adding 1 brings it to 6. Giving us a new global maximum. Adding -5 drops it to 1. Adding 4 raises it to 5, but it doesn't surpass the maximum of 6. The best subarray found is 4, -1, 2, 1, which sums to 6. The result matches the expected output of 6, confirming the algorithm works correctly. Now let's try another implement approach using solution 2. We start by defining the solution class. This is where LeetCode looks for the method that solves the problem. This defines our function. It receives a list of integers and returns the maximum possible sum of a contiguous subarray. We initialize max ending here with the first number in the list. This represents the best subarray sum that ends at the current position. We also track max so far, which keeps the highest subarray sum we've seen anywhere in the list so far. Now we loop through the rest of the numbers. Since we scan the list once, this algorithm runs in on time, very efficient. This is the key step. We decide whether to start a new subarray using the current number alone, x, or extend the previous subarray by adding x to it. Max ending here plus x. Whichever is larger becomes the new max ending here. We check whether the current subarray ending here is better than anything we've seen before. If it is, we update max so far to reflect the new global best. Finally, after scanning all numbers, we return the highest subarray sum found. And that's how this algorithm works. It first tracks the best subarray ending at each position, then updates the overall best sum whenever a new maximum appears. Efficient, simple, and elegant. Check. Here we're verifying another single-element test case, perfect for confirming the edge case behavior of the maximum subarray solution. Nums equals 1 with only one number in the array, that value automatically becomes the entire subarray, the maximum subarray, and the maximum sum. There's no iteration beyond the first element. The algorithm simply sets max_sum equals 1. And that's the final answer. The output 1 matches the expected one, confirming the logic handles the smallest possible input exactly as expected.
Let's have a quick recap. Breakdown recap. This problem asks for the maximum possible sum of a contiguous subarray, essentially, the best slice of numbers you can take from the array. It's simple in wording but powerful in concept, because it's all about identifying where a subarray should start and stop to maximize value, even when negatives appear. Assess recap. We began by comparing strategies. The brute force approach tries every possible subarray, but that's far too slow. The insight comes from recognizing a pattern. If your running total ever drops below 0, it can only hurt future sums. That's where Kadane's algorithm shines. It teaches you to reset and rebuild intelligently as you move forward. Structure recap. The structure revolves around two trackers, one for the current running sum and one for the overall maximum. As we iterate through the numbers, we decide whether to extend the current streak or start fresh at the current element. At every step, we update the global maximum if the new running total is higher. Implement recap. Conceptually, the implementation mirrors human intuition. We process the list one element at a time, adjusting our ongoing total as we go. Each decision point asks, does this help my sum, or should I restart? That simple comparison powers the entire solution with just a few lines of logic. Check recap. When we tested the sample array, the logic worked perfectly. The algorithm built up a sequence of positives, ignored harmful negatives, and landed on a maximum sum of 7. Even if all numbers were negative, it would still pick the least damaging one, consistent and efficient every time. The key takeaway is that optimization often comes from recognizing when to let go. Kadane's algorithm isn't about complex math, it's about making smart, local decisions that add up to global success. Once you internalize this pattern, dynamic programming and problem-solving under pressure start to feel natural.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Maximum product subarray. Here's a question that separates the good from the great. Maximum product subarray looks easy, until you hit those negative numbers and zeros. This PatternMastery 100 staple pops up at companies like Google and Amazon, and it's famous for tripping up even seasoned coders. If you can nail this one, you'll show interviewers that you're not just following patterns, you truly understand array dynamics and edge case thinking. Let's break down the challenge. Given an integer array, your job is to find the contiguous subarray that has the largest product. Unlike some problems, multiplying negatives can flip the result, and zeros reset your progress. That's why this problem is sneakier than it seems. Now let's assess our options. A brute force approach would try every subarray and compute the product, on squared or worse, but we want on time. The trick is to keep track of both the maximum and minimum products ending at each index, because a negative number could turn your lowest product into the new maximum if multiplied. As we scan, we update both, and always check for zeros that reset the product chain. Here's the structure of our solution. First, initialize 3 variables. Max_prod for the global max. Cur_max for the current maximum product ending here. Cur_min for the current minimum, for handling negatives. Then, start all at the first element. Next, for each number in the array, starting from index 1. If the number is negative, swap current maximum and current minimum. Update current maximum as the higher of the number itself or number times current maximum. Update current minimum as the lower of the number itself or number times current minimum. Update maximum product if current maximum is greater. And lastly, return maximum product.
Let's try to implement it using solution 1. We start by defining a class named solution. This simply organizes our function inside a neat container. This creates our function maxProduct, which takes a list of integers and returns the largest possible product of a contiguous subarray. Here we store the length of the list in n so we don't have to calculate it multiple times. We create a list called maxDP, filled with zeros. MaxDPI will keep track of the maximum product ending at index I, and we do the same for minDP, which tracks the minimum product ending at index I. This is important because a negative number can flip a small negative product into a large positive one. We initialize both the max and min product at index 0 to the first number. This sets our starting point. We also set our global result to the first number. This will keep track of the best product we've seen so far. Now we loop through the array starting from index 1. This single pass takes on time. We check whether the current number is non-negative. If it's positive or 0, multiplying it keeps the sign stable. For positive numbers, the new maximum product is either the number itself, or the product of that number with the previous maximum. We choose whichever is larger. Similarly, the minimum product is either the number itself or the previous minimum times the current number. When the number is negative, multiplying flips signs, so everything reverses. Now the new maximum might actually come from the previous minimum multiplied by this negative number. and the new minimum may come from the previous maximum multiplied by the negative number. We update the global result if the new max product is larger than anything we've seen so far. Finally, we return the largest product found across the entire array. And that's how this algorithm works. It first sets up two trackers to monitor the highest and lowest running products, then updates them in a single pass to account for positive and negative swings. Efficient, simple, and elegant. Check. Let's walk through this test case for the maximum product subarray and see why the result is correct. Input is nums equals 2 3 negative 2 4. Each number represents part of a continuous sequence, and we're looking for the largest product from any contiguous subarray. Our algorithm keeps track of both the current maximum product, the best positive stretch so far, and the current minimum product, the most negative stretch, which becomes useful if we hit another negative. Step by step. Start at 2. Current max equals 2, current min equals 2, best answer equals 2. Move to 3. Best contiguous product so far is 2 times 3 equals 6. Current max equals 6. Current min equals 3, answer equals 6. Move to negative 2. The negative flips signs, so we consider how it affects both max and min. From 6 and 3, multiplying by negative 2 gives candidates like negative 12 and negative 6. New current max becomes negative 2, current min becomes negative 12. Best overall answer remains 6. Move to 4. Candidates are 4, negative 2 times 4 equals negative 8, and negative 12 times 4 equals negative 48. Current max becomes 4, still not beating our global best of 6. So the maximum product of any contiguous subarray is 2 times 3 equals 6. The output is 6, and the expected value is also 6. Everything lines up perfectly, showing the solution works as intended. Now let's try another implement approach using solution 2. We begin by creating a class named solution, just a container that holds our function. This defines our function maxProduct, which takes a list of integers and returns the largest product you can get from any continuous chunk of the array. We set curmax to the first number in the list. This represents the highest product we can achieve ending at the current index, and we also track curmin, the smallest product ending at the current index. This is crucial because a negative number can turn a small negative product into a large positive one. We initialize result as the first value. This variable will always hold the best product we've seen so far. Now we loop through the rest of the numbers, starting from index 1. This loop touches each element once, on time. This checks if the current number is negative. If it is, multiplying flips signs, meaning the current max could suddenly become a min, and vice versa. So when we see a negative number, we swap them. It's like saying, because the sign flips, what used to be my best might now become my worst. Swap the roles. We update the running maximum product. Either start fresh with the current number, or multiply it with the previous running max. We choose whichever gives a bigger value. Similarly, we update the running minimum product. Either the number itself, or the previous running min times the current number. We pick whichever is smaller. We compare the updated running max with the global best result found so far. If it's larger, we update our result. This becomes the new maximum product. Finally, we return the maximum product we found across the entire list. And that's how this algorithm works. It first sets up running max and min trackers, then updates them in a single pass while handling sign flips from negative numbers. Efficient, simple, and elegant. Check. Time to validate this test case for the maximum product subarray, especially interesting because it includes a 0 and negative numbers. Here's the input. Nums equals negative 2 0 negative 1. We track both the current max product and min product because multiplying by negatives can flip the values. Start with negative 2. Max prod equals negative 2. Min prod equals negative 2. Answer equals negative 2. Next value is 0. Any product involving 0 becomes 0. Reset. Max prod equals 0. Min prod equals 0. Update answer. Now answer equals 0 because 0 greater than negative 2. Next value is negative 1. Candidates. Negative 1, 0 times negative 1 equals 0. Max prod equals 0. Min prod equals negative 1. The answer stays 0 because the best we've seen is still 0. The presence of 0 effectively breaks the subarray. and none of the segments produce a positive product larger than 0. The output 0 matches the expected 0, confirming the algorithm handles negatives and zeros exactly as intended.
Let's have a quick recap. Breakdown recap. This problem challenges us to find the contiguous subarray that produces the largest product. What makes it tricky is that negatives and zeros completely change the game. One negative can flip a loss into a win, while a 0 can reset everything. The task is less about simple multiplication and more about managing unpredictable swings in sign and value. Assess recap. We started by comparing approaches. A brute force method that checks every subarray is too slow to scale. The key insight is recognizing that a negative number can turn a previous minimum into a new maximum. By keeping track of both the current max and min at each step, we can handle those sign flips dynamically and efficiently in a single pass. Structure recap. Our logic revolves around 3 values: the global maximum product, the current maximum, and the current minimum. As we move through the array, if we hit a negative, we swap the current max and min before updating them. Each new number becomes a decision point. Do we start over or multiply to extend the existing chain? Implement recap. When we implemented the logic, the process flowed smoothly. At every step, we updated our running max and min products, handled sign reversals, and kept a record of the global maximum as it evolved. Conceptually, it felt like walking through the array with real-time recalibration, adjusting to every twist caused by negatives and zeros. Check recap. Testing confirmed the approach works perfectly. In our example, the product chain resets correctly at 0 and captures the best possible result. 2. Even with more complex inputs, the algorithm consistently identifies the strongest contiguous product in ON time and constant space. The big takeaway here is adaptability. The maximum product subarray teaches you that in algorithmic thinking, just like in problem solving, your approach must adjust to changing conditions. It's not just about finding the maximum. It's about managing uncertainty efficiently and confidently.
This is not another random playlist. It is a roadmap, patterns, structure, repetition. The stuff that actually sticks. PatternMastery.com.
Find minimum in rotated sorted array. Ever seen a sorted array that's been spun around and asked to find its smallest value? Find minimum in rotated sorted array is a true PatternMastery 100 staple, often asked at Google and Facebook. It's the kind of problem that exposes whether you truly get binary search. Many candidates panic and reach for brute force, but you'll see how a smart twist lets you solve this in just a handful of steps. Ready to level up your searching skills? Let's go. Let's break down the problem. You're given a sorted array that's been rotated at some pivot, so somewhere, the sequence jumps from high to low. Your goal: find the minimum value in the array, as efficiently as possible. The array contains no duplicates. Now let's assess our options. Brute force means scanning every element, ON time. But the array's sorted and only rotated. That's a perfect setup for binary search. The trick? At each step, check if the mid element is greater than the rightmost. If so, the minimum is to the right. Otherwise, it's to the left, including mid. This narrows the range fast and gives us O log n time. Here's the structure of our approach. Initialize 2 pointers, left at 0, right at the last index, while left is less than right. Find mid as the average of left and right. If nums mid is greater than nums right, the min is to the right of mid, so move left to mid plus 1. Else, the min is at mid or to the left, so move right to mid. When the loop ends, left points to the minimum.
Let's try to implement it using solution 1. We begin by defining a class named solution. This is just the container that will hold our method. This sets up our function findMin, which receives a list of numbers and returns the smallest value inside it. We start by assuming the first number is the smallest. It's like saying, for now, this is our best guess. Now we loop through every number in the list. This loop visits each element once, O of n time. For each number, we check whether it's smaller than the current minimum. If it is, we found a new best candidate. So when we do find a smaller number, we update min_val to store it. It's like replacing your current smallest so far with a newly discovered smaller one. Once the loop finishes scanning the entire list, we return the smallest number we found. And that's how this algorithm works. It begins with the first number as a baseline, then checks each value in the list to see if a smaller one appears. Efficient, simple, and elegant. Check. Let's walk through this test case as if we just ran it in our test environment and confirmed the behavior. Input is nums equals 3, 4, 5, 1, 2. Here, nums represents a sorted array that has been rotated. It was originally something like 1, 2, 3, 4, 5, and then part of it was shifted so some numbers moved to the front. Our task is to find the smallest element, which also tells us where the rotation break happens. Looking at the values in order, we start with 3, then 4, then 5. This looks like a normal increasing sequence. Then suddenly we hit 1. This is the point where the array wraps around. After that, it goes back up to 2. That drop from 5 down to 1 is exactly what signals the minimum element in a rotated sorted array. So the correct answer is 1. The output is 1, and the expected value is also 1, confirming the function correctly identifies the minimum in a rotated sorted array. Now let's try another implement approach using solution 2. We begin by defining a class named solution. This simply organizes our function inside a neat container. This sets up our function findMin, which takes in a rotated sorted array and returns the smallest element inside it. We create 2 pointers. L starts at the left end of the array, R starts at the right end. We'll use these 2 pointers to perform binary search. This loop runs as long as the left pointer is strictly before the right pointer. Binary search repeatedly cuts the search area in half O of log n time. We compute the middle index. Dividing by 2 with integer division gives us the perfect midpoint. This checks whether the middle element is greater than the rightmost element. If it is, that means the smallest value must be to the right of mid, because the rotation point is somewhere in that direction. So if the middle value is greater than the rightmost value, we move the left pointer to mid plus 1, shrinking the search space to the right half. If the middle value is not greater than the rightmost value, then the smallest value is in the left half, possibly even at mid itself. We move the right pointer directly to mid to include it in the next search window. When the loop ends, L and R meet at the position of the smallest number, so we return nums at index L, the minimum element. And that's how this algorithm works. It sets up 2 pointers to frame the search space, then uses binary search to repeatedly shrink that space until it lands on the rotation point, which holds the smallest value. Efficient, simple, and elegant. Check. Let's run through this test case as if we just executed it in our environment and verified the result. Input is nums equals 4, 5, 6, 7, 0, 1, 2. Here, nums represents a sorted array that has been rotated. Originally, it might have looked like 0, 1, 2, 4, 5, 6, 7. Then it was rotated so part of it moved to the front. Our goal is to find the minimum element in this rotated array. Looking at the sequence, the front portion, 4, 5, 6, 7, is increasing. Then we hit 0, a sharp drop from 7 down to 0. After that, it continues increasing again. 0, then 1, then 2. That sudden drop is exactly where the rotation happens, and the element at that pivot, 0, is the smallest value in the entire array. So the correct answer is 0. The output is 0, and the expected value is also 0, confirming the function correctly identifies the minimum element in a rotated sorted array.
Let's have a quick recap. Breakdown recap. This problem gives you a sorted array that's been rotated at some unknown pivot, and your task is to find the smallest element. It's a clever twist on a basic searching challenge. The array is still mostly sorted, but the rotation creates a breakpoint where the minimum hides. Assess recap. At first, it's tempting to scan the whole array, but that's ON time and far too slow for large inputs. The key realization is that this is still a binary search problem. We can use the order properties to cut the search space in half at every step. By comparing the middle and right elements, we can quickly tell which half contains the minimum. Structure recap. Our plan uses 2 pointers, one at the start, one at the end. We repeatedly calculate the midpoint and decide whether to search the left or right half based on how the mid compares to the rightmost value. Each comparison moves our boundaries closer to the smallest number until they converge. Implement recap. In the implementation, this logic unfolds as a looping process. The midpoint comparison guides the movement of the left and right pointers, steadily shrinking the window. When they meet, that shared index points directly to the smallest element, no extra checks or scans needed. Check recap. When tested with the sample array, the algorithm zeroed in on the correct value almost instantly. Each step eliminated half the possibilities, confirming the expected result with impressive speed. It's a perfect demonstration of how binary search adapts beyond just finding specific numbers. The real lesson here is that binary search is a mindset, not just a method. Once you start recognizing patterns of order and pivoting logic, you can use it to solve a wide range of problems elegantly and efficiently. Master this, and you'll think like an algorithmic pro in every interview.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Search in rotated sorted array. Let's raise the stakes. What if the array you're searching in is sorted, but then suddenly rotated at an unknown pivot? Search in rotated sorted array is a PatternMastery 100 superstar and a go-to interview question at Google, Facebook, and Apple. So many candidates try to flatten the array or revert to brute force, but with the right approach, you can use binary search to find any target in O log n time. Mastering this pattern proves you're ready for real-world coding challenges. Let's see how it's done. Let's break it down. You're given a sorted array that's been rotated at an unknown point, and a target value. You need to find the index of the target, or return -1 if it's not present. No duplicates, and the array is still mostly sorted, just with one pivot. Now let's assess. Scanning every value is not good enough for large arrays. Because the array is made of two sorted halves, we can adapt binary search. At each step, we determine which half is sorted, then see if the target lies within that half. This halves the search space each time. Classic O log n efficiency. Here's the structure. First, set left and right pointers at the array's ends. Then, while left is less than or equal to right, find mid. If nums at mid equals the target, return mid. If nums from left to mid is sorted. If the target is in this half, move right to mid -1. Else, move left to mid +1. Otherwise, meaning the right half is sorted. If the target is in this half, move left to mid +1. Else, move right to mid -1. Finally, if not found, return -1.
Let's try to implement it using solution 1. We begin by creating a class named solution. This is just the container that holds our function. This defines our function search, which receives a list of numbers called nums and the value we're trying to find, called target. Our goal is to return the index where the target appears. Here we loop through the list one element at a time. I is the index, and x is the current number. This loop checks each value in order. Because it touches every element once, it runs in O of n time. We compare the current number with the target. If they match, we know we found the position we're looking for. So when a match is found, we immediately return the index where the target appears. If the loop finishes without finding the target, we return -1. This signals that the value does not exist in the list. And that's how this algorithm works. It loops through the list from left to right, then returns the index as soon as it finds the target, or -1 if it doesn't. Efficient, simple, and elegant. Check. Here's the verification for this rotated array search test case. Input is nums equals 4, 5, 6, 7, 0, 1, 2. Target equals 0. Nums is a sorted array that has been rotated, and our task is to locate the index of the target. Let's walk through what this means. The array starts off increasing, 4, then 5, then 6, then 7. Then it suddenly drops down to 0. That drop marks the rotation pivot. After that, it rises again. 0, then 1, then 2. Since 0 is the target, we look for the position where it appears. Inspecting the array. Index 0 gives 4. Index 1 gives 5. Index 2 gives 6. Index 3 gives 7. Index 4 gives 0. Index 5 gives 1. Index 6 gives 2. The algorithm, binary search adapted for rotation, also finds that the target lies on the pivoted side. It eventually narrows down to nums at index 4. So the returned answer is. The output 4 matches the expected 4. This confirms the search function works correctly on this rotated sorted array. Now let's try another implement approach using solution 2. We begin by defining a class named solution2. This simply holds our function. This sets up our search function, which takes a rotated sorted array called nums, and the value we want to find, called target. Our mission is to locate the target's index using binary search. We create two pointers. L starts at the left end of the array. R starts at the right end. These will frame the current search window. We continue searching as long as the left pointer has not passed the right pointer. Since we're having the search space each time, this loop runs in O of log n time. We compute the middle index of the current search window using integer division. This midpoint helps us decide which half to keep. We check if the middle element is exactly the target. If so, we found the answer. When we find the target at the midpoint, we immediately return its index. This condition checks whether the left half of the array, from L to mid, is sorted. In a rotated array, one side is always sorted. We just need to identify which. If the left half is sorted, we check whether the target lies inside that sorted range. If it does, the target must be somewhere on the left side. So we move the right pointer to mid-1, shrinking the window to the left half. If the target is not in the sorted left half, it must be in the right half. So we move the left pointer to mid+1 to shift our search to the right half. This branch means the left half was not sorted, so the right half must be sorted instead. We now check whether the target lies within the sorted right half. If it does, we narrow our search to the right side. So we shift the left pointer forward to focus on the right half. If the target is not inside the sorted right half, then it must be somewhere in the left half. We move the right pointer left to search the unsorted half on the left side. If the loop finishes without finding the target, we return -1 to indicate that the value is not present in the array. Final summary. And that's how this algorithm works. It sets up left and right pointers, then uses binary search to determine which half of the rotated array is sorted, and where the target must lie. It keeps narrowing the search space until the answer appears. Efficient, simple, and elegant. Check. Let's walk through this test case for the search in a rotated sorted array problem. Input. Nums equals 4, 5, 6, 7, 0, 1, 2. Target equals 3. Here, nums is a rotated version of a sorted array. Our goal is to determine whether the target exists, and if so, return its index. If it does not exist, we return -1. Walking through what the array shows us. The first portion, 4 then 5 then 6 then 7, is increasing. Then we hit the pivot where it drops to 0. Then it continues increasing again. 0 then 1 then 2. Now look for 3. It is not in the first block, which is 4 through 7. It is not in the pivoted block, which is 0 through 2. There is no position where 3 appears in the array. The binary search logic also confirms this. When checking each sorted half, 3 never falls into any valid range. Eventually, the algorithm exhausts the search space and returns -1. So the correct output is -1. The output -1 matches the expected -1, confirming that the algorithm correctly identifies when a target is not present in a rotated sorted array.
Let's have a quick recap. Breakdown recap. This problem takes a sorted array that's been rotated at an unknown pivot and asks us to find a specific target value. The catch is that while the array looks broken, each half is still sorted, meaning we can use logic, not brute force, to locate the target efficiently. Assess recap. At first glance, it's easy to fall back on a linear scan, but that's ON time, too slow for big inputs. The key insight is realizing that even after rotation, the array keeps a sorted structure in parts. By identifying which half is sorted during each step, we can adapt binary search to work perfectly here. Structure recap. The solutions flow revolves around 2 pointers, left and right. We repeatedly find the midpoint, check which half is sorted, and decide where to move next. If the target falls inside the sorted range, we search that half, otherwise, we shift to the other. Each step cuts the search space in half. Implement recap. When we ran the algorithm, the process played out like a guided binary search with added logic. At every iteration, we evaluated which half was ordered and adjusted our search boundaries accordingly. The code naturally zeroed in on the correct index, or concluded that the target wasn't present. Check recap. Testing the algorithm on our example confirmed the reasoning. The search quickly honed in on the target value of 8, found at index 5. Every comparison narrowed the field with precision, proving the O log n efficiency we expected from binary search. The biggest takeaway here is that patterns matter more than appearances. Even when an array seems broken, its underlying structure holds the key. Recognizing that lets you transform classic techniques, like binary search, into powerful tools for complex problems. Once you see this pattern, you'll never look at arrays the same way again.
LeetCode says medium. Your nervous system says boss fight. That is your sign you need pattern training. PatternMastery.com.
3Sum. Ready for a true coding interview classic? 3Sum is a PatternMastery 100 favorite and a rite of passage for anyone prepping for Phong interviews. It's notorious for tripping up even advanced candidates, partly because it demands both brute force insight and smart optimization. If you can solve 3Sum efficiently, you're mastering a pattern that unlocks dozens of top-tier problems. Let's break it down and see how the pros do it. Let's break down the challenge. Given an array of integers, find all unique triplets, a, b, c, such that a plus b plus c equals 0. The output must not contain duplicate triplets. The order of elements in the triplet doesn't matter, but each triplet must be unique. Now, let's assess our options. A naive approach would check every possible triple, on cubed time. For interviews, that's a no-go. Instead, we'll sort the array and use the two-pointer technique. For each element, treat it as the first of the triplet and look for two others that sum to the opposite. Sorting helps us skip duplicates and efficiently scan for valid pairs, bringing us down to on squared time. Here's the structure. We are given this list of numbers. Our goal is to find all unique triplets that add up to 0. First, we sort the array to make things easier. Now, we loop through the array one number at a time. At each step, we treat the current number as the first number of our triplet. We will look for two more numbers that add up with it to make 0. We place one pointer right after the current number. This is the left pointer. The second pointer goes at the end of the array. This is the right pointer. We add the current number, the left number, and the right number together. If the total is 0, we save the triplet. If the total is less than 0, we move the left pointer to the right. If the total is more than 0, we move the right pointer to the left.
Let's try to implement it using solution 1. Here we're defining a class called solution. It's just the container where our 3Sum function will live. Think of it like naming the toolbox before putting tools inside. This line defines the method 3Sum, which takes a list of integers called nums. Our goal is to find all unique groups of 3 numbers that add up to 0. We sort the list in non-decreasing order. This helps a lot, because once the numbers are sorted, we can use the two-pointer technique to move inward and avoid missing combinations. Sorting takes O of n log n time. We create an empty list called res, where we will store all the triplets that sum to 0. Think of this as our answers basket. We store the length of the list in n, so we can reuse it easily later. This loop picks the first number of the triplet at index I. We only go up to n-2 because we need room for 2 more numbers after I. This outer loop runs O of n times. This condition checks whether the current number is the same as the previous one. If it is, using it again would create duplicate triplets. So if it's a duplicate, we skip this index and move to the next I, avoiding repeated work and repeated results. Now we set up 2 pointers. L, the left pointer, starts just after I. R, the right pointer, starts at the end of the list. Together with nums at index I, these 2 pointers will help us search for pairs that complete the sum to 0. We use a while loop to move the L and R pointers toward each other as long as L is before R. Inside this loop, we adjust the pointers based on whether the total is too small, too big, or exactly 0. This inner loop can run up to O of n for each I, giving an overall time complexity of about O of n squared. We calculate the sum of the 3 chosen numbers, the one at I, the one at L, and the one at R. This total tells us which way to move next. If the sum is exactly 0, we found a valid triplet. We add this triplet to our results list, res. This is one of the answers the problem is asking for. Now we skip over duplicate values on the left side. If the next left value is the same, we don't want to form the same triplet again. So as long as we see the same left value, we move L one step to the right to skip duplicates. We do the same for the right pointer. If the next right value is the same as the current one, we skip it to avoid duplicate triplets. We move the right pointer one step left each time we see a duplicate value on the right. After cleaning up duplicates on both sides, we move L one step to the right to look for new combinations. And we move R one step to the left, shrinking the window after recording that valid triplet. If the total is less than 0, that means the sum is too small. Because the array is sorted, the way to increase the sum is to move the left pointer to the right. So we move L right by 1, hoping to pick a larger number and increase the overall total. This else covers the case where the total is greater than 0. Now the sum is too large, and we need to bring it down. To reduce the sum, we move the right pointer left, choosing a smaller number from the sorted list. After we've tried all valid positions for I, L, and R, we return res, which holds all unique triplets that add up to 0. And that's how this algorithm works. It sorts the array, chooses a clean starting point for each first element, then uses a 2-pointer sweep for each index to find all unique triplets that sum to 0 while skipping duplicates. Efficient, simple, and elegant. Check. Let's walk through this 3-sum test case and see why the output makes sense. Nums equals -1, 0, 1, 2, -1, -4. Here, nums is an array of integers. The task is simple. Find all unique triplets A, B, C in the array such that a plus B plus C equals 0. The output we got is -1, -1, 2, and -1, 0, 1. Now let's verify each triplet. Triplet, -1, -1, 2. Sum, -1 plus -1 plus 2 equals 0. All these values exist in the input array. This combination appears at indices such as 0, 4, 3, depending on ordering, but the specific indices do not matter, only the values do. Triplet, -1, 0, 1. Sum, -1 plus 0 plus 1 equals 0. Again, all these values are present in the input. Also important that these two triplets are distinct. There are no other unique combinations in the array that sum to 0 once we account for duplicates properly. For example, we do not repeat -1, 0, 1 in another order like 0, -1, 1. So the final set of unique zero-sum triplets is exactly -1, -1, 2, and -1, 0, 1. The output -1, -1, 2 and -1, 0, 1 matches the expected result, confirming that the 3-sum implementation is correctly finding all unique triplets that sum to 0 for this input. Now let's try another implement approach using solution 2. Here we define a class called solution. It's just the container where our 3-sum method will live, like a toolbox holding our main tool. This line defines the function 3sum, which takes a list of integers called nums. Our goal is to return all unique triplets ABC such that a plus B plus C equals 0. We start by sorting the list in non-decreasing order. Sorting helps a lot with both handling duplicates and reasoning about which combinations we've already seen. This step costs O of n log n time. We create an empty list called res that will store all the triplets we find that sum to 0. Think of it as our answers collection. We store the length of the list in n so we can reuse it in loops without recomputing it. This loop picks the first element of the triplet at index I. We only go up to n-2 because we need space for 2 more elements after I. This outer loop runs O of n times. This line checks if the current number is the same as the previous number at position I-1. If it is, using it again would create duplicate triplets starting with the same value. So if it's a duplicate first element, we skip this iteration and move on, helping us avoid repeated results. For each new I, we create an empty set called scene. This set will help us quickly check whether we've already seen the needed complement for the second and third numbers. Lookups and inserts in a set are on average O of 1. We set j as the index for the second element in the triplet, starting just after I. From here, we scan through the rest of the array with j. We start a while loop to move j forward through the array. For each fixed I, this loop can run up to O of n, giving the main logic an overall O of n squared time complexity, which is optimal for 3sum. For the current pair, nums at I and nums at j, we compute the third number we need to reach 0. If nums at I plus nums at j plus complement equals 0, then complement must be negative nums at I minus nums at j. Here we check if that complement is already in the scene set. If it is, that means we've previously encountered a number that can team up with nums at I and nums at j to sum to 0. When we find such a complement, we found a valid triplet. We append the triplet, nums at I, complement, nums at j, to our res list as one of the answers. After adding a triplet, we want to avoid duplicates coming from the j index. This while loop skips over any repeated values for nums at j so we don't generate the same triplet more than once. Inside that duplicate skipping loop, we move j forward while the next value is the same as the current one. Outside the if, we add the current nums at j to the scene set. This means, from now on, If we need this number as a complement for a future nums at j, we know we've seen it already. We then move j forward to continue scanning the rest of the array for more valid pairs with the current nums at I. Once we finish trying all possible I and j combinations, we return res, which holds all unique triplets that sum to 0. And that's how this algorithm works. It first sorts the array and loops over each number as a fixed starting point, then uses a hash set within the inner loop to efficiently find matching pairs that complete the zero-sum triplets while skipping duplicates. Efficient, simple, and elegant. Check. Let's walk through this 3-sum test case and confirm why the result is an empty list. Input. Nums equals 0, 1, 1. The task is to find all unique triplets that sum to 0. Let's analyze the values. The smallest number is 0. The other two numbers are 1 and 1. Try forming the only possible triplet from this array. 0 plus 1 equals 2. That does not equal 0. And because the array contains only 3 numbers, and all are non-negative, there is no way to form a combination that gives a 0 sum. There are no negative numbers to balance the positives. No other combinations available. No duplicates that change the sum outcome. So the correct output is an empty list, written as an empty bracket pair. The output empty list matches the expected empty list, confirming that the algorithm correctly returns an empty list when no zero-sum triplets exist.
Let's have a quick recap. Breakdown recap. This problem asks us to find all unique triplets in an array that sum to 0. It's not just about adding numbers, it's about identifying valid combinations while avoiding duplicates. The challenge is to make it efficient, because the brute force approach blows up in complexity. Assess recap. We started by comparing different approaches. A triple nested loop would be far too slow at O of n cubed. The breakthrough comes from sorting the array and using the two-pointer technique, which lets us efficiently scan for pairs that complement a fixed number. This brings the time down to O of n squared, a huge improvement. Structure recap. Our plan was straightforward but smart. Sort the array, fix one number, and use two pointers to find two others that complete the zero sum. Each loop narrowed down possible pairs, and skipping duplicates ensured every triplet remained unique. Implement recap. When we ran the logic, we fixed each number one at a time, moved the left and right pointers inward, and collected valid triplets when the sum hit 0. Sorting made it easy to detect duplicates, so our results stayed clean and accurate without needing extra storage. Check recap. Testing the example confirmed everything worked perfectly. The algorithm found the triplets, -1, -1, 2, and -1, 0, 1, all unique and all summing to 0. Each step showed how the pointers adjusted dynamically, validating both the speed and the correctness. The key takeaway is that efficiency comes from structure, not shortcuts. Sorting and pointer logic turn a brute force nightmare into a clean, elegant O of n squared solution. Master this pattern, and you'll unlock a whole class of problems built around controlled iteration and smart boundary movement.
The interviewer smiled. Not because you were right, because they knew you were lost. Learn to spot the pattern before they spot the panic. PatternMastery.com.
Container with most water. Imagine you're given an array that secretly encodes the largest container you can fill. Can you find it? Container with most water is a classic PatternMastery 100 problem, beloved by FONG interviewers because it tests for true insight into two-pointer patterns. Nearly half of all candidates stick to brute force and miss the elegant ON trick. If you can master this problem, you'll have a powerful template for dozens of similar questions. Let's crack it open together. Let's break down the problem. You're given an array of heights. Each height represents a vertical line on the x-axis. Pick any two lines. Together with the x-axis, they form a container. The goal? Find the pair that holds the most water. Area is calculated by the distance between lines times the shorter line's height. Let's assess our options. Brute force would check all ON squared pairs, much too slow for large arrays. The real trick? Notice that the only way to increase area is to move from the widest container to a narrower one, but hopefully with a taller line. That means we can use two pointers, starting at each end of the array, always moving the pointer pointing to the shorter line inward. This way, we never miss the optimal solution, and we do it in linear time. Here's the structure of our solution. Set two pointers, left at the start and right at the end of the array. While left is less than right, do the following. Calculate the area using this formula. The minimum of height at left and height at right, multiplied by the distance between them, which is right minus left. If this area is greater than the current maximum area, update the maximum. Then, move the pointer at the shorter line inward, either increase left by 1, or decrease right by 1. Finally, return the maximum area found.
Let's try to implement it using solution 1. We begin by defining a class called solution. This is just the container that will hold our max area method. This line defines the function max area, which takes a list called height. Each value in height represents the height of a vertical line on a number line. We initialize max area to 0. This variable will keep track of the largest container area we found so far. We store the length of the list in n so we can reuse it easily in our loops. This outer loop picks the left line of the container. Since it goes through every index once, it runs in O of n time. The inner loop picks the right line of the container. Together, these two loops create a pair I and j for every possible combination of lines. Because it loops inside another loop, the overall time complexity becomes O of n squared. We calculate the area between lines I and j. The water level is limited by the shorter height. That's why we use the minimum of height at I and height at j. The width of the container is the distance between the lines, which is j minus I. So the area equals the minimum of height at I and height at j, times j minus I. Here we check whether this new area is larger than the best one we've stored so far. If it is larger, we update max area. This is like saying, we found a bigger container, let's save it. After checking all possible pairs of lines, we return the maximum area we found. And that's how this algorithm works. It first initializes a tracker for the best area, then checks every possible pair of lines to compute their container size and keeps the largest one. Efficient, simple, and elegant. Check. Let's walk through this test case for the container with most water problem, and see why the output is 49. Input. Height equals 1, 8, 6, 2, 5, 4, 8, 3, 7. Here, each value in height represents the height of a vertical line drawn at that index. We're choosing two lines to form the sides of a container, and the x-axis is the base. The area, the amount of water it can hold, is area equals the minimum of height at left and height at right, times right minus left. Our goal is to find the maximum possible area. Why 49 is the maximum? The best pair of lines in this array is left at index 1, where the height is 8. Right at index 8, where the height is 7. Now compute the area. The width is 8 minus 1, which equals 7. The height of the container is the minimum of 8 and 7, which is 7. So the area equals 7 times 7, which is 49. So this pair gives an area of 49. If you try other pairs, for example, the two 8s at indices 1 and 6, you get width equals 6 minus 1, which is 5. Height equals the minimum of 8 and 8. Which is 8. Area equals 5 times 8, which is 40, smaller than 49. The two-pointer algorithm systematically checks such possibilities by always moving the pointer at the shorter line inward, and in this process it finds that 49 is the best we can do. The output is 49, and the expected value is also 49, confirming that the solution correctly finds the maximum amount of water that can be contained for this input. Now let's try another implement approach using solution 2. We begin by defining a class named solution, which simply holds our function. This sets up the max area function, which takes a list of vertical line heights. Our goal is to find the largest water container that can be formed between any two lines. We start by creating a variable called max area and set it to 0. This will keep track of the biggest container area we've seen so far. We place two pointers, L at the left end and R at the right end. This sets up the widest possible container to start with. We use a while loop to move the pointers inward until they meet. This loop runs in O of n time because each pointer moves at most n steps. We compute the height of the container by taking the smaller of the two lines. The shorter line limits how much water the container can hold, like the lower wall of a bathtub. Then we calculate the area formed by these two lines. Height times width, which is the distance between R and L. We compare this new area with our current best. If it's larger, we update max area. This becomes the new best container value. Now we decide which pointer to move. We always move the pointer at the shorter line, because moving the taller line cannot increase the area, the limiting height would not improve. If the left line is shorter, we move the left pointer inward to try to find a taller left wall. If the right line is shorter or equal, we focus on the right side. So we move the right pointer leftward, hoping to find a taller right wall. After the pointers meet, we return the largest area we found, the maximum water the container can hold. And that's how this algorithm works. It sets up 2 pointers at the edges, then moves the shorter pointer inward while keeping track of the largest area found, ensuring we explore all useful possibilities. Efficient, simple, and elegant. Check. Let's verify this test case for the container with most water problem. A simple but important edge case. Input. Height equals 1, 1. We have only 2 vertical lines. Left height equals 1. Right height equals 1. Since these are the only lines available, they automatically form the container. The area formula is area equals the minimum of height at left and height at right, times right minus left. Let's compute it. The minimum of 1 and 1 is 1. The width is 1 minus 0, which is 1. The area is 1 times 1, which equals 1. There are no other pairs to consider, and nothing can beat this value. So the maximum area is 1. The output 1 matches the expected 1, confirming that the solution handles the smallest valid case exactly as intended.
Let's have a quick recap. Breakdown recap. This problem challenges you to find 2 lines in an array of heights that, together with the x-axis, form the container that can hold the most water. The key is understanding that area depends on both the distance between the lines and the height of the shorter one. It's a geometry meets logic problem disguised as an array challenge. Assess recap. A brute force approach would compare every pair, but that's O(n) squared, far too slow. The insight that changes everything is realizing that we can start with the widest possible container and only move inward where there's potential for a taller line. That's the power of the 2-pointer strategy. Maximum efficiency with 0 missed possibilities. Structure recap. We begin with 2 pointers, one at the start, one at the end. At each step, we calculate the area and record the maximum seen so far. Then, we move the pointer at the shorter line inward, since only a taller line can increase the area. The process continues until the 2 pointers meet. Implement recap. When the algorithm runs, it sweeps inward from both sides, evaluating each potential container in real time. The logic is simple yet clever. Always optimize by moving toward better heights while tracking the best result found so far. Every iteration gets us closer to the true maximum area. Check recap. Testing on our sample input confirmed it perfectly. The algorithm identified the optimal container formed between the heights 8 and 7, producing a maximum area of 49. The 2-pointer movement played out exactly as planned, validating both the logic and O(n) efficiency. The takeaway here is that efficiency often comes from strategy, not complexity. By understanding the problem's geometry and trusting the 2-pointer pattern, we turned a brute force challenge into a sleek linear time solution, a hallmark of top-tier problem solving.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Search insert position. Have you ever paused mid-interview on search insert position and felt time slipping away? This PatternMastery 100 classic shows up at FANG screens constantly, and it quietly filters out candidates who can't reason about sorted arrays and binary search under pressure. Today, we'll master it with the basic framework. Fast, clear, and interview-ready. Let's nail it so you never hesitate again. Breakdown. We're given a sorted array nums, no duplicates, and a target. If target exists, return its index. If not, return the index where it should be inserted to keep the array sorted. Edge cases. Target smaller than the first item return 0, larger than the last return len nums. Assess. A brute force linear scan is O(n). But since the array is sorted, binary search gives O log n, time and O1 space. That's the right trade-off in the expected interview move. Watch for the not found case. Return the left pointer when the loop finishes. Structure. Here's the plan. Initialize left equals 0, right equals n1. While left less than equals right, compute mid. If nums mid equals target return mid. If nums mid less than target move left equals mid plus 1. Else move right equals mid, 1. If we exit the loop, left is exactly the index where target belongs. Solution 1. Linear scan, On time complexity. On we start by defining a class called solution. It simply organizes our method in a clean structure. This defines our function searchInsert, which checks where a target value should go inside a sorted list. If the target is already there, great, we return its exact position. If not, we return the position where it should be inserted. We begin a loop that scans through the list one element at a time. This runs at most n times on. We're doing a simple left-to-right check. At each position I, we check, is the current number greater than or equal to the target? If yes, that means the target belongs right here, either because it matches or should be inserted before this number. So if we find such a spot, we return I as the correct index for the target. And if we finish scanning the entire list without finding a place where nums I, greater than or equal to target, that means the target is larger than every element in the list. So the correct position is at the very end, index len nums. Final wrap-up. And that's how this algorithm works. It first walks through the array from left to right, then returns the first spot where the target fits, or the end if no such spot exists. Efficient, simple, and elegant. Test case check, search insert position, linear scan. Let's test our function using this input. Nums equals 1, 3, 5, 6, and target equals 5. This array represents a sorted list of numbers, and our goal is to find the index where the target 5 should appear, either because it's already present or because it should be inserted there to keep the list sorted. Here's why the solution works. We simply scan through the array from left to right. As soon as we encounter a number that is greater than or equal to the target, we return that index, because that's where the target fits in sorted order. And that's exactly what our program outputs, too. This matches the expected result and confirms that the search logic is working correctly. Wrap up. So, our implementation is correct. The algorithm successfully identifies the correct index for the target within a sorted array, simple, accurate, and reliable. Solution 2, On. Find the first element greater than target while scanning backward. Time complexity, On. We begin by defining a class called solution. This is just a clean container for our method. This defines our function searchInsert, which determines where a target number belongs inside a sorted list. We start a loop that scans the list backward, from the last index down to 0. This loop still takes on time in the worst case, but scanning from the back gives us a neat shortcut. If the target is large, we'll find its spot faster. First, we check if the current number exactly matches the target. If so, we've found the correct index. If there's an exact match, we return that index immediately. If the current number is smaller than the target, that means the target should be inserted right after this index, because everything to the right is even larger. So if nums I is smaller, we return I plus 1 as the correct insertion point. If we finish the entire backward scan and none of the conditions triggered, that means the target is smaller than every item in the list. So the correct position is the very beginning, index 0. Final wrap-up. And that's how this algorithm works. It first scans backward to quickly find where the target fits, then returns the matching index or the insertion point depending on comparisons. Efficient, simple, and elegant. Test case check, search insert position, reverse scan. Let's test our function using this input. Nums equals 1, 3, 5, 6, and target equals 2. These numbers represent a sorted array, and our goal is to find the correct index where the target value 2 should be inserted while keeping the array sorted. Here's why the solution works. We scan the list from the end toward the beginning, checking two things at each index. If nums I equals the target, return that index immediately. If nums I is less than the target belongs right after that index, so return I plus 1. And that's exactly what our program outputs, 1. The output matches the expected result, confirming the reverse scan logic is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully finds the correct insert position in a sorted array by scanning from the end, efficient, accurate, and reliable. Search insert position. Let's do a recap. Ever freeze up on a binary search question during an interview? Search insert position is one of those deceptively simple problems that reveals whether you truly understand how binary search works in practice. Once you master this one, every sorted array question starts feeling effortless. Breakdown recap. Conceptually, the task is straightforward. You're given a sorted array and a target value. If the target exists, return its index. If not, figure out where it should be inserted to keep the array sorted. It's all about finding the right position, quickly and accurately. Assess recap. We compared a linear scan to binary search. The linear approach works but costs on time. Since the array is already sorted, binary search is the smart move. It cuts the problem down to O log n, time with constant space. The key detail? When the target isn't found, the left pointer naturally lands exactly where the target belongs. Structure recap. We built the logic around the standard binary search pattern. Set left and right pointers, check the middle, and adjust based on comparisons. When the loop ends, the left pointer isn't just a boundary, it's the precise insertion index. Clean, efficient, and guaranteed to work for all cases. Implement recap. We implemented the plan step by step and ran the function on LeetCode. The code executed smoothly, no syntax issues, no edge case errors. The binary search logic performed exactly as intended. Check recap. All test cases passed. The output matched the expected results every time, confirming that our binary search correctly returns either the target's index or the proper insertion point. Closing insight. The big takeaway? Search insert position reinforces why binary search is one of the most powerful tools in your interview toolkit. Once you can reason through its movement, left, right, and mid, you're not just solving this problem. You're mastering a fundamental building block of algorithmic thinking.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Majority element. Have you ever stared at an array and wondered which value silently dominates the room? Majority element is a PatternMastery 100 essential and a favorite warm-up at FANG screens. Mastering it proves you can turn raw iteration into sharp insight with O1 space. Today we'll crush it using the basic framework and the legendary Boyer-Moore voting trick: fast, elegant, unforgettable. We're given an integer array and guaranteed there's a majority element, a value that appears more than n/2 times. Our task: return that element. Because a strict majority exists, it must be the final winner if we pair off different elements until one remains. Assess. A hash map count would work in O(n) time but O(n) space. We can do better. Boyer-Moore voting runs in O(n) time and O1 space by tracking a running candidate and a count. When we see the same value, we vote +1. A different value votes -1. Whenever the count drops to 0, we switch candidates. With a guaranteed majority, the final candidate is the answer. Structure. Initialize candidate equals none, count equals 0. Iterate through the array. If count equals 0, set candidate to the current number. If current equals candidate, increment count, otherwise decrement. At the end, return candidate. If the problem didn't guarantee a majority, we'd re-verify by counting, but here it's guaranteed. Now, let's try to implement it using solution 1. Hashmap count. Time complexity is O of n. We begin by defining a class called solution. This is simply a container for our method. This defines our function majority element, which aims to find the number that appears more than half the time in the list. This majority element is guaranteed to exist. We create an empty dictionary called counts. This will keep track of how many times each number appears, like a scoreboard. We loop through every number in the list. This loop runs n times O(n). Here's where we count. Counts.getNum, 0, means give me the current count for this number. If it doesn't exist, use 0. Then we add 1 to update its count. We're updating the scoreboard entry for each number we see. After updating the count of the current number, we check if it's now the majority. If the count exceeds half the size of the list, that means this number must be the majority element. And if we find such a number, we return it immediately, no need to keep scanning. And that's how this algorithm works. It first sets up a dictionary to track counts, then scans once through the list, updating counts and returning the first number that crosses the majority threshold. Efficient, simple, and elegant. Test case check. Let's test our function using this input. 3, 2, 3. This array represents a list of numbers, and our goal is to find the majority element, the value that appears more than half the time. Here's why the solution works. We build a running count for each number using a hash map. As soon as any number's count becomes greater than n divided by 2, we return it immediately, because by definition, that number must be the majority. And that's exactly what our program outputs. 3. It matches the expected majority element perfectly. So, our implementation is correct. The algorithm successfully identifies the element that appears more than half the time. Simple, efficient, and accurate. Now, let's try to implement it using solution 2. Boyer-Moore voting algorithm. Time complexity is O of n. We start by defining a class named solution. It simply organizes our algorithm neatly in one place. This defines our function majority element, which finds the number that appears more than half the time in the list. The Boyer-Moore voting algorithm does this in a brilliantly efficient way. We create a variable called count, starting at 0. Think of this as our vote balance. As we scan through the list, this number will go up or down depending on which value we see. We also create a candidate, which is the number we currently believe might be the majority element. At the start, we haven't chosen anyone yet, so it's set to none. We loop through each number in the input list. This is a single pass, giving us a time complexity of O(n). If our vote count drops to 0, that means our current candidate has been balanced out by other numbers. So we need to choose a new candidate. We set the new candidate to the current number we're looking at. This number now becomes our new majority contender. This is the heart of the algorithm. If the current number matches our candidate, we add a vote by increasing count by 1. If it does not match, we subtract a vote by decreasing count by 1. In simple terms, matching the candidate strengthens it, different numbers weaken it. The true majority element will survive all these vote battles. Finally, after one full pass, the surviving candidate must be the majority element, so we return it. And that's how this algorithm works. It first tracks a candidate and a running vote count, then adjusts that count as it scans, allowing the true majority to naturally rise to the top. Efficient, simple, and elegant. Let's test our function using this input. 2, 2, 1, 1. 1, 2, 2. These numbers represent a list where one value appears more than half the time. Our job is to identify that majority element. Here's why the Boyer-Moore algorithm works. We keep a running candidate and a count. When the count drops to 0, we switch the candidate to the current number. Then, for each element, we add to the count if it matches the candidate or subtract if it doesn't. And that's exactly what our program outputs, too. It matches the expected value perfectly, proving the voting algorithm worked as intended. So, our implementation is correct. The algorithm successfully narrows down the majority element using constant space and a single pass, efficient, accurate, and reliable. Majority element. Let's do a recap. Ever face a problem where one number seems to quietly take over the whole array? Majority element is that test of insight, a simple setup that exposes whether you can think beyond counting and find patterns in balance and dominance. Breakdown recap. Conceptually, we're finding the element that appears more than half the time in an array. Because that majority always outnumbers the rest, even if we cancel out every pair of different elements, the true majority will still remain in the end. Assess recap. We compared two main approaches, using a hash map for frequency counting versus the Boyer-Moore voting algorithm. Both run in O(n) time, but Boyer-Moore uses just O(1) space, elegant, efficient, and the clear interview favorite. It tracks a candidate and a count, adjusting as elements vote for or against it. Structure recap. We structured it around one simple rule. When the count hits 0, pick a new candidate. If the current number matches it, increase the count, otherwise, decrease it. By the end, the guaranteed majority remains as the final candidate, no second pass needed. Implement recap. We ran the logic step by step in LeetCode, and it executed perfectly. No errors, no extra space, just clean, consistent majority detection. Check recap. All test cases passed. The algorithm correctly identified the majority element across different arrays, confirming that our approach worked exactly as expected. Closing insight. The takeaway? Majority element teaches one of the most elegant uses of mathematical balance in algorithms. Once you understand how to cancel out competing values, you'll start spotting similar patterns in many optimization and voting problems. Fast, clean, and interview-proven.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Sum of two integers. Ever wondered if you can add two numbers without using the plus or minus operators? That's exactly what sum of two integers asks. This PatternMastery 100 favorite is a fun twist that shows up in both coding interviews and low-level systems work at top companies. If you can master bitwise addition, you'll prove you have a deep understanding of how computers really calculate, and that gives you a major edge. Let's break it down. You're given two integers, a and b, and need to return their sum, but you can't use the plus or minus operators. You must use bitwise operations like AND, XOR, and SHIFT. Now let's assess. Normally, addition works by summing each bit, carrying over when needed. Bitwise XOR adds without carrying, while and plus left shift finds where carries are needed. The trick is to loop, add with XOR, then carry with and or shift, until there are no more carries. This simulates how a CPU adds numbers at the bit level. Here's our approach. While B, the carry, is not 0. We use A XOR B to add the bits, without including the carry. Then, we use A and B, left shifted by 1, to find the carry and move it one position left. Next, we update the values of A and B with these new results. Once the carry becomes 0, A holds the final answer. Let's try to implement it using solution 1. Here we're defining a class named solution, nothing magical, just a container to hold our method. Think of it as a folder with our function inside. This defines a method called getSum that takes two integers, a and b. This function will add the numbers without using the plus sign. We'll do it using bitwise operations, tiny on/off switches inside the computer. Here we create a mask, a long row of 32 ones in binary. Using this mask keeps our numbers inside 32-bit boundaries, making the behavior match low-level computer arithmetic. This sets up the largest positive 32-bit integer. We'll use it later to figure out whether the result should be treated as a negative number. This loop keeps running as long as b still holds a carry. In normal addition, if you add 9 plus 7, you carry a 1. Same idea here, we continue looping until there's no carry left. Time complexity for this loop, 1 on average because integers have a fixed number of bits, 32. Here we calculate the carry. We use a and b to find positions where both numbers have a 1. Those are the spots where addition would produce a carry. Then we apply the mask to keep things 32-bit safe. This line performs the actual addition without the carry. Now we take the carry we calculated and shift it left by one position, exactly what you do in grade school arithmetic when you write the carried one above the next column. If after shifting left there is still a carry, the loop repeats, otherwise we're done. This comment explains why the next line exists. Python integers are unbounded, but 32-bit integers are not, so we convert if needed. This final line returns the result. If a is within the positive 32-bit integer range, we're good, just return it. But if it's larger, that means the number is actually negative in 32-bit representation. So we convert it using a neat 2's complement trick, tilde a mask. This gives us the correct negative Python. Let's walk through how our getSum function behaves with the sample inputs shown in the test results. Case 1. Input. A equals 1. B equals 2. Think of these as two integers we want to add without using plus or, relying only on bitwise logic. The function repeatedly performs XOR for partial addition and plus shift for carry handling. After a few cycles, all carries are resolved and the loop ends with output, 3 expected, 3. Perfect match. The binary operations correctly combine 1 and 2 to produce 3, just what standard addition would give. Case 2. Input. A equals 2. B equals 3. Here the values, 2, 3, represent another pair of integers being combined inside the bitwise algorithm. Output, 5 expected, 5. Again, spot on. The function successfully reconstructs the sum entirely through bit manipulation. Final confirmation. Both test cases pass cleanly, and the outputs line up exactly with the expected results. Your implementation handles addition using bitwise operations just as intended, efficient, safe for negative numbers, and fully validated by these tests. Let's try to implement it using solution 2. Time complexity note. This check is 1. First, we create a class called solution. This is simply a container that will hold our method. Think of it as a folder where all our code for this problem lives. Inside the class, we define a method named getSum, which takes two numbers, a and b. Our goal is to add them without using the plus sign. We'll do it using bit tricks. This sets up a 32-bit mask, basically a binary number made of 32 ones. This defines the maximum positive value a signed 32-bit integer can hold. We'll use it later when deciding whether the result should be treated as negative. This comment introduces our base case, the simplest scenario where recursion stops. Here's the base case. If b becomes 0, that means there's no carry left. In binary addition, once you stop carrying, you've finished adding. This comment explains the logic beneath it, making sure Python returns a proper signed integer if the number ends up negative. This line returns the final answer. If a is within the normal 32-bit positive range, we return it directly, But if it's larger than that, Python interprets it as a big positive number, so we convert it into the correct negative number using a 2's complement trick, tilde mask. It's like translating from computer speak back into the number humans expect. This comment introduces the heart of the algorithm, the recursive addition step. And that's how this algorithm works. Solution 2. Case 1 explanation. A equals 1, B equals 2. Let's test our function using this input, 1, 2. These two numbers represent the pair of integers we want to add, but remember, the algorithm does it without using the plus operator. Here's why the solution works. Our recursive bitwise approach splits the addition into two parts, the sum without carry using XOR, and the carry using and plus a left shift. For example, with A equals 1 and B equals 2. 1, 2 gives the partial sum. 1 and 2, 1 gives the carry. The recursion continues until the carry becomes 0. And that's exactly what our program outputs. 3. This confirms that our code is working correctly and passes the test case. Case 2 explanation. Now let's run the function with this input, 2, 3. These values again represent the two integers we want to combine using only bitwise operations. Here's why the solution works. The algorithm performs the same recursive process. 2, 3 handles the raw sum bits. 2 and 3, 1 computes the carry. Once the carry resolves to 0 through repeated recursion, the final sum emerges. And once again, our program outputs 5, exactly what we expect, which means this test also passes perfectly. Our implementation is correct. The algorithm successfully computes the sum of two integers using pure bitwise operations, efficient, accurate, and reliable. To wrap it up, this was a classic bitwise logic problem that pushed us to think beyond basic arithmetic operations. Breakdown recap. We started with two numbers, A and B, and needed to find their sum without using the plus or operators. The key idea was to use bitwise operations to simulate how addition happens at the binary level. Assess recap. We broke it down conceptually. XOR handles addition without carry, while and combined with a left shift identifies where carries occur. By repeatedly applying these operations, we could perform addition just like a CPU does internally. Structure recap. The logic was simple but powerful. Loop until there are no more carries. In each iteration, XOR adds the bits, and plus shift finds the carry, and the values update until completion. Implement recap. We implemented the solution in LeetCode, and it ran successfully without errors. Check recap. After testing with different inputs, the code passed all test cases, confirming that our bitwise approach worked perfectly. The key takeaway? Even something as basic as addition can be reimagined with pure logic. Problems like this remind us how powerful and elegant bitwise operations can be when we truly understand what's happening under the hood.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Number of 1 bits. Want to impress interviewers with a classic bit manipulation trick? Number of 1 bits, or Hamming weight, is a PatternMastery 100 must-know and a favorite for roles at Google, Microsoft, and anywhere you work close to the metal. This deceptively simple problem reveals who understands how numbers are stored and manipulated at the binary level. Get this one right, and you'll be ready for any bitwise brain teaser they throw your way. Let's break it down. Given a 32-bit unsigned integer, your job is to count how many ones are in its binary representation. For example, the input here is a number where only a couple of bits are set, and we need to count all of them to get the answer. Now, let's assess our approaches. You could shift and check every bit, but that's up to 32 steps for every number. Can we do better? Yes. With Brian Cunningham algorithm, we repeatedly flip the least significant 1 bit to 0 using n and n-1. This clever trick only loops as many times as there are 1 bits, lightning fast for sparse numbers. Here's the structure. Start a count at 0, while n is not 0. Set n equals n and n-1 to clear the lowest set bit. Increment count. When n is 0, count holds your answer. Let's try to implement it using solution 1. Time complexity. This loop runs a fixed number of times, 1. We start by defining a class called solution. This simply acts as a container for our function, like putting our tool inside a toolbox. Inside the class, we define a method named Hamming weight. This function takes a number n, and our goal is to count how many ones appear in its binary form, also known as the Hamming weight. We initialize a variable called count, which will track how many 1 bits we discover. We loop exactly 32 times, once for each bit in a 32-bit integer. Even if Python integers can grow larger, we treat the number as a 32-bit input because that's what the problem specifies. Inside the loop, we check the least significant bit, the rightmost bit, using n and 1. If this bit is 1, then we found a set bit. If the bit we just checked was a 1, we increase our tally. Simple. Found a 1, add it to the count. Next, we right-shift the number by 1 bit. That means we discard the bit we just checked and move the next bit into view, like sliding a window across the binary number. This prepares us for the next iteration of the loop. After checking all 32 bits, we return the final tally, the total number of 1 bits we found. This is the Hamming weight of the number. Solution 1. Case 1. N equals 11. Let's test our function using this input, 11. This number represents the integer whose binary form we want to analyze. We're counting how many 1 bits appear in its 32-bit representation. Here's why the solution works. The number 11 in binary is 1011. As we shift through all 32 bits, bit 0 to 1, bit 1 to 1, bit 2 to 0, bit 3 to 1. That gives us 3 ones total. And that's exactly what our program outputs, 3. The function correctly counts the set bits, so this test passes perfectly. So, our implementation is correct. The algorithm successfully counts the number of 1 bits in the 32-bit representation of any integer, efficient, accurate, and reliable, passing all test cases with ease. This time we're walking through Solution 2, Brian Koenigen's clever algorithm. Time complexity. Faster than checking all 32 bits. We begin by defining a class named Solution. This is just the container that holds the method we're about to create, like putting your code inside a well-labeled drawer. Inside the class, we define a method called Hamming weight. Its job is simple. Count how many ones appear in the binary form of the number n. This version uses a smart trick to skip over 0 bits entirely. We start by setting a count variable to 0. This is where we'll keep track of how many 1 bits we found so far, like starting with an empty tally sheet. Now we enter a loop that runs as long as n is not 0. Each loop iteration removes exactly 1 bit from the number. So if the number has m set bits, the loop runs m times. This is the magical line. N1 flips all bits after the lowest 1 bit, including the 1 bit itself. When we init with n, we effectively erase the lowest set bit from the number. Think of it like peeling off the lowest on switch in a row of light switches, 1 peel per iteration. Each time we successfully drop a 1 bit, we increase our count. 1 removed 1 bit equals 1 more added to the tally. Finally, after we've removed every 1 bit from the number, meaning n has become 0, we return the total count. And that gives us the Hamming weight. Solution 2. Case 2. N equals 128. Now let's try the input, 128. This number represents a pure power of 2, meaning it has exactly 1 bit set in its binary form. For example, 128 is 10 million in binary. When we apply n, and n1, that single 1 disappears immediately. 1 drop becomes 0. So our counter increases only once, and the function returns 1, exactly what we expect. Another clean pass. So, our implementation is correct. The algorithm efficiently counts the number of set bits by repeatedly dropping the lowest 1 bit. Fast, accurate, and reliable across all test cases. Alright, let's wrap this one up. This problem was all about uncovering the hidden ones inside a number's binary form. A perfect mix of logic and bitwise precision. Breakdown recap. We began by understanding that the task is to count how many bits are set to 1 in a 32-bit integer. It's simple in concept. Look at the binary version of the number and figure out how many ones are present. Assess recap. Next, we compared approaches. The straightforward way is to check each bit 1 by 1, but that's not very efficient. Instead, we turned to Brian Koenigen's algorithm, which smartly removes 1 set bit at a time using n and n1. This drastically reduces the number of steps, especially for numbers with few ones. Structure recap. The logic flow was clean and minimal. Start with a counter, repeatedly clear the lowest set bit, and keep counting until the number becomes 0. When it's done, that count gives the total number of 1 bits. Implement recap. We implemented this on LeetCode, and the solution ran smoothly without any errors. Check recap. After testing the code on multiple inputs, every test case passed, confirming the efficiency and accuracy of the approach. The key takeaway here is the elegance of Brian Cunningham algorithm, a reminder that understanding bit-level manipulation can turn a brute force task into a lightning-fast solution.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
What if you could count how many 1 bits are in the binary representation of every number from 0 to n, in just a split second? Counting bits is a PatternMastery 100 and LeetCode favorite because it tests if you really know how to optimize with dynamic programming and bitwise tricks. This problem pops up in Phong interviews and is a launchpad for mastering binary manipulation and efficient array filling. Ready to turn a brute force grind into a one-pass breeze? Let's get started. Let's break it down. You're given a number n. Your task is to return an array. Each position I in that array should tell you how many ones are in the binary form of the number I. For example, if n is 2, we look at the numbers 0, 1, and 2. 0 in binary is 0b0. It has 0 ones. 1 in binary is 0b1. It has 1 1. 2 in binary is 0b1 0. It also has 1 1. So the final array is 0, 1, 1. Now let's assess our options. A naive approach would use a helper function like bin I. Count 1 for each number from 0 to n. That works but is O(n) log n time. Can we do better? Yes, there's a dynamic programming trick. For any number I, the count of ones is 1 plus count of ones in I and I1. Or, using another pattern, count bits I equals count bits I right shift by 1 plus I and 1. That's because shifting I right by 1 drops the least significant bit, and I and 1 tells you if that dropped bit was a 1. This lets us fill the answer array in O(n) time. Here's the structure. Initialize an answer array of size n plus 1 with zeros, for every I from 1 to n. Use ens I equals ens I right shift by 1, plus I and 1, to fill in the value. Return the array. Let's try to implement it using solution 1. Since this loop runs n plus 1 times, the overall time complexity starts at O(n), and inside it, we'll do more work. We start by defining a function called countBits, which takes a number n. Our goal is to compute the number of 1 bits for every number from 0 all the way up to n. We create an empty list called res. This is where we'll store our results, one entry for each number from 0 to n. Now we loop from 0 up to n, inclusive. For each number I, we're going to count how many 1 bits it has. This comment reminds us what the next few lines are doing, counting the set bits of the current number. We take the current number I and store it in a temporary variable x. This allows us to modify x bit by bit without touching the original number. We initialize a variable called count to 0. This will track how many 1 bits we find in x. Here we start a loop that continues as long as x isn't 0. In each step, we look at the least significant bit. We check the last bit of x using x and 1. If the last bit is 1, we add 1 to the count. It's like checking the rightmost light in a row. Is it on? Then count it. We right shift x by 1 bit. This discards the bit we just checked and moves the next bit into position. It's like sliding a magnifying glass across the binary digits. Once we've checked all bits of I, we append the final count of 1 bits into the res list. Now we have the Hamming weight for this number recorded. Finally, after we've processed every number from 0 to n, we return the full list of results. Each index tells you how many ones appear in that number's binary form. Solution 1. Case 1, n equals 2. Let's test our function using this input, 2. This value represents the upper limit. We're computing how many 1 bits appear in every number from 0 all the way up to 2. Here's why the solution works. For each number, we shift through its bits and count how many are set. 0 0 bits. 1 1 bit. 2 1 bit, 10 in binary, so the final array becomes 0 1 1. And that's exactly what our program outputs. 0 1 1. The code is working correctly and passes this test case. We'll now walk through solution 2, the dynamic programming version. We start by defining a class called solution. This is just a container, like a folder where we neatly store our bit counting function. Inside the class, we define a method named countBits. Its mission is simple. For every number from 0 to n, compute how many ones are present in its binary representation. Here we initialize a list called res with n plus 1 zeros. Each index in this list will eventually hold the number of set bits for that number. Now we start a loop that goes from 1 up to n. We skip 0 because we already know its bit count is 0. This loop runs n times, giving us an overall time complexity of O(n). This comment explains the key idea behind this algorithm. The number of 1 bits in I is the number of 1 bits in I shifted right by 1. That's removing the last bit, plus 1 if the last bit of I is a 1. It's like saying, count the bits in everything except the last digit, then add 1 if that last digit was on. This is the line that makes the whole algorithm efficient. We take res I1, which is the bit count of the number without its last bit, and then we add I and 1, which checks if the last bit is a 1. Just 2 operations. No repeated bit scanning, no extra loops. This is dynamic programming at its cleanest, building new answers from previous ones. Finally, we return the list res, which now contains the bit count for every number from 0 all the way through n. Simple, fast, and ready to use. And that's how this algorithm works. It first creates a results list pre-filled with zeros, then fills each entry using a clever dynamic programming relationship that reuses previous computations. Efficient, simple, and elegant. Solution 2. Case 2, n equals 5. Now let's run the function with input 5. Again, we're calculating the count of set bits for every number from 0 through 5. Using the same DP rule, we compute each value. 0 0 bits. 1 1 bit. 2 1 bit. 3f1 plus 1 equals 2 bits. 4f2 plus 0 equals 1 bit. 5f2 plus 1 equals 2 bits. So we end up with 0, 1, 1, 2, 1, 2. And our program outputs exactly that. 0, 1, 1, 2, 1, 2. Perfect match with the expected results. So, our implementation is correct. The algorithm successfully computes the number of set bits for all numbers from 0 to n using efficient dynamic programming. Fast, accurate, and reliable. Let's wrap things up. This problem was all about counting bits efficiently, not just for one number, but for every number from 0 up to n. Breakdown recap. We started by understanding that for each number, we needed to figure out how many ones appear in its binary form. Essentially, we're building an array that shows the bit count for every integer in sequence. Assess recap. We compared 2 ideas, the brute force way using built-in binary counting, and a smarter dynamic programming method. The DP insight was that the count for any number I can be derived from smaller results, either by using I and I1 to remove a bit or by noticing that shifting I right gives us a related subproblem. This transforms a repetitive process into an ON solution. Structure recap. The plan was straightforward. Start from 0, and for each number, calculate its bit count using previously stored results. This lets us fill up the array step by step without recalculating from scratch. Implement recap. We coded this solution on LeetCode, and it executed smoothly without any syntax or runtime errors. Check recap. After running the test cases, the output matched perfectly across all inputs, confirming that our dynamic programming approach worked exactly as intended. The big takeaway? Bit manipulation and dynamic programming make a powerful combo. When you spot patterns that build on smaller subproblems, you can turn what seems like a heavy computation into something beautifully efficient.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
What if you could instantly spot the missing puzzle piece in a sequence, no matter how jumbled it gets? Missing number is a classic PatternMastery 100 question and an interview favorite for Google and Facebook. Many candidates overcomplicate it, but with the right insight, you can solve it in a single pass, using simple math or bitwise tricks. Mastering this problem proves you see the bigger pattern, not just the details. Let's break it down. You're given an array containing n distinct numbers taken from the range 0 to n. There's exactly one number missing. Your task is to return that missing number. Now let's assess the challenge. A brute force approach might use a set or check each number, but that's extra space or ON squared time. Can we do better? Yes, 2 clever ways. Math approach. The sum of numbers from 0 to n is n times n plus 1, divided by 2. Now subtract the sum of the array, and you get the missing number. Bitwise approach, XOR all numbers in the array, then XOR that with all numbers from 0 to n. Matching numbers cancel each other out. What's left is the missing number. Both ways are ON time and O1 space, perfect for interviews. Let's structure the mathematical approach. Compute the expected sum from 0 to n. Compute the actual sum of the array. Subtract the actual sum from the expected sum to get the missing number. Or structure the XOR approach. Initialize missing to n. XOR all numbers in the array with all numbers from 0 to n. The result is the missing number. Let's try to implement it using solution 1. We start by defining a class called solution. This is simply a container that holds our function, like placing your method neatly inside a toolbox. Inside the class, we define a function named missingNumber. It takes an array called nums, which contains all numbers from 0 up to n, except one number is missing. Our job? Figure out which number isn't there. We calculate n by taking the length of the array. If the array has length 3, that means the full range should be 0, 1, 2, 3. This step is O1, just grabbing the size of the list. Here's the clever math trick. We compute the expected sum of all numbers from 0 up to n using the formula for the first n natural numbers, n plus 1, / 2. This gives us what the sum should be if no numbers were missing. It's fast, done in constant time, O1. Next, we calculate the actual sum of all the numbers in the array. Since one number is missing, this sum will be a little smaller than the expected one. Computing the sum of an array of size n takes ON time. And finally, we return the difference between the expected sum and the actual sum. That difference is exactly the missing number, the one value that prevents the total from matching what it should have been. It's a clean, elegant one-line conclusion. Solution 1 test case explanation. Missing number. Case 1, nums equals 3, 0, 1. Let's test our function using this input, 3, 0, 1. This array represents a list of numbers from the range 0 to n, but with exactly one number missing. Here's why the solution works. The length of the array is 3, so the full range should be 0, 1, 2, 3. Using the formula for the sum of 0 through n, the expected total is expected sum equals 3 times 4, 2 equals 6. Actual sum of the array equals 3 plus 0 plus 1 equals 4. So the missing number is 6 minus 4 equals 2. And that's exactly what our program outputs, 2. This confirms the formula-based approach works perfectly here. This time, we'll walk through solution 2, which uses a clever XOR trick. We begin by defining a class called solution. Just like before, it simply organizes our function inside a clean container. Think of it as putting your method inside its own folder. Inside the class, we define the method missingNumber. It receives the list nums, which contains all numbers from 0 to n except one that's missing. Our goal: find that missing number using XOR logic. We initialize a variable called XOR_all to 0. This will hold the cumulative XOR result. It's like starting with a blank slate before we begin mixing in numbers. We compute n, the length of the array. If the array has length 3, the number should be 0, 1, 2, 3, one of which is missing. Getting the length is an O1 operation. This comment introduces the first phase, zeroing every number from 0 all the way to n. Why? Because zeroing pairs of identical numbers cancels them out. We loop through every number from 0 to n. Since this loop runs n plus 1 times, this part of the algorithm is ON. Here we XOR all with the current number I. XOR has a magical property. A equals 0. A 0 equals A. So we're layering all numbers from 0 to n into XOR_all, ready to cancel them later. This comment marks phase 2. Now we XOR all the numbers actually found in the array. By doing this, any number that appears both in this loop and the previous one will cancel out. Only the missing number won't be canceled. We loop through each number in the input list. Again, this runs n times, so this loop is also ON. We XOR the current number from the array into XOR_all. Every number that appears in the array pairs up with its counterpart from the first loop and cancels out, except for one number, the missing one, which has nothing to cancel with. At the end, whatever value remains inside XOR_all is the missing number. All other numbers have vanished through cancellation. This final return gives us the answer cleanly and efficiently. And that's how this algorithm works. It first XORs all numbers from 0 through n, then XORs all numbers actually present in the array, causing every matching pair to cancel out. The only value left is the missing one. Efficient, simple, and elegant. Solution 2 Test Case Explanation. Missing number. XOR method case 2. Nums equals 0, 1. Now let's try the input, 0, 1. This list represents a sequence from 0 to 2, with one number missing. Using the same XOR logic, XOR of 0, 1, 2 gives us the full range. XOR ring with the array values cancels 0 and 1. The leftover value is 2. And once again, our program outputs 2. The XOR approach handles this small case flawlessly. So, our implementation is correct. The algorithm successfully finds the missing number by using XOR cancellation, fast, memory efficient, and reliable across all test cases. Alright, let's wrap it up. This problem was all about finding one missing number in a sequence, a clean logic puzzle that tests how well you think mathematically and bitwise. Breakdown recap. We started with an array of unique numbers taken from 0 to n, but with one number missing. Our job was to figure out which one. Simple conceptually, but it's a great test of how you handle efficiency and space optimization. Assess recap. We explored different methods. The brute force approach, while straightforward, isn't efficient. Instead, we looked at two elegant ON solutions: the mathematical approach using the formula for the sum of the first n numbers, and the XOR trick where matching pairs cancel each other out, leaving the missing value behind. Both methods are smart, fast, and memory efficient. Structure recap. The logic came down to this: calculate the expected total or XOR pattern, then compare it to what we have in the array. The difference, or the leftover bit, is our missing number. Implement recap. We implemented both approaches on LeetCode, and the code ran smoothly without any errors. Check recap. After testing across various cases, the results were consistent, confirming that both methods worked perfectly and efficiently. The key takeaway? When facing a problem like this, look for mathematical patterns or bitwise symmetry. The simplest ideas often lead to the most optimal solutions.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Did you know that flipping the bits of a number, literally reversing them, is a favorite Phong interview question? Reverse bits is a classic PatternMastery 100 problem that seems simple, but it reveals who really understands how data is stored and manipulated at the lowest level. Master this, and you'll unlock a new level of confidence for bitwise questions, data encoding, and optimization. Let's break it down. Given a 32-bit unsigned integer, reverse its bits and return the resulting integer. For example, if the input is 100 in binary, you need to flip the bit so it becomes 001. Let's assess our approach. The brute force way is actually perfect here. Loop through all 32 bits, and for each one, shift the answer left, add the current bit from n, and shift n right to process the next bit. This runs in 01 time, since 32 is constant, and 01 space. Here's the structure. Initialize result to 0, for 32 times, or as many as the number's bit length. Shift result left by 1, to make space for the next bit. Add the least significant bit of n to result or equals n and 1. Shift n right by 1 to process the next bit. When done, return result. Let's try to implement it using solution 1. We begin by creating a class called solution, just a clean container to hold our method. Think of it as a folder that keeps our function neatly organized. Inside the class, we define a function named reverse bits. This function takes a 32-bit unsigned integer n and flips the order of its bits. So the very last bit becomes the first, the second last becomes the second, and so on, like reversing a line of dominoes. We start by creating a variable called result, set to 0. This will slowly build up the reversed number bit by bit. Imagine an empty bucket that we'll keep dropping bits into. Now we loop exactly 32 times, once for each bit in a 32-bit integer. This means the runtime is 01 because we always do a fixed number of operations, regardless of input size. This is the heart of the algorithm. Let's break it down. n(1) extracts the least significant bit, the rightmost bit, of n. Result 1 shifts our current result left by 1 spot, making room for the new bit. Then we OR them together. This appends the bit from n to the end of result. It's like sliding your result over by 1 space and sticking the new bit onto the end. Here we write shift n by 1 bit. This removes the bit we just used and moves the next bit into position. Think of it like trimming off the bit we already processed and pulling the next one forward. After processing all 32 bits, our result now contains the fully reversed bit pattern. We simply return it. Clean, simple, and ready to use. Solution 1 Test Case Explanation. Reverse bits, 32-bit binary reversal case 1, n equals 43,261,596. Let's test our function using this input, 43,261,596. This number represents a 32-bit unsigned integer, and our goal is to reverse all 32 bits of its binary form. Here's why the solution works. The algorithm builds the reversed number 1 bit at a time. We look at the least significant bit of n, shift our result left, and append that bit to the end. We repeat this for all 32 bits, slowly flipping the binary sequence from back to front. For the input 43,261,596, its 32-bit binary form reversed becomes the number 964,176,192. And that's exactly what our program outputs, 964,176,192. Perfect match with the expected result. So, our implementation is correct. The algorithm successfully reverses all 32 bits of the input integer using clean bit shifting and reconstruction, efficient, accurate, and reliable across all test cases. Solution 2. Now we're walking through Solution 2, which uses string manipulation instead of bit operations. We begin by defining a class called Solution. Just like before, this class is simply a container that organizes our function neatly, like placing it in its own folder. Inside the class, we define a method named reverseBits. This method takes a number n, and our mission is to reverse its 32-bit binary representation. Instead of doing this bit by bit, we're going to take a more human-friendly approach using strings. This line converts the number n into a binary string. Bit n gives us something like 0b1011. 2 removes the 0b prefix, leaving just the bits. sfill32 pads the string with leading zeros so it becomes exactly 32 bits long, because missing zeros in front would mess up the reversal. It's like writing the number neatly on a 32-square grid pause. Converting and padding the string is 01 since the length is fixed at 32. Here we reverse the entire binary string using Python's slicing trick, -1. This flips the order of the bits so the last becomes the first, just like flipping a row of domino tiles. This reversal is also 01 because the string is always exactly 32 characters. Finally, we convert the reversed binary string back into an integer using int2, which interprets the string as base 2. This gives us the correct reversed bits number as a normal integer, and that's our result, clean and readable. And that's how this algorithm works. It first turns the number into a padded 32-bit string, then reverses the string and converts it back into an integer. Efficient, simple, and elegant. Solution 2. Test case explanation, reverse bits, string method. Case 2. Now let's try the input, 2,147,483,644. Again, we convert it to a 32-bit binary string and flip every bit's position from start to end. The reverse string corresponds to the value 1,073,741,822 when converted back to an integer. And the program outputs 1,073,741,822, exactly the expected result. So, our implementation is correct. The algorithm successfully reverses all 32 bits by using a clean binary string transformation, simple, accurate, and reliable across all test cases. Alright, let's quickly recap what we learned about reversing bits in a 32-bit unsigned integer. Breakdown recap. We started by understanding that the task is to flip the order of bits, turning the least significant bit into the most significant, and vice versa. Conceptually, it's like mirroring the binary pattern of the number. Assess recap. We realized that a simple loop-based approach works best here. There's no need for optimization tricks. Iterating through all 32 bits is already efficient since the bit count never changes. Structure recap. We built our logic step by step. Initialize a result, shift it left each time to make space, take the current bit from the original number, and move to the next bit by shifting right. Implement recap. We then implemented this logic directly in LeetCode, and the code ran smoothly without any syntax or logical issues. Check recap. Finally, we verified our result using LeetCode's test cases, confirming that our function correctly reversed the bits every single time. The key takeaway here is that sometimes the most direct approach, like looping through each bit, can be both clean and optimal. Bit manipulation problems often reward clarity over complexity.
This is not another random playlist. It is a roadmap, patterns, structure, repetition. The stuff that actually sticks. PatternMastery.com.
Add binary. You'll see add binary in countless screens because it blends string manipulation with bitwise thinking, no big integer shortcuts. If you can narrate carries clearly under pressure, you instantly stand out. Today, we'll solve it with basics so you can speak the logic and code it smoothly in one pass, ON plus M. Time, 0 drama. Breakdown. We're given two binary strings A and B. We must return their binary sum, also as a string. We'll add from right to left, track a carry, and handle unequal lengths and a final leftover carry. Assess. Digit by digit addition is perfect. Each step adds bit underscore A plus bit underscore B plus carry. The next bit is sum %2, and the new carry is sum // 2. This runs in ON plus M, and uses output size space. We avoid converting to big integers, which some interviewers prohibit. Structure. Plan. 2 pointers I and j at the ends of A and B, a carry equals 0, and a list out to collect bits. While any pointer is valid or carry is 1, grab bits, 0 if out of bounds, sum, push sum %2, set carry equals sum // 2, move left. Reverse out at the end. Solution 1. Using Python conversion time complexity. ON plus M, for conversion. We begin by defining a class named solution. This simply organizes our method in a clean structure. This defines our function add binary, which takes two binary strings and returns their sum, also as a binary string. This single line does all the work, and here's the breakdown. Int A2 converts string A from binary to a normal integer. Int B2 does the same for string B. We add the two integers together. Bin converts the sum back into a binary string, but Python prefixes the result with 0b. 2 slices off the 0b part, leaving only the clean binary digits. This approach relies heavily on Python's built-in conversion tools. The time complexity comes from converting the strings to integers and back, which takes ON plus M. Final wrap-up. And that's how this algorithm works. It first lets Python convert the binary strings into integers, then adds them and converts the result back to binary, trimming away the formatting prefix. Efficient, simple, and elegant. Test case check. Add binary. Int bin approach lets test our function using this input. A equals 11 and B equals 1. These strings represent binary numbers, so 11 is 3 in decimal, and 1 is 1. Here's why the solution works. We convert both binary strings into integers, add them together, and then convert the result back into binary. Python's bin function gives us a binary string with a 0b prefix, so we slice it off with 2. And that's exactly what our program outputs, 100. It matches the expected result perfectly, showing that the binary addition is handled correctly. Wrap up. So, our implementation is correct. The algorithm successfully converts binary inputs, adds them, and returns the proper binary output. Simple, accurate, and reliable. Solution 2. Manual bit-by-bit addition time complexity. O max len A, len B. We start by defining a class called solution. It simply organizes our binary addition method. This defines the function add binary, which takes two binary strings and returns their sum, also as a binary string. We create two pointers, I and j, starting at the last index of each string. This lets us add the binary digits from right to left, just like how we add decimal numbers starting from the ones place. We initialize a carry value. If adding 2 bits goes over 1, we'll carry the extra into the next position. We create an empty list called result, which will store our resulting bits as we compute them. We begin a loop that keeps running as long as there are bits left in string A, or bits left in string B, or we still have a leftover carry. This loop runs at most max len A, len B, times ON. We read the current bit from string A, unless we've run out of characters, in which case we treat it as 0. Same idea for string B. If the pointer is still valid, grab the bit. Otherwise use 0. We compute the total sum of the two bits plus any carry. For example, 1 plus 1 plus 1 equals 3 or 1 plus 0 equals 1. We update the carry. In binary, totals 0 or 1 give carry 0. Totals 2 or 3 give carry 1. We append the resulting bit, either 0 or 1, by taking total %2. This gives us the current bit of the sum. We move the pointer I one step left to read the next bit from string A, and we move pointer J one step left to read the next bit from string B. Finally, we reverse the result, because we built it backwards, and join it into a string. This gives us the final binary sum. Final wrap-up. And that's how this algorithm works. It first sets up pointers and a carry, then adds the bits from right to left while updating the carry and building the result, finishing by reversing everything to get the correct binary number. Efficient, simple, and elegant. Test case check. Add binary, manual addition with carry. Let's test our function using this input. A equals 1010 and B equals 1011. These strings represent two binary numbers that we want to add together bit by bit, just like doing binary addition by hand. Here's why the solution works. We process each number from right to left, adding the bits along with any carry from the previous step. Each time, we calculate the sum of the two bits, the new bit to store, and the next carry. And that's exactly what our program outputs, 10,101. It matches the expected answer perfectly, showing that our manual bit addition logic handles carries and alignment correctly. Wrap up. So, our implementation is correct. The algorithm successfully adds two binary numbers digit by digit with full carry handling, efficient, accurate, and reliable. Add binary. Let's do a recap. If you can explain carries under pressure, add binary becomes a flex. It blends string handling with bitwise thinking, no big integer shortcuts, so it's perfect for showing clarity, control, and speed in interviews. Breakdown recap. We're adding two binary strings and returning their sum as a binary string. The core idea: add from right to left, keep a running carry, and handle different lengths plus a possible final carry at the end. Assess recap. We compared options and chose digit by digit addition. At each step, we combine the two current bits with the carry. The new bit comes from the remainder, and the carry comes from the quotient. This gives linear time in the total length of the inputs and uses only output size space, exactly what interviewers expect. Structure recap. We set two pointers at the ends of the strings, track a carry, and loop while there are bits or a carry left. Each step: read bits, or 0 if out of bounds, add with carry, record the current result bit, update the carry, and move left. Finally, flip the collected bits to get the correct order. Implement recap. We followed that plan precisely and ran it on LeetCode. Smooth execution, no conversions to big integers, and no edge case surprises. One pass, clean logic, and fully compliant with interview constraints. Check recap. We verified the behavior across typical and edge inputs, different lengths, all zeros, long carry chains, and everything matched expected outputs. All LeetCode test cases passed. Closing insight. The big takeaway? Master the carry. Once you can narrate read, add, write bit, update carry, move left, you'll handle binary arithmetic, base conversions, and many pointer-based string problems with calm, reliable precision.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Binary search. If there's one algorithm interviewers expect you to speak fluently, it's binary search. It's the litmus test for algorithmic rigor, pointer discipline, off by one control, and logarithmic thinking. This PatternMastery 100 staple shows up everywhere, from search problems to boundaries and monotonic checks. Let's lock it in using basics so your explanation and code are crisp and unbeatable. We're given a sorted array nums and an integer target. Return the index of target if found, otherwise return -1. Because the data is sorted, we can eliminate half the search space each step by comparing the middle element to the target. Binary search runs in O log n time and O1 space, way better than a linear scan. Key pitfalls: computing mid, updating left and right correctly, and using while left less than equals right to avoid infinite loops. We'll return as soon as nums mid equals target, else move the appropriate boundary. Plan: Initialize left equals 0, right equals len nums minus 1. While left less than equals right, compute mid. If nums mid equals target, return mid. If it's smaller, discard the left half by doing left equals mid plus 1, otherwise discard the right half via right equals mid minus 1. If we exit the loop, return minus 1.
Let's try to implement it using solution 1. We begin by defining a class named solution. This simply organizes our function inside a neat container. This sets up our function binary search, which takes a sorted list called nums and a value called target that we want to locate inside that list. We initialize 2 pointers. L at the far left, index 0, R at the far right, the last index. These pointers mark the current search boundaries. We continue searching as long as our left pointer has not passed the right pointer. Because we keep having the search area, this loop runs in O of log n time. We compute the middle index between L and R using integer division. The midpoint is where we check next, just like flipping to the middle page of a book to decide whether to look left or right. We check if the value at the middle index matches the target. If it does, we found exactly what we're looking for. And if the middle value is the target, we return the index and end the search. If the middle value is smaller than the target, that means the target must be to the right of mid, so we shift our search window to the right half. To search the right half, we move the left pointer just past the midpoint. This covers the final case. The middle value is greater than the target, which means the target must be in the left half of the list. So we move the right pointer just before the midpoint, shrinking the search window to the left side. If the loop finishes and we still haven't found the target, we return -1 to indicate that the value is not in the list. And that's how this algorithm works. It sets up left and right boundaries, then keeps having the search space by comparing the midpoint value with the target until the value is found or the range collapses. Efficient, simple, and elegant. Check. Let's walk through this test case as if we just ran it through the binary search solution. Input is nums equals -1, 0, 3, 5, 9, 12. Target equals 9. Here, nums is a sorted array. We want to find the index of the value 9. If it exists, return the index. Otherwise, return -1. Why the output is 4. Let's inspect the array. Index 0 gives -1. Index 1 gives 0. Index 2 gives 3. Index 3 gives 5. Index 4 gives 9. Index 5 gives 12. The value 9 clearly sits at index 4. The binary search process also confirms this. It checks the midpoint. It narrows down to the right side when the midpoint is too small. It continues until it hits nums at index 4, which equals 9. So the correct answer is 4. The output 4 matches the expected 4, confirming that the binary search implementation is correctly locating the target in a sorted array. Now let's try another implement approach using solution 2. We start by defining a class named solution. This simply holds the function we're about to build. This sets up our binary search method. It receives a sorted list of numbers called nums, and a target value that we want to locate. Inside the main function, we define a helper function. This helper takes 2 numbers, L, the left boundary, and R, the right boundary. It will perform the actual recursive binary search. This is our base case. If the left boundary crosses the right boundary, it means there is nowhere left to search. In that case, we return -1 to signal that the target does not exist in this part of the array. We calculate the middle index of the current search range. Binary search always checks the midpoint first, like checking the middle page of a book to decide which direction to flip. Here we check whether the midpoint value matches the target. If it does, we return the index immediately. The search is complete. If the midpoint value is smaller than the target, it tells us the target must be somewhere in the right half of the current range. So we recursively call helper, updating the left boundary to just past the midpoint. This halves the search range, giving us the classic O of log n time complexity of binary search. The final case is when the midpoint value is larger than the target, meaning the target lies in the left half of the range. So we call helper again, adjusting the right boundary to just before the midpoint. To start the whole process, we call the helper on the full search range, from index 0 to the last index of the list. And that's how this algorithm works. It sets up a recursive helper that receives the current left and right boundaries, then continually halves the search space by comparing the midpoint with the target. moving left or right until the value is found. Efficient, simple, and elegant. Check. Let's walk through this test case using our binary search logic. Input is nums equals -1, 0, 3, 5, 9, 12. Target equals 2. Here, nums is a sorted array, which is exactly what binary search expects. We're trying to find the index of the value 2. Why the output is -1. Look at the values in the array. -1, 0, 3, 5, 9, 12. The value 2 does not appear anywhere. Binary search will confirm this by checking the midpoint, which is 3, too large, so it searches left, then checking a smaller midpoint region, which is 0, too small, so it searches right. Eventually the boundaries cross, meaning the value is not present. Since the target never matches any element, the correct return value is -1. The output -1 matches the expected -1, confirming the function correctly reports when a target is not found in a sorted array.
Let's have a quick recap. Breakdown recap. So, to wrap it up, binary search is all about finding a target efficiently in a sorted list. Instead of checking one element at a time, we cut the search space in half with every step, comparing the middle element to the target. Assess recap. We compared approaches and saw why this one stands out. A linear scan takes O(n) time, but binary search drops it to O log n. The key challenges aren't in the math, they're in managing pointers, avoiding infinite loops, and computing the mid correctly. Structure recap. The logic was straightforward. Set 2 pointers at the start and end, find the middle, and adjust the search window based on whether the target is smaller or larger. Keep narrowing until it's found or the window closes. Implement recap. When we implemented it, everything came together through a clean loop that halved the range at each step. The left and right pointers guided the search precisely, and returning the mid when found kept the function minimal and robust. Check recap. We ran multiple test cases, finding numbers correctly and returning -1 when not found. Every run matched expectations, confirming our binary search logic worked perfectly in logarithmic time. The big takeaway? Binary search isn't just a single algorithm, it's a mindset. Mastering it trains you to think in halves, control boundaries precisely, and reason with mathematical efficiency, skills that show true algorithmic discipline in any coding interview.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
First bad version. This one sneaks up on candidates. First bad version looks easy, but it tests whether you can turn a plain binary search into a boundary finder. FANG interviewers love it because getting the loop and the off by one details right under pressure is a real signal. Let's lock it in with basic, so your explanation and code are crisp and bulletproof. Solution walkthrough. Breakdown. We have versions 1 through n, and an API called isBad version of x that returns true if version x is bad. Once a version is bad, every later version is bad. We must return the first bad version's index. That's a classic monotonic pattern. FFF, FTTT, T. We're not searching for a value, we're finding the leftmost true. Assess. Linear scan is O of n, but the predicate is monotonic, so binary search gives us O of log n time and O of 1 space. The pitfalls are the termination condition and deciding which side to keep when mid is bad. If mid is bad, the first bad could be mid or somewhere to its left. If mid is good, the first bad must be to the right. Structure. We keep a closed interval from left to right, initialized to 1 and n. While left is less than right, we compute mid. If isBad version of mid is true, we shrink right by setting right equal to mid. Otherwise, we move left past mid by setting left equal to mid plus 1. When the loop ends, left equals right, and that index is the first bad version.
Let's try to implement it using solution 1. We start by defining a class called solution, which groups our method neatly inside it. This defines the function first bad version, which takes in n, the total number of versions. Our goal is to find the first version where the product turned bad. We set 2 pointers. L starts at version 1, R starts at version n. This creates the full range we'll search through. We initialize bad to n. The worst case assumption is that the last version is the bad one. As we narrow things down, We'll keep updating this to the earliest bad version we find. We continue searching as long as the left pointer has not surpassed the right. Because we repeatedly cut the range in half, this loop runs in O of log n time. We calculate the midpoint of our current search range. This is the version we'll test next. Similar to checking the middle shelf to see where a problem starts, we call the provided function is bad version on the middle version. If this version is bad, it means the first bad version must be at mid or somewhere earlier. Because the midpoint is bad, we update our bad variable. This might be the earliest one. Then we shrink the search range to the left half, since earlier versions might also be bad. If mid is not a bad version, then the first bad version must be to the right. So we move the left pointer rightward to search the later versions. Once the search finishes, bad holds the earliest bad version we found, and that's what we return. And that's how this algorithm works. It first sets up a full search range, then uses binary search to repeatedly test midpoint versions and narrow down the earliest bad one. Efficient, simple, and elegant. Check. Let's walk through this test case for the first bad version problem, where we use a binary search style strategy to find the earliest version that fails. Input is n equals 5, bad equals 4. Here's what the input means. Versions are numbered 1 through 5. Version 4 is the first bad one. Any version after 4 is also bad. Any version before 4 is good. Our goal is to identify the very first version that is bad. Why the output is 4. Let's simulate the logic. First, we check the midpoint between 1 and 5. Mid equals 3. Version 3 is good, so the first bad version must be after version 3. The new search range is 4 to 5. Now mid equals 4. Version 4 is bad, so this might be the first bad version, but we must check if there is any earlier one. Next, the search range becomes 4 to 3, meaning the left side closes and the loop ends. That confirms 4 is the first bad version. So the algorithm locks onto. The output 4 matches the expected 4, confirming that the solution correctly identifies the first bad version in the sequence. Now let's try another implement approach using solution 2. We start by defining a class named solution, which is simply the container for our method. This sets up the main function first bad version, which receives n, the total number of versions we need to check. Inside our main function, we define a recursive helper function. It takes two values, L, the left boundary, and R, the right boundary. This helper will perform the binary search through recursive calls. This is the base case. If the left boundary meets or passes the right boundary, it means we've narrowed the search down to a single version, the first bad one. When that happens, we return L, because it represents the earliest possible bad version. We compute the midpoint of the current search interval. Binary search always checks this midpoint first. The halfway point helps us decide which direction to search next. We call the provided API function is bad version of mid. If the midpoint version is bad, then the first bad version must be at or before this midpoint. So we recursively search the left half of the range, including mid itself, because it might be the earliest bad version. If mid is not bad, then the first bad version must be somewhere after mid. So we recursively search the right half of the range, starting just after the midpoint. To kick off the recursive binary search, we call our helper on the full range of versions, from 1 to n. And that's how this algorithm works. It first sets up a recursive helper to search between left and right bounds, then keeps having the range based on whether the midpoint is bad until it isolates the earliest version. Efficient, simple, and elegant. Check. Let's walk through this test case for the first bad version problem. It's the simplest scenario but a great sanity check. Input is n equals 1. Bad equals 1. Here's what this means. There is only one version, version 1. Version 1 is already marked as the first bad version. There are no earlier versions to compare against. Why the output is 1? Since the problem states that all versions before the first bad version are good. All versions from the first bad version onward are bad. And here we only have a single version that is bad. It must automatically be the first bad version, which is 1. No binary search is needed beyond checking that one value. The output 1 matches the expected one, confirming the logic works even on the smallest possible input case.
Let's have a quick recap. Breakdown recap. So, wrapping it up, the first bad version problem isn't about finding a value, but identifying a boundary. We're given versions from 1 to n, and once one version is bad, all the ones after it are bad too. Our goal is to pinpoint the very first bad version, the exact point where good turns into bad. Assess recap. We compared our options and saw that a linear scan would work, but it's way too slow. The key insight is that this setup is monotonic, which means we can apply binary search. The trick is in how we move our pointers, deciding which half to keep and which to drop, while never losing sight of the possible boundary. Structure recap. The plan was simple but precise. Start with the full range from 1 to n. On each step, check the middle version. If it's bad, the first bad could still be to the left, so we keep mid in play. If it's good, we move right past mid. The loop ends when both pointers meet, and that meeting point is the answer. Implement recap. In the implementation, we used a clean binary search loop, updating our boundaries carefully. We avoided off-by-one errors by keeping the logic tight. Bad means shrink the right boundary, good means move the left boundary forward. It's a perfect example of control and precision in algorithm design. Check recap. When we ran the tests, every case passed, whether the first bad version was early, late, or right at the start. The function consistently returned the correct index with O of log n time and O of 1 space, just as expected. The big takeaway? Boundary-style binary search is about discipline, not just finding something, but knowing exactly where a condition changes. Mastering this pattern builds the confidence and accuracy that top interviews are designed to test.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Search a 2D matrix. If you can spot hidden structure, you win interviews. Search a 2D matrix disguises a sorted array inside a grid and tests whether you can binary search it without flattening anything in memory. This PatternMastery 100 classic filters for pointer precision and index math. Let's solve it with basics so you can explain it cleanly and code it fast in O of log of m times n. Breakdown. We're given an m by n matrix where each row is sorted in ascending order. The first element of each row is greater than the last element of the previous row. That structure means the matrix behaves exactly like one long sorted array of length m times n when read row by row. Given a target, we return true if it exists and false otherwise. Assess. A naive scan is O of m times n, but because the matrix is globally sorted, we can run a standard binary search in O of log of m times n with O of 1 extra space. The key trick is mapping between dimensions. Row equals mid divided by n, using integer division. Col equals mid modulo n. Or using Python's built-in, row, col equals dov mod mid, n. Structure. The plan is straightforward. Guard against empty inputs. Set left to 0 and right to m times n minus 1, while left is less than or equal to right. Compute mid. Convert mid into row and column. Compare matrix at row and column to the target. If it matches, return true. If the midpoint value is smaller, move left to mid plus 1. Otherwise, move right to mid minus 1. If the loop ends with no match, return false.
Let's try to implement it using solution 1. We begin by defining a class named solution, which simply organizes our function. This sets up our search matrix function, which receives a 2D list called matrix and a value called target that we want to locate somewhere inside it. This line checks whether the matrix is empty, or whether the first row is empty. If either is true, there is nothing to search. So if the matrix has no data, we immediately return false, because the target cannot be present. We store the number of rows in M and the number of columns in N. This helps us translate between a 1D index and a 2D position later. We set up 2 pointers for binary search. L starts at index 0. R starts at the last index of a flattened version of the matrix, which is total elements minus 1. This lets us pretend the matrix is one long sorted array. The binary search begins. We continue as long as the left index has not passed the right. Since we have the search range each step, the time complexity is O of log of m times n. We compute the middle index in our imaginary 1D list. This midpoint is where we will check next. This clever line converts the 1D midpoint index back into a 2D row and column. Mid divided by n, using integer division, gives us the row. Mid modulo n gives us the column. Val is the actual number stored at that spot in the matrix. We check whether the value at the midpoint is exactly the target. If it is, We have found the target and return true right away. If the midpoint value is smaller than the target, then the target must be further to the right in our virtual list. So we shift the left pointer to just after the midpoint. This covers the case where the midpoint value is larger than the target. We move the right pointer left to search the earlier half of the list. If the loop ends without finding the target, we return false, meaning the value does not exist in the matrix. And that's how this algorithm works. It first checks that the matrix is valid, then treats the entire 2D grid as one sorted list and uses binary search to test middle positions until the target is found or ruled out. Efficient, simple, and elegant. Check. Let's walk through this test case for the search a 2D matrix problem and confirm why the output is true. Input is matrix equals 1, 3, 5, 7, 10, 11, 16, 20, 23, 30, 34, 60. Target equals 3. Here's what the input means. Matrix is a 2D grid where each row is sorted in ascending order. The first element of each row is greater than the last element of the previous row. Target equals 3 is the value we want to check for inside this matrix. The problem usually treats this structure almost like a flattened sorted array, so we can use binary search logic. Why the output is true. Let's inspect the matrix row by row. Row 0, 1, 3, 5, 7. Row 1, 10, 11, 16, 20. Row 2, 23, 30, 34, 60. The target is 3, and we can see. It appears in row 0, at column 1, matrix at row 0 column 1 equals 3. Whether the implementation first finds the correct row, because 3 lies between 1 and 7, and then searches inside that row, or treats the whole thing as a single sorted list and binary searches directly. It will eventually land on this element and return true. The output is true, and the expected value is also true, which confirms the search logic is correctly locating the target inside the 2D matrix. Now let's try another implement approach using solution 2. We start by defining a class named solution, which simply groups our function. This sets up our search matrix function, which receives a 2D matrix and the value we're searching for. This line checks whether the matrix is empty or whether the first row is empty. If the matrix has no data, we immediately return false. The target cannot be found. We store the number of rows in M and the number of columns in N, giving us the full dimensions of the grid. We set up 2 pointers to perform a binary search over the rows. Top starts at the first row. Bottom starts at the last row. We initialize a variable called row to store which row the target might be in. A value of -1 means we have not found that row yet. We begin a binary search on the rows. This loop runs in O of log m time. We compute the middle row index to check next. If the target is smaller than the first element of this middle row, then it must be somewhere above this row. So we move the bottom pointer upward. If the target is larger than the last element of the middle row, then it must be below this row. We move the top pointer downward to search lower rows. If the target is not too small or too large for this row, it means the target could be in this row. We store this row index. This is the only row where the target could possibly exist, and we stop the raw search. If the raw search ended without finding any valid row, we return false, because the target cannot be anywhere in this matrix. Now we set up a second binary search, this time within the identified row, using column pointers. This begins the column-level binary search, which runs in O of log n time. We calculate the midpoint column. If the value in the middle column equals the target, we have found it and return true right away. If the midpoint value is smaller than the target, we look to the right half. We move the left pointer to narrow our search to columns on the right. This means the midpoint value is larger than the target, so we move the right pointer leftward to search earlier columns. If the loop ends without finding the target, we return false. It is not in this row. And that's how this algorithm works. It first locates the only possible row using a binary search across the row range, then runs a second binary search inside that row to pinpoint the target. Efficient, simple, and elegant. Check. Let's verify this test case for the search a 2D matrix problem and see why the output is false. Input is matrix equals 1, 3, 5, 7, 10, 11, 16, 20, 23, 30, 34, 60. Target equals 13. What the matrix structure tells us. Each row is sorted. The first element of each row is larger than the last element of the previous row. The entire matrix behaves like one long sorted list. Our goal is to determine whether 13 appears anywhere inside this structure. Why the output is false. Let's scan logically. Row 0, 1, 3, 5, 7, 13 is greater than all of these. Row 1, 10, 11, 16, 20, 13 lies between 11 and 16, but it is not equal to any element in this row. Row 2, 23, 30, 34, 60, 13 is less than all of these. Since 13 does not match any number in any row, the binary search, or this row and column search, never finds a match and never returns true. Thus, the correct result is false. The output false matches the expected false, confirming the function correctly determines that the target 13 does not exist in the matrix.
Let's have a quick recap. Breakdown recap. So, wrapping up, search a 2D matrix is all about recognizing structure. You're given a matrix where each row is sorted, and every next row starts higher than the last one. Conceptually, that means the entire matrix behaves like one long sorted array. The challenge is to find the target efficiently, without actually flattening the data. Assess recap. We looked at our options. A brute force scan checks every element in O of m times n, but that's wasteful. Because the matrix is globally sorted, we can treat it as a single sorted list and use binary search. That drops the time down to O of log of m times n, while keeping space constant. The key was mapping a 1D index back to 2D coordinates using simple math. Structure recap. The logic was straightforward. Set up 2 pointers, left at 0 and right at m times n minus 1, and repeatedly check the middle index. Convert that index into a row and column, compare the value to the target, and adjust boundaries until you find it or the range collapses. Implement recap. During implementation, we guarded against empty input, then built a clean binary search loop. Each step calculated mid, mapped it to row and column, and compared the value. The solution stayed compact, efficient, and easy to follow. Check recap. When we ran through multiple test cases, every result matched perfectly. The function correctly returned true for existing values and false for values that were missing. All outputs confirmed the O of log of m times n performance and flawless index mapping. The big takeaway? When problems look multidimensional, look for patterns that reduce them to one dimension. Spotting hidden order is a key interview skill, and mastering that mindset turns complex grid challenges into elegant binary search solutions.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Ever had to schedule a new meeting in a busy calendar and wondered where it fits? Insert interval is a PatternMastery 100 staple, loved by Google, Amazon, and Facebook to test your interval merging and array traversal skills. Over 30% of candidates stumble on edge cases, especially when the new event overlaps with many intervals. Master this and you'll breeze through scheduling, merging, and range questions in interviews. Let's solve insert interval using the basic approach, so you can handle any interval insertion or merging scenario step by step. You're given a list of non-overlapping intervals sorted by start time and a new interval. Insert the new interval, merging if necessary, so the output remains non-overlapping and sorted. List of intervals, each as start, end, sorted, non-overlapping new interval, start, end. List of intervals after insertion and merging. Think of adding a new meeting to a packed conference room schedule. You have to insert it in the right spot and merge if there's any overlap. Interviewers might ask, how would you efficiently handle time slot insertions in a shared calendar app? What's tricky? Need to merge if new interval overlaps with any existing. Carefully handle cases where the new interval is before, after, or in between intervals. Avoid unnecessary merges, stick to intervals that actually overlap. Loop through existing intervals. If current interval ends before the new interval starts, add it to output. If current interval starts after new interval ends, add the new interval, then the rest of the intervals, you're done. If there's overlap, merge, update the new interval start to min_cur.start, new.start, end to max_cur.end, new.end. Add any unmerged new interval at the end if needed. Let's clarify. The output must be sorted and non-overlapping. At most one merge run is needed, since input is non-overlapping and sorted. Edge cases. New interval before all others. New interval after all others. New interval overlaps multiple intervals. Initialize an empty result list. Iterate over each interval. If current ends before new starts, append current. If current starts after new ends, append new, then append the rest and return. If overlap, update new interval to merged range. After the loop, add the last new interval if not already added. Return the result. Let's implement solution 1. Insert interval with merge strategy. Define a solution class as a wrapper. Takes a list of sorted, non-overlapping intervals and a new interval to insert. Append the new interval to the list. Sort intervals by start time to make merging easier. Initialize list to store merged intervals. Loop through intervals and merge overlaps. No overlap. Overlap. Return merged list with new interval inserted and overlaps combined. Insert interval adds the new interval, sorts, and merges overlaps efficiently into clean, non-overlapping ranges. Test input. Intervals equals 1, 3, 6, 9. New interval equals 2, 5. 1, 3 covers 1 to 3, 6, 9 covers 6 to 9. New interval 2, 5 overlaps with 1, 3, but not 6, 9. Why the solution works. Algorithm steps. Add new interval and sort 1, 3, 2, 5, 6, 9. Merge overlaps. 1, 3 and 2, 5 overlap merge to 1, 5, 6, 9 starts after 5 append as is. Final merged intervals 1, 5, 6, 9. Program outputs 1, 5, 6, 9, matching expected. New interval inserted and overlaps merged efficiently and accurately. Solution 2. Insert interval using single pass merge. Define a solution class as a wrapper. Takes sorted, non-overlapping intervals and a new interval to insert. Initialize result list to build the final merged intervals. Pointer I iterates through intervals, n is the total count. Phase 1. Add intervals before new interval. Copy intervals that end before new interval starts, no overlap. Phase 2. Merge overlapping intervals. Extend new interval to cover all overlapping intervals. Add the fully merged interval to result. Phase 3. Add intervals after new interval. Append remaining intervals that don't overlap. Return result, all intervals before, one merged interval, then remaining intervals. Single pass, on time and space. Algorithm efficiently inserts and merges the new interval in one pass, keeping intervals non-overlapping. Let's test our function using the intervals 1 to 2, 3 to 5, 6 to 7, 8 to 10, and 12 to 16, and a new interval 4 to 8. We want to insert this new range and merge any overlaps. 1 to 2 covers time 1 to 2. 3 to 5 covers time 3 to 5. 6 to 7 covers time 6 to 7. 8 to 10 covers time 8 to 10. 12 to 16 covers time 12 to 16. The new interval 4 to 8 overlaps with 3 to 5, 6 to 7, and 8 to 10. Copy intervals before the new one. 1 to 2 comes before 4 to 8, keep 1 to 2. Merge overlapping intervals. 3 to 5, 6 to 7, and 8 to 10 all overlap with 4 to 8 merge into 3 to 10. Append remaining intervals. 12 to 16 stays as is. Output the final merged intervals are 1 to 2, 3 to 10, and 12 to 16. Our function correctly inserts the new interval and merges overlaps. The result is 1 to 2, 3 to 10, and 12 to 16. Clean, accurate, and efficient. Let's have a quick recap. We're given a sorted list of non-overlapping intervals and a new interval to insert. The goal is to place the new one correctly, merging it with any overlaps so the final list remains sorted and clean. It's all about managing order and boundaries efficiently. The challenge comes from the overlap logic. You need to handle 3 scenarios. When the new interval is before all others, after all others, or overlaps one or several intervals in the middle. The trick is merging only when necessary, not overcomplicating what's already sorted. Here's the plan. Loop through the intervals one by one. If the current interval ends before the new one starts, just add it to the result. If the current one starts after the new ends, add the new interval, then the rest, and you're done. If there's overlap, Merge by taking the min start and max end, and keep going. After the loop, add the final merged interval if it hasn't been added yet. We followed this linear plan, merged overlapping intervals smoothly, and kept the final list sorted. The code ran on LeetCode successfully. No errors, no missed cases. After running the solution, every test case passed perfectly. The logic handled overlaps, gaps, and edge positions exactly as expected. All outputs matched. The key takeaway? Smart traversal beats complexity. By respecting the sorted order and merging only when needed, you can turn any scheduling or range insertion challenge into a simple, predictable one-pass solution.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Ever tried to clean up a messy calendar with overlapping meetings? Merge Intervals is a PatternMastery 100 classic and a go-to at Google, Amazon, and Meta for interval manipulation and sorting skills. More than 30% of candidates miss subtle merge cases or get tangled in the logic. Master this, and you'll be set for any range, timeline, or schedule question. Let's break down merge intervals with the basic approach, so you can handle any overlap or merging scenario with confidence. Given an array of intervals where each interval is start, end, merge all overlapping intervals and return an array of the non-overlapping intervals that cover all the input. List of intervals, unsorted, may overlap. List of merged intervals, sorted, non-overlapping. Think of merging meeting times on a shared calendar so no one gets double booked. Interviewers might ask, how would you efficiently compress overlapping bookings or busy periods? What's tricky? Input intervals may be unordered. Overlaps may cascade. Merging two can create new overlaps. Sorting first is essential. Sort intervals by start time. Initialize a result list with the first interval. For each interval, if it overlaps with the last in result, start less than or equal to end, merge, update end to max current end, new end. If it doesn't overlap, add it as a new interval to result. Let's clarify. Always compare current intervals start with last result intervals end. Only merge when there is overlap. Edge cases. Intervals already non-overlapping. All intervals overlap into one. Empty input. Sort intervals by their start value. Initialize the merged result with the first interval. For each interval from the second onwards. If interval.start less than equals last.end, merge, update last's end. Else, append interval to result. Return the result. Sort the list. Single pass through intervals for merging. Let's try to implement it using solution 1. This comment labels the strategy, sort the intervals, then merge overlaps. We start by defining the solution class. This defines the merge method, which takes a list of intervals and combines any that overlap. We sort all intervals by start time so they're in order. We create an empty list called merge to store the final intervals. We loop through each interval to decide if it starts a new block or should be merged. If merged is empty, or the current interval starts after the last one ends, we add it as a new interval. When there's no overlap, we simply append it. Otherwise, they overlap. We update the end to the maximum value to merge them. Finally, we return the list of clean, non-overlapping intervals. And that's how the algorithm works. Sort first, then scan once to merge anything that overlaps. Efficient and simple. Test input. These intervals show ranges on a timeline, with some overlapping. 1,3 and 2,6 overlap merge into 1,68,10 and 15,18 don't overlap keep as they are final expected. 1,6, 8,10, 15,18. Why the solution work steps: sort intervals 1,3, 2,6, 8,10, 15,18, scan and merge 1,3 plus 2,6, 1,6, no overlap with 8,10, append no overlap with 15,18, append final 1,6, 8,10, 15,18. Output matches expected. Now let's try another implement approach using solution 2. This comment says we're solving merge intervals using a stack-like structure. We define a solution class. This defines the merge method, which takes a list of intervals and merges any overlaps. We sort the intervals by start time so overlapping ones sit next to each other. We create an empty stack to store merged intervals. We loop through each sorted interval and decide if it starts a new block or merges with the last one. If the stack is empty or the current interval starts after the last one ends, there's no overlap. In that case, we push the current interval. Otherwise, they overlap. We merge them by updating the end of the top interval. After processing all intervals, we return the final merge stack. This approach sorts first, then merges using a simple stack, clean and efficient. Let's test our function using this input. These intervals represent ranges on a timeline. 1, 4, and 4, 5, touch, so they should be merged. 1, 4, and 4, 5, overlap/touch merge into 1, 5 final expected intervals, 1, 5, why the solution works our algorithm. Sort intervals, 1, 4, 4, 5, loop through each interval. Push 1, 4 onto the merge list. 4, 5, overlap/touches, 1, 4, merge to 1, 5 final merged intervals, 1, 5. The output matches the expected result. The algorithm efficiently merges overlapping or touching intervals into clean, non-overlapping ranges. Let's have a quick recap. We're given a list of intervals, and the task is to merge all overlapping ones so that the result is a set of sorted, non-overlapping intervals. Conceptually, this is all about organizing ranges, grouping overlapping segments so that each time span appears once. The tricky part is handling multiple overlaps that cascade. You can't just check pairs. Merging one interval can extend into others. Sorting by start time is the key insight. Once sorted, you can scan linearly and merge as you go. It's clean, efficient, and easy to reason through. Here's the plan. Sort intervals by their start value. Initialize the result with the first interval. For each new interval, check if it overlaps with the last in the result. If yes, merge by extending the endpoint. If no, simply append it to the result. After one pass, you've got your merged list, sorted and clean. We followed that plan, sorted the intervals, merged overlaps in a single pass, and built the final result step by step. The solution ran smoothly on LeetCode, no syntax issues, no logic errors. We verified the output thoroughly. Overlapping, adjacent, and empty cases all produced the right results. Every test case passed successfully on LeetCode. The key takeaway? Sorting simplifies complexity. By thinking in sequence and merging only when needed, you transform what looks like chaos into perfect order, one of the most fundamental problem-solving lessons in computer science.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
How would you maximize your calendar by removing the fewest overlapping meetings? Non-overlapping intervals is a PatternMastery 100 favorite and a go-to at Google, Meta, and Amazon to test your greedy reasoning with intervals. Over 30% of candidates make the wrong removal choice or miss the best sorting strategy. Nail this and you'll master scheduling and optimization problems in interviews. Let's break down non-overlapping intervals using the basic approach, a proven strategy for greedy interval problems. Given a set of intervals, start, end, find the minimum number of intervals to remove to make the rest of the intervals non-overlapping. List of intervals, unsorted, may overlap. Integer, minimum number of intervals to remove. Think of cleaning up an overloaded meeting calendar. What's the smallest number of meetings you need to cancel so that no two overlap? Interviewers might ask, how do you optimize a schedule to fit as many appointments as possible without conflicts? What's tricky? Choosing which intervals to remove for minimal impact. A greedy approach, sorting by end time, works best. If you always pick the interval that ends earliest, you leave more space for future intervals, classic greedy logic. Sort intervals by end time, not start. Initialize end to -infinity and count to 0. Loop through the intervals. If the current interval start is greater than equals previous end, keep it and update end. If not, remove it, increment count, since it overlaps with the last chosen interval. Let's clarify. You're maximizing the number of non-overlapping intervals, so removal count equals total, max non-overlapping. Sorting by end time ensures each choice leaves the most room for what comes next. Edge cases. No intervals or only one, return 0. All intervals overlap, remove all but one. Sort intervals by end time. Initialize end equals inf, count equals 0. For each interval. If interval.start greater than equals end, keep it, update end equals interval.end. Else, overlap, increment count, remove this interval. Return count. Let's try to implement it using solution 1. We start by creating a class called solution. This is just a container to hold our method. Inside our class, we define a function called erase_overlap_intervals. It takes in a list of intervals, where each interval looks like start, end. Our goal is to remove the minimum number of intervals so that no intervals overlap. First, we sort the intervals by their start time. This puts everything in order, like lining up tasks on a timeline so we can process them from earliest to latest. Sorting costs O(n) log n time. We store the number of intervals in n. Just a quick helper variable so we don't compute the length repeatedly. We create a DP array, where each entry starts as 1. Why 1? Because any single interval by itself forms a non-overlapping chain of length 1. This array will eventually store the longest chain of non-overlapping intervals ending at each index. This uses O(n) space. We also track a variable called max_chain to remember the largest non-overlapping chain we've seen so far. We loop through all intervals from left to right. This is the ending position of our chain. For each interval I, we compare it with all earlier intervals j. This double loop creates a time complexity of O(n², because we're comparing every pair. This conditional checks two things. Non-overlapping condition: if the end of interval j is less than or equal to the start of interval I, then interval j can come right before interval I in a chain. DP update condition: if taking interval j and then I creates a longer chain than what we have so far, we update it. If the chain improves, we update DPI to reflect the new longest chain ending at interval I. We also keep track of the largest chain found anywhere so far. This lets us compute the final answer later. At the end, we return the number of intervals to remove. Why n max_chain? Because if the longest non-overlapping chain has max_chain intervals, then everything else must be removed. This turns our DP chain length into the minimum removal count. Solution 1. Test case 1. Let's test our function using this input. 1, 2, 2, 3, 3, 4, 1, 3. These pairs represent intervals on a timeline. Each one has a start and an endpoint. Here's why the solution works. We first sort the intervals, then we try to build the longest chain of non-overlapping intervals. For this input, the best chain is 1, 2, 2, 3, 3, 4, which has length 3. Since we have 4 intervals total, that means we need to remove one interval, the one that overlaps too much. And that's exactly what our program outputs. 1. This confirms that our code is working correctly and passes the test. So, our implementation is correct. The algorithm successfully finds the minimum number of intervals to remove by computing the longest non-overlapping chain, efficient, accurate, and reliable. Let's try to implement it using solution 2. Overall time complexity. Sorting, O(n) log n single pass through the intervals, O(n). So the total time is dominated by the sort, O(n) log n, with O(1) extra space. We only keep a few variables. This line defines a class called solution. Nothing magical here, just the container for our code. Inside the class, we define a method called erase_overlap_intervals. It takes one argument, intervals, which is a list of start, end, pairs. Each pair represents a time interval on a line, and our goal is to remove as few intervals as possible so that no two overlap. Here we sort the intervals by their end time. So instead of looking at when intervals start, we care about when they finish. Why? Because this is a classic greedy trick. If you always pick the interval that ends earliest, you leave as much room as possible for future intervals. We initialize a counter called removals to 0. This will keep track of how many intervals we decide to remove because they overlap. Next, we set prev_n to -infinity. You can think of prev_n as the end time of the last interval we decided to keep. Starting with -infinity just means before we pick any interval, the timeline is completely empty. So the very first interval we see will always fit. Now we loop through every interval in the sorted list. For each interval, we unpack it into start and end. Here we check whether the current interval overlaps with the one we last kept. If start greater than equals prev_end, that means the current interval starts after or exactly when the previous one ends, so they do not overlap. If start less than prev_end, there is an overlap. So this condition is our overlap test. This comment is just explaining the happy path. When there's no overlap, we choose to keep this interval. In the no overlap case, we update prev_n to the end of this interval. That means We're officially accepting this interval into our non-overlapping set. And from now on, all future intervals must start at or after this new prev_end. If the if condition fails, meaning start less than prev_end, we land in the else block. That's the overlap case. This comment reminds us what we're doing in the else case. The current interval overlaps the last one we took, so we'll remove this one instead of breaking our chain of non-overlapping intervals. Because we sorted by end time, the current interval ends later or equal to the previous one, so it's always safe and optimal to remove the current one. Here we increment our removals counter by 1. We're saying, this interval caused an overlap, so we're counting it as removed. We don't change prev_end in this case, because we're not keeping this interval, we're sticking with the previous one that ends earlier. Finally, we return removals. That number represents the minimum number of intervals we need to remove so that the remaining intervals are non-overlapping. And that's how this algorithm works. It first sorts all the intervals by their end time and initializes a running previous end marker, then greedily walks through the intervals, keeping non-overlapping ones and counting how many overlapping intervals must be removed. Efficient, simple, and elegant. Solution 2. Test case 2. Now testing with 1, 2, 1, 2, 1, 2. All of these intervals overlap completely. The greedy strategy keeps the interval that ends earliest and removes all others. Since only one interval can remain without overlapping, we must remove 2 of them. And that's exactly what our program outputs, 2. Perfect match with the expected behavior. So, our implementation is correct. The algorithm efficiently determines how many intervals must be removed to eliminate all overlaps. Simple, greedy, and highly effective. Quick recap time. We tackled the classic calendar cleanup problem. Remove the fewest intervals so the rest don't overlap. Breakdown recap. Conceptually, we're optimizing a schedule. From a pile of possibly overlapping intervals, we want the smallest number of deletions so what remains is conflict-free. Assess recap. We compared options and landed on a greedy strategy. Brute force is impractical here, but if we always keep the interval that ends earliest, we leave maximum room for everything after it. This directly maximizes the number of non-overlapping intervals and, by complement, minimizes removals. Structure recap. The plan was straightforward: sort by end time, sweep once, and keep an interval only if it starts at or after the end of the last kept one. Every time we see an overlap, we count a removal. The final count is the minimum deletions required. Implement recap. We implemented this flow on LeetCode and the solution executed cleanly without any errors. Check recap. We verified the logic with LeetCode's runs, confirming that it behaves exactly as expected and passes the test cases, including edge scenarios. Key takeaway: when scheduling is involved, earliest finish first is a powerful greedy pattern. By maximizing what you can keep, you automatically minimize what you need to remove.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
How do you know if you can attend every meeting on your schedule? Meeting Rooms is a PatternMastery 100 favorite and a classic warm-up at Google, Amazon, and Meta for interval reasoning and sorting. Over 25% of candidates miss subtle overlaps or forget to handle back-to-back meetings. Master this. Unlock a whole world of scheduling and interval-based interview questions. Let's break down Meeting Rooms using the basic approach, a reliable method for interval overlap problems. You're given an array of meeting time intervals where each interval is start, end. Determine if a person could attend all meetings. List of intervals, unsorted, each as start, end. Boolean: true if you can attend all meetings, false otherwise. Imagine planning your day with back-to-back meetings. Can you get to everyone without running late? Interviewers might ask, how would you quickly check if any 2 appointments on your calendar overlap? What's tricky? Input can be unordered. Meetings that end exactly when the next starts do not overlap. Only need to find one overlap to return false. First, sort all intervals by their start time. Then, walk through the sorted list. For each meeting, compare its start to the previous meeting's end. If the current meeting starts before the previous one ends, there's an overlap, return false. If you make it through without overlaps, return true. Let's clarify. Sorting is critical. Unsorted input can hide overlaps. Edge cases: one meeting, always true. Empty list, true. Edge cases: empty list, true. Single meeting, true. Overlapping at end: 0, 30, 30, 40, no overlap. Sort intervals by start time. For each meeting from the second onward. If interval I0, less than interval I11, overlap, return false. Now let's solve solution 1, the min heap, or sorting, approach for checking meeting conflicts. Time complexity is O(n) log n, due to sorting the meeting intervals. The idea: first, sort all meetings by their start time. After they're sorted, walk through the list one by one. For each meeting, check if it starts before the previous one ends. If you ever see overlap, return false. If you finish the loop with no conflicts, return true. Even though this is called min heap, this solution uses sorting, but the logic follows the same principle. Track n times to detect overlaps. Line-by-line explanation of the code. We begin by defining a class called solution. This is just the wrapper that holds our method. We create a function that takes a list called intervals. Each interval is a meeting with a start and end time. Here we sort all the meetings by their start time. This makes it easy to compare each meeting with the one right before it. Think of it like arranging events in a calendar so you can scan them in order. We loop through each meeting starting from the second one. We do this because we are always comparing meeting I with meeting I1. This is the core check. We compare the start time of the current meeting with the end time of the previous meeting. If the current meeting starts before the last one ends, that means the two meetings overlap. If we detect overlap, we immediately return false, meaning you cannot attend all meetings. If we finish the loop with no overlaps, we return true. This means all meetings are spaced out enough and can be attended without conflict. And that's how this algorithm works. It first sorts all the meetings by start time, then checks one by one whether any meeting overlaps with the previous one. Efficient, simple, and elegant. Sorting the meetings costs O(n) log n. The scan afterward is O(n). Overlap happens when the current meeting's start time is less than the previous meeting's end time. No heap is required. The sorted list already gives us the correct order to detect conflicts. Now we test our can attend meetings function with a sample schedule. Input intervals are 0, 30, 5, 10, 15, 20. Each subarray shows a meeting start and end time. The algorithm sorts meetings by start time and checks for overlaps. If any meeting starts before the previous one ends, it returns false. Here, meeting 2 starts at 5, before meeting 1 ends at 30, so there's an overlap. Output is false, confirming the function works. The implementation efficiently detects overlaps and ensures the schedule is feasible. In this approach, we're using a simple brute force method. We check every possible pair of meetings to see if any two overlap. It's easy to understand and implement, but not the most efficient for large inputs. Time complexity is O(n) squared, where n is the number of meetings. Every meeting is compared with all others. Simple but can be slow if n is large. We define a class solution to hold our meeting schedule checking method. Define the function can attend meetings and get the total number of meetings. Use nested loops to compare every meeting with all later meetings. The outer loop picks one meeting, and the inner loop checks it against all following meetings. Check if the current pair of meetings overlap. If they do, immediately return false because you can't attend both. If all pairs are checked and no overlaps are found, return true, all meetings can be attended. This is a simple brute force method. Each meeting is compared with every other meeting, giving O(n) squared complexity. It works well for small numbers of meetings but is inefficient for large inputs. Let's see how our solution checks meeting intervals and determines if all can be attended. Input intervals are 7, 10, 2, 4. Each pair shows a meeting start and end time. The algorithm compares each pair of meetings. If any meeting starts before the previous one ends, it overlaps and returns false. Here, 7, 10, and 2, 4 do not overlap, so the function returns true. Output is true, confirming the implementation works. The method efficiently checks for overlaps, handles all cases, and ensures accurate results. Let's wrap up the meeting rooms problem. It's one of those deceptively simple scheduling questions that interviewers love, and it quietly tests your logic around sorting and interval overlap. Miss a single detail, and you'll end up double-booked. Breakdown recap. We're given a list of meeting intervals, each with a start and end time, and we need to determine if a person can attend all meetings without any overlaps. If any two meetings overlap, the answer is false, otherwise, true. Assess recap. The key insight here is that meetings can come in any order, and back-to-back meetings are allowed. So, we first sort all intervals by their start time. Then, we walk through the list, comparing each meeting's start to the previous meeting's end. If a meeting starts before the last one ends, we found an overlap and can immediately return false. If we reach the end with no conflicts, we return true. Structure recap. Our structure is simple. Sort the intervals by start time. Loop through each one, checking for overlap with the previous meeting. If none are found, return true. Edge cases like an empty list or a single meeting automatically return true since there's nothing to conflict with. Implement recap. We implemented the sorting and single pass check using built-in functions, quick, clean, and efficient. When we ran it on LeetCode, the solution executed smoothly without any errors. Check recap. We tested multiple cases, including overlapping and non-overlapping intervals, and all returned the expected results. The time complexity was O(n) log n. For sorting, with only O1 extra space. Closing insight. The big takeaway? Sorting is your best friend in interval problems. Once your data is ordered, detecting overlaps becomes a simple linear scan, turning what looks complex into something elegantly straightforward.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
Can you juggle a jam-packed schedule and still find enough rooms for every meeting? Meeting Rooms 2 is a PatternMastery 100 favorite and a must-know at Google, Amazon, and Meta. Over 35% of candidates get tripped up by overlapping intervals and efficient resource tracking. Master this, and you'll be set for any scheduling, heap, or interval-based interview problem. Let's break down Meeting Rooms 2 using the basic approach, so you can solve any resource allocation or interval overlap challenge step by step. You're given an array of meeting time intervals, start, end. Return the minimum number of conference rooms required for all meetings. List of intervals, unsorted, each as, start, end. Integer, minimum number of meeting rooms needed. Picture running an event center. How many rooms do you need to make sure every meeting can happen without conflicts? Interviewers might ask, how do you efficiently track the maximum number of simultaneous bookings in a day? What's tricky? Intervals can overlap in complex ways. Tracking active meetings efficiently is key. Use a min heap to always know which room is free next. Sorting is crucial for an optimal solution. Sort all intervals by start time. Use a min heap to track meeting end times, smallest end time on top. For each meeting. If the current meeting starts after the earliest ending meeting, that room is freed, pop from heap. Otherwise, allocate a new room, push end time to heap. The heap size at any moment tells you how many rooms are in use. Let's clarify. Heap contains the end times of all ongoing meetings. Always pop from heap when a room frees up, i.e., when a meeting ends before the next starts. Edge cases. No meetings, 0 rooms. All meetings overlap. Need as many rooms as meetings. Sort intervals by start time. Initialize a min heap, priority queue. For each interval. If heap is not empty and interval starts greater than or equal to heap 0, earliest end, pop from heap. Push interval's end time onto the heap. After all meetings, heap size equals rooms needed. Now let's solve solution 1, the min heap approach for finding the minimum number of meeting rooms needed. We'll go step by step, explain each line, and understand why a min heap is the perfect structure for this problem. Time complexity is O(n) log n, where n is the number of meetings. Sorting takes O(n) log n, and each heap operation is O log n. The idea, store all end times in a minute heap. Sort all meetings by start time. For each meeting, check if the earliest ending meeting in the heap ends before the current meeting starts. If yes, free the room by popping from the heap. Allocate a room for the current meeting by pushing its end time to the heap. The heap size at the end is the minimum number of rooms needed. Think of it like tracking rooms. The heap always knows the meeting that finishes soonest. Line-by-line explanation of the code. We import Python's heapp module, which lets us easily manage a min heap. Think of it as a priority queue where the smallest element is always on top. We define our class solution. This is standard for coding problems. This function will return the minimum number of meeting rooms needed for a list of intervals. Sort all meetings by their start time. This ensures we handle meetings in chronological order. Imagine lining up events on a timeline. We create an empty heap. It will store the end times of meetings currently occupying rooms. The smallest end time is always at the top. We iterate over each meeting in order. We check if there is a meeting in the heap and whether the earliest ending meeting finishes before or exactly when the current meeting starts. If yes, that room is now free. Remove the earliest ending meeting from the heap, freeing that room. Think of it as a room becoming available for the next meeting. Add the current meeting's end time to the heap. Either it's a new room or a reused room. The heap automatically keeps the earliest ending meeting on top. The heap now contains all ongoing meetings at the end of the process. Its size equals the minimum number of rooms required. And that's how this algorithm works. It first sorts the meetings by start time, then uses a min heap to track ongoing meetings and room availability. Efficient, simple, and elegant. Sorting meetings is O n log n. Each heap push or pop is O log n. The heap always tracks the meeting that ends earliest. Heap size at the end equals the minimum number of rooms needed.
Let's test the function with intervals, 0, 30, 5, 10, 15, 20. Meeting 0 to 30 goes in the heap, 30. Meeting 5 to 10 overlaps push 10, 10, 30. Meeting 15 to 20 starts after 10 ends pop 10, push 20, 20, 30. Heap size is 2, so we need 2 rooms, and the program outputs exactly 2.
We're going to look at solution 2 for finding the minimum number of meeting rooms needed. The time complexity of this approach is O n log n, mostly because we need to sort the start and end times of all meetings. In this approach, we don't use a heap. Instead, we use 2 sorted lists, one for start times and one for end times. Think of it as lining up all meetings by when they start and keeping track of when each meeting ends. Then, we move through them one by one to see whether a new room is needed or an existing room can be reused. We start by defining a class called solution. Think of it as a container that holds all the code for solving this problem. Inside the class, we have a function called min meeting rooms. This function takes a list of meetings, where each meeting has a start and end time, and calculates the minimum number of rooms needed. First, the function checks if the list of meetings is empty. If there are no meetings, it immediately returns 0, because no rooms are needed. Next, it collects all the start times and all the end times of the meetings, and sorts both lists. Sorting helps us process meetings in chronological order, like lining up events on a timeline. We then set 2 pointers, S for the start times and E for the end times, and also initialize a counter called rooms to keep track of how many rooms we need. Now, we loop through all the meetings. Each time, we compare the next meeting start time with the earliest ending meeting. If the next meeting starts before a meeting ends, that means rooms overlap and we need a new room. So we add 1 to the room count. Otherwise, a meeting has finished, freeing up a room. We move the end pointer forward to track the next meeting that will end. After that, we move the start pointer to the next meeting and continue checking. Finally, once all meetings have been processed, the function returns the total number of rooms needed. And that's how solution 2 works. It first sets up the class and function, organizes start and end times, then uses 2 pointers to efficiently track overlaps and count the rooms. Simple, fast, and elegant.
Let's check how our solution figures out the minimum number of meeting rooms using this test case. The input is 7, 10, 2, 4. Each pair shows when a meeting starts and ends. We sort the start times 2, 7, and the end times 2, 4, 10. The first meeting, 2 to 4, uses 1 room. The next meeting starts at 7, which is after 4 ends, so we reuse the same room. Total rooms needed is 1, and the program outputs exactly 1.
Breakdown recap. We're given an array of meeting intervals, each with a start and end time, and we need to return the minimum number of rooms required so that all meetings can happen without conflict. In short, it's all about finding the maximum number of meetings that overlap at any point in time. Assess recap. The challenge is tracking overlapping intervals efficiently. Instead of checking every pair, we sort the meetings by start time and use a min heap to keep track of ongoing meetings by their end times. The heap helps us know which room will be free next. If a new meeting starts after the earliest one ends, we pop it off the heap, that room is now available. Otherwise, we push the new meeting's end time, meaning we need another room. The heap's maximum size during the process tells us how many rooms are needed. Structure recap. We start by sorting all intervals by start time. Then, we initialize a min heap to store end times. For each meeting, if the heap isn't empty and the current meeting starts after or exactly when the earliest one ends, we free that room by popping the heap. Then, we always push the current meeting's end time. Once all meetings are processed, the heap size equals the number of rooms required. Implement recap. We implemented this using Python's heap-key module. It ran efficiently, with a time complexity of O n log n, from sorting and heap operations, and passed all tests smoothly. Check recap. We verified the logic using multiple test cases. For example, 0, 30, 5, 10, 15, 20 needed 2 rooms, while 7, 10, 2, 4 only needed 1. Even edge cases like no meetings or fully overlapping schedules produce the correct results. Closing insight. The key takeaway? When dealing with overlapping intervals, sorting plus a min heap is a powerful combination. It's not just about detecting overlaps, it's about managing them efficiently.
one meeting at a time.
Rejected, rejected, rejected. At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Schedulers decide who runs next, and the PatternMastery 100 Essential Task Scheduler tests if you can translate a real-world CPU cooldown rule into tight math. Interviewers love it because brute force simulations get messy, but an elegant counting plus formula nails it in one line. Let's master it with BASIC and ship an optimal solution in minutes. Let's break this down. We're given a list of tasks labeled by letters, for example, A, Z, and a cooldown N. Between two runs of the same task, there must be at least N idle intervals. We must compute the minimum number of intervals, tasks plus idles, to finish all tasks. Now let's assess it. A priority queue simulation works but is overkill. There's a clean formula. Let max be the maximum frequency among tasks, and num_max be how many tasks achieve that frequency. We build max 1 full frames, each of length n+1, task plus cooldown slots. The final layer places the num_max most frequent tasks. The answer is max len tasks, max, 1, n+1, plus num_max, because if we have enough other tasks to fill idles, total time is just len tasks. Here is the structure. Plan, count task frequencies, compute fmax and num_max, then apply the formula and return the max with len tasks. Handle edge cases like tasks equals. Now let's implement the greedy heap-based simulation, repeatedly scheduling the most frequent tasks while respecting cooldown gaps. We import heap, which gives us a priority queue, perfect for always choosing the most frequent task next. We also bring in collections, so we can use counter to count task frequencies easily. We're defining the solution class that will compute the least time needed to finish all tasks. This method receives the list of tasks and the cooldown time n, and must schedule them with minimal idle time. We count how many times each task appears. This gives us a frequency map, almost like knowing how many copies of each job we must process. We convert each frequency into a negative number. Python's heap is a min heap, but using negatives makes it behave like a max heap. We turn our list into a heap so we can always grab the task with the highest remaining frequency. We start a global clock that counts every passing unit of time, tasks, or idles. This queue will hold tasks that are cooling down. Each item is release_time, remaining_count. We keep going as long as there are tasks to run or tasks waiting to cool down. Each loop iteration represents one time unit passing. If we have tasks available to run right now, we pop the most frequent task, the negative number with largest magnitude. Because this is stored as a negative, adding 1 moves it closer to 0, meaning we've used one occurrence of the task. If the task still has more remaining occurrences, we push it into the cooldown queue with the time when it will be allowed to run again. Current_time plus n. If the earliest cooling task is now ready to run again, we remove it from the queue. This task is available again. We push it back into the heap so it can be scheduled on future cycles. When all tasks and cooldowns are done, our clock tells us exactly how long the schedule took. And that's how this algorithm works. It first counts how often each task appears, then simulates time using a max heap to pick the best task and a cooldown queue to manage delays. Accurate, greedy, and wonderfully intuitive. Let's check. These are CPU tasks where each same letter must have at least 2 time units of cooldown before it can run again. With a greedy heap simulation, we always pick the task with the highest remaining count that isn't in cooldown, and insert idle slots only when no valid task is available. A valid schedule, one of several, is A, B, idle, A, B, idle, A, B. All 3 A's are spaced by at least 2 units. All 3 B's are also spaced by at least 2 units. Total time slots equals 8. The computed timeline length matches the expected answer, so the heap-based simulation is working correctly. Now let's implement the counting approach, using frequency analysis and a direct formula to compute the minimum required intervals without simulating the timeline. We import collections so we can use counter to count how many times each task appears. We define our solution class that computes the minimum time needed to finish all tasks under cooldown constraints. This method receives the tasks and the cooldown n, and returns the fewest time units needed to finish everything. We build a frequency map of all tasks, essentially counting how many of each type we have. We find the maximum frequency, the number of times the most common task appears. This number dictates the structure of our schedule. We count how many task types appear exactly max_freq times. There might be multiple tasks tied for most frequent, and we must account for them.
We create max_freq, 1 gaps between these highest frequency tasks. Think of the most frequent tasks as forming a skeleton with slots between them. Each gap has a certain size. We start with n cooldown slots, but if multiple tasks tie for most frequent, they fill some of those slots automatically. So we subtract count_max, 1, to compute the leftover empty positions per gap. We now compute the total number of empty slots across the whole schedule frame. We count how many tasks are not part of the most frequent category. These tasks will fill the empty slots if possible. If we still have unused empty slots after placing all remaining tasks, those leftover slots become mandatory idle cycles. If we have enough leftover tasks to fill everything, idle time becomes 0. The total time is simply number of tasks plus number of required idle cycles. This gives us the minimal possible timeline. And that's how this algorithm works. It first analyzes task frequencies to identify the scheduling constraints, then uses a mathematical formula to calculate exactly how many idle slots are unavoidable. No simulation needed, clean, fast, and elegantly optimized. Let's test our function using these tasks. Each letter represents a CPU job, and n=1 means identical tasks need at least 1 cooldown slot between them. We count how often each task appears. A 2 times, B 2 times, C 1 time, D 1 time. The most frequent tasks are A and B, both appearing twice, using the task scheduling formula. But since we have 6 total tasks, the schedule can simply fit all of them with no idle time, giving us 6 units. And that's exactly what our program outputs, 6. The result matches perfectly. So, our implementation is correct. The counting formula efficiently computes the minimal schedule length and behaves exactly as expected. Schedulers decide who runs next, and Task Scheduler turns that real-world CPU rule into math you can master in minutes. It's a brilliant test of logic, counting, and optimization. Let's do a recap. We're given tasks and a cooldown value n, meaning identical tasks must have at least n intervals between them. The goal is to find the minimum total intervals, tasks plus any necessary idle time. While simulating with a priority queue works, it's not efficient. The elegant way is counting. Find the most frequent task, fmax, and how many tasks tie for that frequency, num_max. Use a formula that accounts for full frames of cooldowns and then fills remaining slots. The plan. Count frequencies of all tasks. Compute fmax and num_max. Apply the formula, max total tasks, max, 1, n+1, plus num_max. This gives the minimum time with no unnecessary simulation. We executed this logic cleanly, counted frequencies, applied the formula, and ran the code successfully on LeetCode without any errors. All test cases passed. The math perfectly matched the scheduling outcomes. The big takeaway, math beats simulation. Once you spot patterns in frequency and gaps, scheduling problems become pure arithmetic.
This is not another random playlist. It is a roadmap. Patterns, structure, repetition. The stuff that actually sticks. PatternMastery.com.
Ever had your inbox flooded with duplicate aliases? Accounts Merge is a PatternMastery 100 essential that checks if you can model real data with connectivity. Interviewers love it because the code is short, but the idea, linking emails across users, exposes whether you know union find or DFS cold. Let's conquer it with basic, so your explanation and code are crisp. Let's break this down. We're given a list of accounts. Each is name, email 1, email 2. 2 accounts belong to the same person if any email overlaps. We must merge such accounts and return name, sorted_emails, for each person. Names can repeat, emails are the true identifiers. This screams connected components. Let's assess it. 2 standard approaches. Union find, DSU. Union all emails within an account and then group by the root parent. Graph plus DFS. Connect emails that appear together and collect connected components. Both are near linear in total emails. DSU is tidy and fast. OE alpha, V, almost linear, with hash maps. Sorting each component dominates time. Here's the structure. Create a DSU over emails and a email_to_name map. For each account, union the first email with every other email and record the name for each email. After unions, compress parents and bucket emails by root. For each bucket, output, name, plus sorted emails. Now let's implement the graph-based DFS approach, connecting emails that belong to the same person and exploring each component to merge accounts. We begin with our solution class. This will hold our graph-based merging logic. This method receives a list of accounts, where each account has a name followed by email addresses. Our job is to merge accounts that share at least one email.
This dictionary maps each email back to the person's name. This will become our adjacency list, effectively a graph where each email connects to other emails belonging to the same person. We iterate through every account provided in the input. The first element is always the account holder's name. The rest of the elements are that person's emails. We loop through each email to build our maps. We associate each email with the correct owner's name. If this email hasn't appeared before, initialize it in the graph with an empty set of neighbors. We take the first email as an anchor for connecting all other emails in the same account. We link every other email in the account to this first email. This creates a connection from the first email to the other. And we create the reverse connection, making the graph undirected. We keep track of all emails we've already explored to avoid repeating work. This will store our final merged accounts. We iterate over every email node in the graph. If this email hasn't been grouped yet, we start a DFS from it. We mark it as visited. We use a stack for depth-first search. This list will collect all emails that belong to the same person, one connected component. As long as there are emails to explore, we continue the DFS. We pop the next email from the stack. We add it to our current group. We check all emails connected to this one. If an email hasn't been grouped yet, we mark it visited and push it onto the stack to explore later. We add a new merged account to the output, the owner's name, followed by all emails in the connected component, sorted alphabetically. We return all merged accounts after grouping them by connected components in the email graph. And that's how this algorithm works. It first builds a graph linking all emails that belong together, then performs DFS to gather each connected component into a merged account. Simple graph theory, powerful results. Let's check. Accounts with shared emails must be merged. Using graph plus DFS. First two John accounts share johnsmith@mail.com, so all three emails merge. Mary's email is alone. johnnybravo@mail.com is alone. Sorted groups match the expected sets, order doesn't matter. Output matches expected. The DFS solution is correct. Now let's implement the union find method, efficiently grouping related emails through disjoint set operations to produce the merged account lists. First, we define a union find class. This handles grouping and merging emails that belong to the same account. We initialize an empty dictionary that will track each email's parent in the union find structure. This dictionary maps an email to its parent email, forming a tree-like structure. The find method returns the ultimate root, representative, of an email. If an email's parent isn't itself, it means we've not yet reached the root. This performs path compression, flattening the tree for efficiency. This is why our time complexity is almost linear. Alpha, n, is extremely small. And finally, we return the root. The union method connects two emails under the same root. We find the root of the first email, and we find the root of the second email. If the emails do not yet belong to the same group, we merge them by pointing one root to the other. Now they belong to the same account. We now define the main solution class. This method performs the actual merging using the union find structure. We create a union find instance to manage email groups. We map each email to its account owner so we can label merged accounts later. We loop through each account. The first element is the user's name. We treat the first email as the reference point to connect all others in the account. Now we iterate through all emails belonging to that account. Each email is mapped back to its user. If this email hasn't been seen before, we initialize it as its own parent. We do the same for the account's first email. And here's the key. We unite the first email with the current one, grouping them. Over time, all emails for this user merge into one connected component. We prepare a dictionary to collect emails by their root parent. We iterate through every email we've seen. We find the root parent of this email, that determines which group it belongs to. If this group hasn't been created yet, we initialize it. And then we add the email to its roots group. We prepare our output list. We iterate through each root and its list of emails. For each group, we add a merged account, first the person's name, then all their emails sorted alphabetically. We return the fully merged, sorted list of accounts. Clean, efficient, and elegant. And that's how this algorithm works. It first builds a union find structure to connect related emails, then groups them by their root parent, and finally assembles clean merged accounts. Efficient, structured, and very fast in practice. Let's check. Each row is an independent account. No emails are shared across different names. Union find groups emails that belong together. Here, every one account's emails only union within that row.
so each original account becomes one sorted group. Gabe, Kevin, Ethan, Hanzo, Fern each keeps their own emails, just sorted. Your output has the same groups as expected, only the order of groups differs, which is fine. Output matches expected up to ordering. Union find solution is correct. If your inbox has ever been overrun with duplicate aliases, you know the pain. Accounts merge turns that chaos into clarity, and it's a perfect test of whether you truly understand connectivity with Union Find or DFS. Let's do a recap. We're given accounts as name, email 1, email 2. Any overlap in emails means those accounts belong to the same person. Our job is to merge them so each person appears once with all their emails, sorted. We compared two clean approaches, Union Find, DSU, and Graph plus DFS. Both treat emails as nodes and look for connected components. DSU is especially tidy and near-linear. The time cost is dominated by sorting each merged component. Here's the plan. Map each email to a name, union all emails within the same account, then compress parents and bucket emails by their root. For each bucket, output, name, plus sorted emails. We applied path compression and union by rank to keep operations effectively constant, tied every email in an account to the first one, grouped by root, sorted the emails, and it all ran cleanly on LeetCode without any errors. We verified the logic through the LeetCode run. Components merged correctly, outputs were deterministic after sorting, and all test cases passed as expected. The big takeaway: model the data, not the strings. Once you see emails as a connectivity problem, DSU or DFS makes merging straightforward, fast, and interview-proof.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Have you ever wondered how apps instantly check for repeated characters in your passwords or highlight the longest unique word streak in text analysis? That's the magic behind LeetCode's longest substring without repeating characters, a PatternMastery 100 essential and a frequent favorite in Facebook and Google interviews. Over 40% of candidates overthink this. Let's get you in the winning group. Let's tackle this using the basic framework. This lets us break down the problem, analyze trade-offs, design a clear plan, and check our work, just what interviewers want to hear. We're given a string and need to find the length of the longest substring without any repeating characters. For example, in abcabcb, the answer is 3 for ABC edge cases, empty strings, all repeating characters, and mixed cases. Suppose you're designing a text editor that suggests the longest word or phrase with all unique letters for cryptography or password suggestions. This problem helps you power that feature efficiently. A brute force solution checks every substring, but that's O(n) squared time, much too slow. The optimal approach is to use the sliding window pattern with a hash map, or set, to track characters and their indices. This lets us expand and contract our window efficiently as we scan, guaranteeing O(n) time. Here's our plan. Use 2 pointers, left and right, to define the current substring window. Use a hash map to remember the last index of every character we've seen, as we scan from left to right. If the current character is already in our window, i.e., in the map and its stored index is greater than equals left, move left just past its last occurrence. Update the character's last index in the map. Track and update the maximum window size seen so far. After scanning, return the max length found. Now, let's break down the first Python solution for longest substring without repeating characters, a clean sliding window strategy that tracks unique characters and expands or shrinks the window to find the longest repeat-free stretch. We begin by defining the solution class. LeetCode looks inside this class to find the method it should run. This defines our function. It receives a string s, and our job is to find the longest stretch of characters with no repeats. We create a set called scene. This acts like a quick lookup basket that stores all characters currently inside our sliding window. Using a set gives us O(1) lookup time, helping the whole algorithm stay O(n). This is our left pointer. It marks the beginning of the sliding window. We initialize max_len, which will keep track of the longest substring without repeating characters. We now loop through the string using r as the right pointer. This right pointer expands the sliding window 1 character at a time. If the character at the right pointer is already in our set, that means we've hit a repeat. To fix that, we shrink the window from the left until the repeated character is removed. We remove the character at the left pointer from the set, because we're sliding the window forward. Then we move the left pointer 1 step to the right, narrowing the window. Once repeats are cleared out, we add the new right pointer character into the set. At this point, the window contains only unique characters. Here we update our longest window length. We compare the current window size, r, l plus 1, with the best one we've seen so far. Finally, after exploring the entire string, we return the maximum length found. And that's how this algorithm works. It first sets up a sliding window and a set for tracking characters, then expands and shrinks the window efficiently to avoid repeats. Efficient, simple, and elegant. Test case check. Let's walk through it. Input s equals abc. Let's test our function using this input string, abc. This represents a sequence of characters where we want to determine the length of the longest substring without repeating characters, essentially the longest stretch of unique letters. Quick logic check. As we slide through the string, the first three characters ABC are all unique length 3. When the string repeats at index 3, we reset our window. Several repeats follow, but no substring becomes longer than the initial ABC. So the maximum length of a substring with no duplicated characters is 3.output 3. And that's exactly what our program outputs, 3. It matches the expected result perfectly, confirming the sliding window logic is keeping track of unique characters correctly. So, our implementation is correct. The algorithm efficiently scans through the string using a dynamic window to track unique characters, accurate, optimized, and fully validated by the test case. We begin by defining the solution class. This is where LeetCode looks to find our method. This defines our function. It receives a string s and returns the length of the longest substring that contains no repeating characters. We create a dictionary called index. This will store the most recent position of each character as we scan through the string. This small change makes the algorithm run in on time, because we never move the left pointer backward. This variable will track the length of the longest valid substring we've seen so far. L is our left pointer, marking the start of our sliding window. We now move a right pointer r across the string while grabbing each character ch. This expands our sliding window. This checks whether the current character has appeared inside our current window. If it has, we need to adjust our window to remove the duplicate. Here we move the left pointer just past the previous position of the repeated character. This ensures our window contains only unique characters again. We update the latest index of the current character, overwriting any previous entry. Now we compute the length of the current window, r, l plus 1, and update max_len if this window is the largest so far. Finally, we return the longest substring length we found with no repeating characters. And that's how this algorithm works. It first sets up a sliding window with an index map, then moves the pointers intelligently to skip past repeats while tracking the longest clean stretch of characters. Efficient, simple, and elegant. Highlight input box, s equals bbb. Let's test our function using this input, bbb. This string represents a sequence of repeating characters, and our goal is to find the length of the longest substring without repeating characters. Quick logic check. Here's why the solution works. In this case, the string contains only one unique character, b, repeated 5 times. For example, the first character b gives us a substring of length 1 with no repeats. The moment we move to the second b, we immediately hit a repeat, so the window resets. And the same thing happens for every subsequent character. So the longest stretch of non-repeating characters is simply b by itself, length 1. And that's exactly what our program outputs, 1. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully finds the longest substring without repeating characters, efficient, accurate, and reliable. So, what did we just learn? This problem, longest substring without repeating characters, is one of those perfect tests of logic and pattern recognition that shows how well you can think through a real-time data problem. Breakdown recap. We started by understanding the goal, finding the longest substring in a string that has no repeating characters. Essentially, it's about tracking a clean stretch of unique letters. Assess recap. Then we discussed why brute force just doesn't cut it. It's too slow, checking every possible substring. Instead, the optimal approach uses the sliding window pattern combined with a map or set to keep track of characters efficiently. Structure the logic step by step. 2 pointers to define the window, a map to store character positions, and a way to slide the window forward whenever we hit a repeat, always keeping track of the maximum length seen so far. Implement recap. We then implemented the logic cleanly and ran it on LeetCode, no errors, just a smooth execution. Check recap. The test cases confirmed everything worked as expected, and our solution passed across all examples. Closing insight, the real takeaway? Sliding window problems are all about balance, knowing when to expand and when to contract. Master this technique, and you'll fly through a whole category of string and array problems with confidence.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Ever wondered how text editors like Google Docs can highlight the longest run of nearly identical characters, even if you're allowed to make a few mistakes? That's the magic behind LeetCode's longest substring without repeating characters, a PatternMastery 100 essential and a frequent favorite in Facebook and Google interviews. This problem is the ultimate test of sliding window mastery. Let's use the basic approach: break down, assess, structure, implement, check, to get clarity and confidence. You're given a string and an integer k. Your task? Find the length of the longest substring you can get by replacing at most k characters so that all the characters in the substring are the same. For example, in AABABBA with k equals 1, you can replace 1b to get AAABBA or AABAAA, making a substring of length 4. Edge cases. Strings with all the same characters, k greater than the string's length, or an empty string. Suppose you're building a DNA sequence analyzer. To identify mutation-prone regions, you want to know the longest segment that could be made uniform by changing at most k bases. A brute force approach would try every substring, making replacements. This is O(n cubed), which won't work for long inputs. The optimal strategy is a sliding window. Keep track of character frequencies in the window. The minimum number of replacements needed is window length, count of most frequent character. If this is less than or equal to k, we're good. Otherwise, we shrink the window from the left. This ensures O(n) time, since both pointers only ever move forward. Here's our game plan. Use a hash map or array to track the frequency of each character in the current window. Use 2 pointers, left and right, for the sliding window. For each step, expand the window by moving right. Update the count of the most frequent character in the window. If the window needs more than k replacements, shrink from the left. Track and update the maximum window length throughout. Return the max found. Now, let's break down the first Python solution for longest repeating character replacement. A smart sliding window strategy that tracks character frequencies and expands or shrinks the window to form the longest stretch of repeatable characters. We start by defining the solution class. LeetCode looks inside this class to find the method it should run. This defines our function. It takes a string s and a number k, meaning we're allowed to replace up to k characters to create the longest possible substring of repeating characters. We create a dictionary called count to keep track of how many times each character appears in the current window. This variable will track the highest frequency of any single character inside the sliding window. This number tells us how stable our window is. This will store the longest valid window we've seen so far. This is our left pointer. It marks the beginning of the sliding window. We start moving our right pointer r across the string, expanding the window 1 character at a time. Because each character is visited at most twice, once when added, once when removed, this algorithm runs in O(n) time. We update our frequency map to include the character at the right pointer. We update max_count if this new character appears more frequently than any other in the current window. This expression checks whether the current window is invalid. L+1 is the window size. Max_count is the number of characters we don't need to change. The difference tells us how many characters we must replace to make the window uniform. If that number is greater than k, we need to shrink the window. We reduce the count of the character at the left pointer, because it's leaving the window. We move the left pointer 1 step to the right, shrinking the window. We update our answer with the longest valid window seen so far. Finally, we return the maximum window length that satisfied our replacement rule. And that's how this algorithm works. It first sets up a sliding window and tracks character frequencies, then expands the window while only shrinking when replacements exceed k. Efficient, simple, and elegant. Test case check. Let's walk through it. Input s equals ababk equals 2. Let's test our function using this input string. abab with k equals 2. The string represents a sequence of characters, and our goal is to find the length of the longest substring where we can replace at most k characters to make the entire substring consist of the same character. Quick logic check. In abab, if we choose to make the substring all a's, we can replace the 2 b's. If we choose to make it all b's, we can replace the 2 a's. Because k equals 2, both scenarios are perfectly valid. That means the entire string of Bob can be turned into all A's or all B's with exactly 2 replacements, so the longest valid substring spans the full length, 4. Output PatternMastery. And that's exactly what our function returns, 4. This matches the expected output, confirming our sliding window logic correctly tracks the most frequent character and determines how many replacements are needed. So, our implementation is correct. The algorithm efficiently identifies the longest stretch transformable into repeating characters, accurate, optimized, and fully validated by the test case. We begin by defining the solution class, the container where LeetCode expects our solution method. This declares our function. It receives s, the string we want to analyze, k, the maximum number of replacements allowed. We create a variable to keep track of the longest valid substring we can form. We store the length of the string so we don't have to compute it repeatedly. We loop through all uppercase letters from A to Z. For each letter, we pretend that this character is the final uniform character we want to build a long substring of. This approach takes 26 times n, which simplifies to on since 26 is constant. We set the left pointer of our sliding window to 0. This tracks how many characters inside the current window are not equal to our target letter ch, meaning how many changes we would need. Now we move the right pointer from the start to the end of the string, expanding our window. If the character at the right pointer is not our target letter, we increase the count of characters we would need to replace. If the number of required replacements becomes greater than k, our window becomes invalid. We now shrink the window from the left until it becomes valid again. If the leftmost character is not our target letter, we reduce the replacement count because we are removing that character from the window, and we slide the left pointer to the right, shrinking the window. Here we compute the current window size and update max_length if this window is the largest valid one so far. Finally, after testing all 26 possible target letters, we return the length of the longest valid substring we found. And that's how this algorithm works. It first tries every letter as the target, then uses a sliding window to expand and contract while keeping track of replacements. Efficient, simple, and elegant. Let's test our function using this input. S equals a baba and k equals 1. This string represents a sequence of characters, and k tells us how many characters we're allowed to replace in order to form the longest possible substring of repeating characters. Quick logic check. Here's why the solution works. We want the longest substring we can turn into all the same letter using at most one replacement. For example, consider the window ABA. It has 3 A's and 1 B. With one replacement, we can turn the B into an A, giving us a length of 4. The algorithm slides across the string, keeping track of how many times the most frequent character appears in the window, and whether we can fill the rest using at most k changes. No other window can beat that length of 4 using only one replacement. And that's exactly what our program outputs, 4. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully finds the longest substring transformable into repeating characters with up to k replacements, efficient, accurate, and reliable. Alright, let's wrap it up. The longest repeating character replacement problem is one of those elegant sliding window challenges that tests how well you can balance flexibility and precision, just like optimizing text or DNA analysis in real time. We began by understanding the goal. Find the longest substring where you can replace at most k characters to make every character in it the same. Essentially, it's all about maximizing a uniform run within limited edits. We compared the brute force approach, which checks every possible substring, far too slow, with the sliding window method, which keeps track of character frequencies and adjusts efficiently. This gave us a clean ON solution. Our plan was clear. Use 2 pointers to represent the window, track how often each character appears, and expand or shrink the window based on whether we exceed the allowed number of replacements. Throughout, we keep updating the longest valid window length. We translated this logic step by step, ran it successfully on LeetCode, and the code executed perfectly without any errors. All test cases passed smoothly, confirming that our logic correctly handles everything from uniform strings to shifting mixed patterns. The takeaway? Sliding window mastery is all about control, expanding when you can, contracting when you must, and always keeping track of what matters most. Nail this, and you'll be ready for some of the toughest optimization problems in interviews.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com
Have you ever tried to find the shortest snippet of text that contains all the key words you care about, like searching for the tightest passage in an email or document? That's exactly the challenge behind LeetCode's minimum window substring, a top PatternMastery 100 problem and a classic interview favorite at Google and Amazon. Many stumble on window management here. Master it and you'll instantly stand out. Let's break it down with the basic approach: breakdown, assess, structure, implement, and check. We're given two strings, S, the text, and T, the set of required characters. Our goal: find the smallest substring in S that contains all the characters from T, including duplicates. For example, with S equals ADOBEC, ODEBANC, and T equals ABC, the answer is BANC. Edge cases: what if no window exists? What if T is longer than S? What if all required characters are the same? Imagine building a search feature that highlights the shortest quote or phrase containing every important keyword, perfect for emails, log analysis, or even bioinformatics. A brute force approach would check every possible substring. O(n) cubed time, way too slow for large data. Optimal solution: use a sliding window with two hash maps, or arrays, one to count needed characters, one for the current window's characters. Move the window's right edge to expand until you have all of T, then move the left edge to shrink and minimize. Key insight: we only care about windows that are valid, have all of T, and we want the minimum length 1. Time complexity: O(n) plus m, where n and m are the lengths of S and T. Here's our plan. Build a hash map for character counts in T. Set up 2 pointers, left, right, for the window, and variables to track how many required chars are satisfied. Expand right to include new characters and update the window count. When the window is valid, contains all of T, try shrinking from the left to minimize it, always updating the best minimum window found. Continue until you've scanned S, return the minimum window, or empty string if none found. Now, let's break down the first Python solution for minimum window substring, a clever sliding window approach that finds the smallest substring containing all the required characters. We start by defining the solution class. LeetCode looks inside this class to find the function it needs to run. This defines our function min_window, which receives two strings. S, the big string we're searching through. T, the set of characters we need to find inside a window of S. This checks if either string is empty. If one is empty, we already know there's no meaningful window to return. In that case, we immediately return an empty result. We build a frequency map of all the characters in T. This tells us exactly how many times each character must appear in our window. This setup is part of the sliding window strategy, and the algorithm overall runs in O(n) plus m time. Have will track how many times each character appears in our current sliding window. Required is the number of unique characters we must fully match to satisfy the window. This counts how many characters currently meet the required frequency inside the window. We set our left pointer L, which will slide forward to shrink the window whenever possible. This will store the best, smallest, valid window we find. We track the best window length using a very large initial number so any real window will be shorter. Now we begin sliding the right pointer across the string. Each step expands the window by one character. We update our have count to show that this character is now included in the current window. If this character is needed and we now have the exact amount required, we increase formed. This signals that one more required character condition has been satisfied. This loop runs only while our window is fully meeting all character requirements, meaning the current window is valid. Here, we try to shrink the window from the left to make it as small as possible. If the current window is smaller than the best one we found, we update our best answer. We record the new smallest length, and we save the actual window substring. Before shrinking the window, we capture the character at the left edge. Then we reduce its count in our have dictionary, because it's about to be removed from the window. If removing this character makes us fall below the required amount, the window is no longer valid. So we reduce formed since we no longer meet all requirements. And we slide the left pointer forward, officially shrinking the window. After scanning the entire string, we return the smallest valid window found. And that's how this algorithm works. It first sets up the character requirements, then uses a sliding window to expand and contract until it finds the smallest substring containing all needed characters. Efficient, simple, and elegant. Test case check. Let's walk through it. Input S equals ADOBECODEBAN, CT equals ABC. Let's test our function using this input. ADOBECODEBANC as the source string, and ABC as the target set of characters. We're looking for the smallest substring in S that contains all characters from T, including duplicates if needed. Quick logic check to satisfy the requirement: the window must include
A, B, C. As we slide through the string, the first valid window we encounter is ADOBEC, but it's longer than needed. Continuing the search, we eventually find a tighter window, bank, which starts at index 9 and ends at index 12. This window contains all characters A, B, and C exactly once, and no smaller valid window exists. Output BANC, and that's exactly what our program outputs, BANC. It matches the expected result perfectly, confirming that our sliding window logic is working as intended. So, our implementation is correct. The algorithm efficiently narrows down the smallest valid substring using a dynamic window, accurate, optimized, and fully validated by the test case. We start by defining the solution class. This is the structure LeetCode uses to find the method that solves the problem. This defines our function. It receives two strings. S, the long text we search inside. T, the set of characters we want to find in the smallest possible window. We create a frequency map of all characters in T. This tells us exactly how many of each character must appear in a valid window. We set min_len to infinity so that any real window we find will be smaller. This will eventually store the best, shortest, window that contains all characters of T. We begin scanning S from the left using index I. This marks the start of a possible window. If the starting character isn't even in T, there's no reason to start a window here. So we skip this position and move on. We copy the requirements for this specific attempt. As we scan forward, we'll reduce counts until we satisfy the entire set. Now we expand the window using index J, scanning forward to see how many characters we can collect. If the current character is part of what we need, we reduce the required amount for that character. If we've collected enough of that character, we remove it from the list of remaining requirements. This checks whether our window now contains all characters from T. If cur_need is empty, we've satisfied the entire requirement. If this is the smallest valid window we've seen so far, we update our smallest window length, and we store the actual substring as our new result. Because we found a valid window starting at I, there's no need to expand further. Any larger window wouldn't be better. After checking all possible windows, we return the smallest substring that contains all characters from T. And that's how this algorithm works. It first sets up the required character counts, then uses a two-layer scan to test every valid window and record the smallest one. Efficient, simple, and elegant. Let's test our function using this input. S equals A and T equals A. These values represent two single character strings, and our goal is simply to check whether they contain the same character, which is the definition of an anagram. Quick logic check. Here's why the solution works. Since both strings contain just one character, the algorithm compares them by counting how many times each character appears. For example, in S, the character A appears once. When we process T, we subtract 1A from the count. After this, there are no leftover characters or mismatches, so the strings match perfectly. And that's exactly what our program outputs. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully verifies that both strings contain the same character in the same amount, efficient, accurate, and reliable. Sliding window mastery equals control over efficiency and precision. Learning this teaches how to balance expansion and contraction logic, a must for advanced string problems. Alright, let's wrap it up. The minimum window substring problem is a true test of precision. It's not just about finding a match, but finding the tightest possible window that contains all required characters. Nail this one, and you've mastered one of the trickiest patterns in string manipulation. We started with the challenge: given two strings, find the smallest substring in the main text that contains all characters from the target, including duplicates. It's like locating the most compact snippet that covers every key requirement. We compared approaches and saw why brute force quickly becomes unmanageable. Checking every substring is simply too slow. The sliding window method, powered by character frequency tracking, gives us the efficiency and control we need, running in linear time. Our plan was to use two pointers to expand and shrink the window dynamically. As we move right, we include more characters. When the window meets all requirements, we shift left to minimize it, constantly updating the smallest valid window found so far. We built the logic step by step, ran it on LeetCode, and it executed smoothly, no errors, perfectly capturing the minimal window each time. After verifying with multiple test cases, every result matched expectations, confirming that our approach handles both typical and edge cases efficiently.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Today, we're diving into LeetCode's Valid Anagram, a PatternMastery 100 classic that every Apple or Microsoft interviewee must master. Did you know this question gets asked in over 10% of all top-tier coding interviews? It seems simple, but it's a lightning-fast test of your string and hash map skills. Let's see how you can ace it. We'll use the basic framework, which gives us a systematic way to break down, analyze, and solve problems, going beyond star by focusing on code, patterns, and pitfalls. Let's restate the problem. Given two strings, s and t, we need to determine if t is an anagram of s. That means both strings must have exactly the same characters with the exact same frequencies, but possibly in a different order. For example, listen and silent are anagrams. Edge cases, empty strings, case sensitivity, strings of different lengths. Picture an e-commerce platform checking if two customer orders contain the exact same items, just arranged differently. Maybe someone's resubmitted their cart. A quick anagram check can flag duplicate orders with items shuffled. What challenges do we face? At first glance, you might think, just sort both strings and compare. That's valid. O(n) log n. Time, simple, but maybe not optimal for very large datasets. A more efficient way? Use a hash map, or an array if all chars are lowercase English letters, to count occurrences for each character in both strings, and then compare the results, O(n) time and O(1) space, since our alphabet size is fixed. Here's our plan. If the strings have different lengths, return false right away. Use an array, size 26 for lowercase, to count up each character in s and subtract for each in t. After processing, if any count isn't 0, they're not anagrams. Imagine you're a chef double-checking two lists of ingredients for the same recipe. For every item in the first list, add a tally. For every item in the second list, subtract a tally. At the end, every tally should be exactly 0, meaning you have the same stuff, just in a different order. Let's do a walkthrough. Example, s equals anagram, t equals anagram. Start with an array of zeros. Count a in anagram, +3. Count n, +1. Count g, +1. Count r, +1. Count m, +1. Now, subtract for each character in anagram. N, -1, now 0. A, -3, now 0. G, -1, now 0. R, -1, now 0. M, -1, now 0. After all, every count is 0, so they're anagrams. This approach is blazing fast and uses barely any extra memory. Now, let's break down the first Python solution for valid anagrams, a simple and intuitive approach that checks whether two words contain exactly the same letters. We begin by defining the solution class. This is the standard structure LeetCode expects, so it knows where your function lives. This defines our function as anagram, which takes two strings, s and t. Our job is to determine whether they're anagrams of each other, meaning they contain the same letters in any order. Right away, we check if the two strings have different lengths. If they don't match, they can't possibly be anagrams, like two puzzles with different numbers of pieces. If the lengths aren't equal, we stop immediately and return false. Here's the heart of the solution. We sort the letters in each string, turning messy letter order into neat alphabetical order. If the sorted versions match, the strings contain the same letters, so they are anagrams. Because sorting takes time, this step gives the algorithm its O(n) log n, time complexity. And that's how this algorithm works. It first checks for a quick length mismatch, then compares the sorted versions of both strings to confirm whether they're perfect letter matches. Efficient, simple, and elegant. Test case check. Let's walk through it. Input. S equals anagram. T equals anagram. Let's test our function using these two strings. Anagram and anagram. These represent the classic anagram check scenario. We want to determine whether both strings contain the exact same characters with the same frequencies, just in a different order. Quick logic check. When we break down the letters, anagram contains A3, N1, G1, R1, M1. Anagram contains A3, N1, G1, R1, M1. Every count matches perfectly. So yes, they are anagrams. Output true, and that's exactly what our program outputs. True. This matches the expected result, which confirms that the algorithm correctly checks the character frequencies. So, our implementation is correct. The algorithm efficiently counts characters and verifies both strings match, accurate, quick, and fully validated by the test case. Here we're defining a class called solution. This just organizes our function the way LeetCode expects. This defines our function as anagram, which takes in two strings, s and t, and checks if they're anagrams. First, we compare the lengths of the two strings. If their lengths don't match, there's no way they contain the same characters in the same amounts, so if the lengths differ, we immediately return false. Quick, simple, and prevents unnecessary work. This early check runs in O1 time. Next, we create an empty dictionary called count. Think of this like a small tally sheet where we'll keep track of how many times each character appears in S. Now we loop through every character in the first string, S. This full pass through the string takes ON time. For each character, we update its count. If it's already in our dictionary, we add 1. If it's not there yet, get ch, 0, starts it at 0. We're basically saying, I saw this character one more time. Now we loop through every character in the second string, t. Another ON pass. For each character in t, we check two things. If this character never appeared in S, or if we've already used up all its available counts. In either case, t cannot match S, so they're not anagrams. If either condition is true, we return false right away. No need to keep checking further. Otherwise, we reduce that character's count by 1, meaning we're using up one occurrence of it. This keeps the character tallies perfectly balanced between the two strings. Finally, if we make it through both loops without failing any checks, it means every character is accounted for. The two strings match perfectly, so we return true. And that's how this algorithm works. It first builds a count of all characters in the first string, then subtracts those counts based on the second string. If everything evens out, the words are anagrams. Efficient, simple, and elegant, all in ON time. Let's test our function using this input. S equals anagram and T equals anagram. These strings represent two words, and our goal is to check whether they contain the exact same characters with the exact same frequencies, just arranged differently. In other words, whether they are anagrams. Quick logic check. Here's why the solution works. Our algorithm creates a character count for the first string and then subtracts those counts using the second string. For example, in anagram, the character appears 3 times. When we loop through anagram, we subtract 1 each time it appears. The same happens for N, G, R, and M. If any character count ever hits below 0, or a character doesn't exist in the dictionary, we would immediately return false. But here, everything matches perfectly. Every character in T cancels out the counts from S. And that's exactly what our program outputs, true. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully verifies that both strings contain matching character frequencies, efficient, accurate, and reliable. The key takeaway? Problems like this remind you that elegant solutions often come from counting, not sorting. When you understand data patterns deeply, efficiency becomes second nature, and that's what truly sets strong engineers apart. Let's wrap this up. The valid anagram problem might look simple at first glance, but it's one of the best tests of your ability to think efficiently about string comparison, a favorite at companies like Apple and Microsoft. We started by defining the goal. Determine if two strings contain the exact same characters with the exact same frequencies, just possibly in a different order. In other words, can one be rearranged to form the other? We compared two main ideas, sorting both strings and comparing them, which works but takes extra time, versus using a hash map or frequency array to count characters in linear time. The latter gives us a clean, ON approach that scales beautifully. Our logical plan was simple. If the two strings differ in length, they can't be anagrams. Otherwise, tally up character counts from the first string, subtract for the second, and ensure everything balances back to 0, meaning perfect character symmetry. We followed that logic step by step, ran it successfully on LeetCode, and the execution was flawless, no errors, no extra space wasted. After testing multiple cases, every result matched exactly as expected, confirming our logic handles all edge scenarios, from empty strings to repeated letters.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
Here's a problem that really tests your data structure instincts. Group anagrams. This Pattern Mastery 100 favorite pops up at Google, Meta, and Amazon, challenging you to group together words that are rearrangements of each other. As shown in the image, we're not just checking two words, we're clustering a whole list. If you master this, you'll show interviewers that you can go beyond pairwise logic and handle real-world data grouping. Let's dive in. Here's the challenge. Given an array of strings, group the anagrams together. Anagrams have the same letters in a different order, so eat and tea are anagrams, as are tan and ant. As shown in the image, the output should be a list of lists, with each group containing words that are anagrams of each other. What's tricky? A brute force way would be to check every word against every other, n² comparisons. That's slow. The real trick is to find a unique signature for each group, so you can collect them in n time. The easiest way? Sort each word alphabetically and use that as a hash map key. Every anagram will have the same sorted form. Here's the plan. Create a hash map, dictionary, to group words by their sorted signature. For each word, sort its letters to get the signature key. Add the word to the group in the hash map with this key. At the end, return all the grouped values as a list. Now, let's break down the first Python solution for group anagrams, a simple and intuitive approach that groups words by their shared letter patterns. We start by defining a solution class. This is the standard structure LeetCode uses to run your code. This defines our main function. It receives a list of strings, and our job is to group together all words that are anagrams of each other. Here we create an empty dictionary called groups. Think of this as labeled buckets where each key represents a group of anagrams, and each bucket stores all the strings that belong together. We loop through every word in the list. One by one, we're going to figure out which bucket that word belongs in. This is the clever part. We sort the letters of the word S, and that sorted version becomes the signature of the anagram group. For example, both eat and tea become eat. Creating this key requires sorting, so this part contributes to the onk log k time complexity. We check whether this signature already exists in our dictionary. If the bucket doesn't yet exist, we create a brand new empty bucket for this anagram pattern. Now we add the current word S to its matching bucket. Words with the same sorted signature are grouped together automatically. Finally, we return all the buckets as a list. Each inner list contains one full group of anagrams. And that's how this algorithm works. It first builds a dictionary to store groups, then uses a sorted version of each word to place it into the right group. Efficient, simple, and elegant. Test case check. Let's walk through it. Input strs equals eat, tea, tan, ate, nat, bat. Let's test our function using this input array. Eat, tea, tan, ate, nat, bat. These strings represent a list of words, and our goal is to group the anagrams, words that contain the exact same letters but in different orders. Quick logic check. To group anagrams, we sort the characters of each word. Eat, tea, and ate all become eat, they go in the same group. Tan and nat both become ant, they form another group. Bat becomes abt, stands alone in its own group. So we expect 3 groups total. Output: tan, nat, bat, eat, tea, ate, and that's exactly what our program outputs, neatly grouped sets of anagrams. Even though the order of groups can vary, the content matches the expected result. Expected: bat, nat, tan, ate, eat, tea. Your output: tan, nat, bat, eat, tea, ate. Everything lines up correctly, same groups, same words. So, our implementation is correct. The algorithm accurately groups all anagrams by using their sorted signatures, clean, efficient, and fully validated by the test case. We begin by defining the solution class, the structure LeetCode looks into to run our method. This defines our function. It receives a list of strings and must group together all words that are anagrams of each other. We create an empty dictionary called groups. This will map a unique signature, our character count key, to a list of all anagrams that share that signature. We loop through each string in the input. Every word will be analyzed and placed into its matching anagram group. We build a 26-element list representing the frequency of each letter from A to Z. This becomes the key idea behind Solution 2, transforming each string into a fixed-size signature, making grouping fast and efficient. This keeps our solution at onmiddle.k time, where n is the number of strings and k is the average length. We now scan through each character in the current string. This increments the bucket that corresponds to the letter ch. By converting the character to an index, we ensure accurate tracking of all letters. We convert the list into a tuple so it becomes hashable and can be used as a dictionary key. This tuple uniquely represents how many of each letter appear in the word, meaning all true anagrams share exactly the same key. If this signature hasn't been seen before, we create a new group for it. We initialize an empty list to store all words belonging to this anagram group. Then we add the current word to its matching group. Finally, we return a list of all grouped anagrams. And that's how this algorithm works. It first builds a fixed-size character count signature for each word, then groups words that share the same signature. Efficient, simple, and elegant. Let's test our function using this input. Eat, t, tan, ate, nat, bat. These strings represent a list of words, and our goal is to group together all the words that are anagrams of each other, meaning they use the exact same letters, just rearranged. Here's why the solution works. The algorithm groups words by a common key, usually the sorted version of the word. For example, eat, tea, and ate all sort to eat, they belong in the same group. Tan and nat both sort to ant, they form another group. Bat sorts to abt, it stands alone in its own group. So we end up with 3 valid anagram groups. And that's exactly what our program outputs. Eat, tea, ate, bat, tan, nat. This matches the expected groups. Bat, nat, tan, ate, eat, tea. The order of the groups and the order of words inside each group doesn't matter, as long as the anagram sets are correct, and they are. So, our implementation is correct. The algorithm successfully groups all anagrams that share the same character multiset, efficient, accurate, and reliable. The big takeaway? When solving problems like this, stop comparing, start categorizing. By identifying unique signatures for patterns, you not only improve efficiency but also show interviewers that you think like a true problem solver. Have you ever noticed how some problems test not just your logic, but your data structure instincts? That's exactly what group anagrams does. One of those interview favorites that shows whether you can move from pairwise logic to true data grouping. We were asked to take a list of words and group together all those that are anagrams, words made up of the same letters, just in different orders. Essentially, it's about finding clusters of rearranged words efficiently. A brute force approach would compare every word against every other, (n² time, which is way too slow. Instead, we looked for a smarter way, giving each group a unique signature by sorting the letters inside each word. That becomes our hashmap key, and every anagram naturally falls into its matching group. We looped through the list, sorted each word alphabetically, and used that sorted version as the key in a hashmap. Each time, we simply added the original word to its corresponding group. By the end, each key represented one group of anagrams. Implement recap. We then ran this logic step by step in LeetCode. No syntax issues, no edge case surprises. The grouping worked perfectly. After running through the test cases, every input matched the expected output, confirming that the hashmap method grouped all anagrams correctly and efficiently.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Have you ever wondered how apps like WhatsApp or Google Docs instantly check if a message reads the same backward and forward, even with punctuation and mixed case? That's the challenge behind LeetCode's valid palindrome, one of the top Pattern Mastery 100 questions and a regular feature in tech interviews. Over 25% of candidates fumble with edge cases here. Let's make sure you're not one of them. A step up from the classic star method, perfect for technical breakdowns. We're given a string and need to determine if it's a palindrome. We're given a string and need to determine if it's a palindrome, meaning it reads the same backward and forward, ignoring non-alphanumeric characters and letter case. For example, a man, a plan, a canal, Panama should return true, while race a car should return false. Empty strings, strings with only symbols, mixed upper and lower case, or numbers mixed in. Imagine building a chat moderation tool that checks if users are sending palindromic phrases for fun badges, regardless of punctuation, spaces, or case. You want this check to be fast and bulletproof against any formatting. A naive approach would be to reverse the string and compare, but we'd need to remove all non-alphanumeric characters and normalize case first. We want an efficient approach that also handles gigantic strings without wasting space. Optimal pattern. Use the two-pointer technique, one pointer from the start, one from the end. Skip all non-alphanumeric characters, and compare as you go. Time complexity is O(n). Space is O(1) if we process in place. Here's the plan. Initialize two pointers, one at the start, one at the end, while the pointers haven't crossed. Skip any non-alphanumeric characters at each end. Compare the characters, convert both to lowercase. If they match, move both pointers inward and continue. If they don't match, return false, it's not a palindrome. If all checks pass, return true. Let's try to implement it using solution 1. Line-by-line narration, line highlighted, class solution. Here we're simply defining a class called solution. This is just a container where our function will live. Pause. Line highlighted, def is palindrome self, str, greater than bool. This line defines a function named isPalindrome, which takes a string s and will return a true or false value depending on whether the string is a valid palindrome. Think of this like naming a little machine whose job is to check symmetry. Pause. Line highlighted, left, right equals 0, lens, 1. Here we set up 2 pointers, one starting at the very beginning of the string, left equals 0, and one starting at the very end, right equals lens, 1. It's like having 2 fingers pointing at opposite ends, slowly walking inward. Time complexity note. Just setting variables, 1, pause. Line highlighted, while left less than right. This loop keeps running as long as our left pointer hasn't crossed our right pointer. Essentially, we'll keep checking pairs of characters from both sides until they meet in the middle. Time complexity. This loop can move each pointer across the string once, giving us on, pause. Line highlighted, #skip non-alphanumeric characters from the left. This comment tells us exactly what the next block of code will do. Ignore anything that isn't a letter or number. Pause. Line highlighted, while left less than right and not s left. Isonym. This line checks whether the current character on the left is not alphanumeric. If it's something like a space, comma, emoji, or punctuation mark, we'll skip it. This ensures we only compare real letters and numbers. Pause. Line highlighted, left plus equals 1. If the character wasn't alphanumeric, we move the left pointer one step to the right, kind of like saying, nope, skip that, try the next one. Time complexity. Skipping still counts toward on because each pointer moves at most n times. Pause. Line highlighted, #skip non-alphanumeric characters from the right. Another helpful comment. Same idea, but now for the right side. Pause. Line highlighted, while left less than right and not s right. Isonym. This checks if the current right side character isn't alphanumeric. If it's something like exclamation mark or white space, we'll skip past it. Pause. Line highlighted, right equals 1, and here we step the right pointer one space to the left, moving inward. Pause. Line highlighted, #compare characters case insensitively. This comment reminds us that uppercase versus lowercase shouldn't matter when checking for palindromes. Pause. Line highlighted, if s left, lower, equals s right, lower, we now finally compare the actual letters. We convert both sides to lowercase to avoid mismatches like a versus a. If they don't match, we immediately know the string isn't a palindrome and return false right away. Time complexity. Each comparison is 1, but done up to n/2 times overall on. Pause. Line highlighted, left plus equals 1. Since the characters matched, we move the left pointer inward for the next comparison. Pause. Line highlighted, right equals 1, and we do the same with the right pointer, stepping it one position to the left. Pause. Line highlighted, return true. If the loop finishes without finding any mismatched characters, then the string is indeed a palindrome, so we return true as our final result. Pause. Final wrap-up. And that's how this algorithm works. It first sets up 2 pointers, then moves them inward while skipping non-alphanumeric characters and comparing the meaningful ones. Efficient, simple, and elegant. Highlight input box. S equals a man, a plan, a canal, Panama. Let's test our function using this string. A man, a plan, a canal, Panama. This is a classic palindrome phrase that includes spaces, commas, and a colon, along with both uppercase and lowercase letters. Explain the logic briefly. Our algorithm ignores all non-alphanumeric characters and treats letters in a case-insensitive way. So this input is effectively turned into a man, a plane, a canal, Panama. If we compare characters from the start and end moving toward the center, every pair matches, so the clean string reads the same forwards and backwards, exactly what defines a palindrome. Highlight output box. Output, true, expected, true, and that's what our program returns. True, which matches the expected result true. So, our implementation is correct. The algorithm successfully finds the maximum profit in a single pass through the prices, efficient and accurate. Now let's try another implement approach using solution 2. Line highlighted, class solution. We begin by creating a class called solution, just a container to hold our palindrome checking method. Pause. Line highlighted, def is palindrome self s. This defines our function as palindrome, which checks whether a given string reads the same forwards and backwards after we clean it. Pause. Line highlighted, #build filtered string with only alphanumeric chars in lowercase. This comment explains the plan. We're going to build a clean version of the string that contains only letters and digits, all in lowercase. Pause. Line highlighted, filtered equals. Here we create an empty list called filtered. Think of it as a small basket where we'll store only the useful characters from the input. Pause. Line highlighted, for char in S. This loop goes through the string one character at a time. Time complexity. This loop inspects every character on. Pause. Line highlighted, if char.isolnum, we check if the character is alphanumeric, meaning it's a letter or a number. Spaces, punctuation, and special symbols are ignored. Pause. Line highlighted, filtered.append char.lower. If it is alphanumeric, we convert it to lowercase and add it to the filtered list. This ensures case doesn't affect our palindrome check. A and A are treated the same. Appending is O1, so across the whole loop we remain at ON. Pause. Line highlighted, hash check if filtered list equals its reverse. This comment tells us the final step. Compare the cleaned version of the string to its reverse. Pause. Line highlighted, return filtered equals filtered. -1 This is the key comparison. Filtered is our cleaned sequence of characters. Filtered, -1, creates a reversed copy. If both lists are identical, the string is a palindrome. Otherwise, it isn't. Creating the reversed list is ON, and comparing the two is also ON. Overall time complexity, ON. Overall space complexity, ON because we store the filtered list and its reversed copy. Pause. Final wrap-up. And that's how this algorithm works. It first builds a filtered lowercase list of only alphanumeric characters, then checks whether that cleaned list is equal to its reversed version. Efficient, simple, and elegant. Highlight input box. S equals a man, a plan, a canal, Panama. Let's test our function using this string. A man, a plan, a canal, Panama. This is a classic palindrome phrase that includes spaces, commas, and a colon, along with both uppercase and lowercase letters. Explain the logic briefly. Our algorithm ignores all non-alphanumeric characters and treats letters in a case-insensitive way. So this input is effectively turned into a mana plane a canal Panama. If we compare characters from the start and end moving toward the center, every pair matches, so the clean string reads the same forwards and backwards, exactly what defines a palindrome. Highlight output box. Output, true, expected, true, and that's what our program returns. True, which matches the expected result true. So, our implementation is correct. The algorithm successfully finds the maximum profit in a single pass through the prices, efficient and accurate. Let's wrap up valid palindrome. A deceptively simple question that tests your attention to detail and mastery of two-pointer logic. The task was to check if a string reads the same forward and backward, ignoring punctuation, spaces, and case sensitivity. It's about comparing structure, not formatting. We compared two main approaches, cleaning and reversing versus using two pointers. The two-pointer method won for efficiency. Scanning from both ends while skipping non-alphanumeric characters gives us ON time and O1 space. Our plan was simple. Move two pointers inward, skip invalid characters, compare lowercase letters, and stop early if any mismatch is found. We translated that plan directly into code, using clean pointer movement and case normalization, and it executed perfectly on LeetCode. Tests like a man, a plan, a canal, Panama returned true, while race a car returned false. Edge cases like empty or all space strings also passed as valid palindromes. The takeaway? Two-pointer strategies aren't just for arrays, they're powerful tools for string analysis too. Once you master this flow, you're ready for problems like valid palindrome 2 and longest palindromic substring.
This is not another random playlist. It is a roadmap, patterns, structure, repetition. The stuff that actually sticks. PatternMastery.com.
Can you count all the hidden mirrors in a string? Palindromic substrings is a PatternMastery 100 staple and a favorite at Google, Amazon, and Meta for testing two-pointer and dynamic programming fluency. Over 30% of candidates either miss double counts or don't handle both even and odd centers. Nail this, and you'll master one of the most fundamental patterns in string analysis. Let's break down palindromic substrings using the basic approach, so you can confidently handle any substring counting or expansion problem. Given a string S, return the number of palindromic substrings in it. Substrings must be contiguous. Each character counts as a palindrome. String S. Integer, total number of palindromic substrings. Imagine analyzing DNA or encrypted messages to find every symmetrical pattern. Interviewers might ask, How would you efficiently count all mirrored subsequences in a string? What's tricky? Need to count every palindromic substring, not just the longest. Must handle odd, centered at a character, and even, centered between two characters, length palindromes. Expanding around centers is more efficient than checking every substring directly. For each character, and each gap between characters, expand outward as long as you have a palindrome. For every expansion, increment a count. This covers both odd, single center, and even, double center, palindromes. Let's clarify. There are two n1 centers for a string of length n characters plus n1 gaps. Each expansion is on in total, so the overall solution is on squared. Edge cases. Single character, count is 1. All same characters, count all possible substrings. Empty string, count is 0. Initialize a count to 0. For every index in S. Expand around center at index, odd length. Expand around center between index and index plus 1, even length. For each valid expansion, increment the count. Return the total count at the end. Use a helper function to expand. Let's try to implement it using solution 1. We begin by defining a class called solution, which simply groups our function together. Think of it as a folder holding the code we're about to explain. This line defines a function named count substrings, which takes a string S and returns how many palindromic substrings it contains. In other words, we're counting all the mini palindromes hidden inside the string, even single letters count. Pause. Line highlighted. Def expand underscore around underscore center left, right. Inside our function, we define a helper function called expand underscore around underscore center. Its job is to check how many palindromes can expand outward from a given center point. This is the heart of the algorithm. By setting up a counter that will track how many palindromes we find for this particular center. This while loop expands outward as long as 3 conditions are true. We stay inside the bounds of the string. The characters at the left and right pointers match, meaning we're still forming a palindrome. If any of these stop being true, we stop expanding. Time complexity note. Expanding each center is on in the worst case. We found another palindrome, so we increment our count. Even a single matching pair like A is counted. Then we expand one step to the left, checking if we can grow the palindrome larger. We expand one step to the right. The goal is to stretch the palindrome as far as possible. Once the expansion stops, we return how many palindromes were discovered for this specific center. Now back in the main function, we set up total to keep track of how many palindromic substrings we find in the whole string. This loop goes through each index in the string, treating each position as a potential center of a palindrome. Time complexity. This loop runs n times. Combined with expansion, our full complexity becomes on squared. Comment tells us the next line counts palindromes with a single central character. Examples include A, race car. We call our helper function with both pointers at the same position. That checks for odd-length palindromes. Every single character guarantees at least one palindrome. Center between I and I plus 1. This comment explains that some palindromes don't have a middle character. Examples include AA or ABBA. Here we check for even-length palindromes by starting with 2 adjacent characters as the center. If they match, we expand outward from there. Finally, after checking every possible center, we return the total number of palindromic substrings found in the entire string. And that's how this algorithm works. It first sets up a helper function that expands around a center, then loops through every possible center, both odd and even, to count every palindrome it can form. Efficient, simple, and elegant. Highlight input box, S equals ABC. Let's run our function with the input string, ABC. Here, each character is unique, so we're looking at a sequence with no repeats at all. Explain the logic briefly. Our algorithm slides a window across the string while tracking characters we've already seen. Since A, B, and C are all distinct and appear only once, the longest substring without repeating characters is simply the whole string itself, length 3. Highlight output box, output, 3, expected, 3, and that's exactly what the program returns. 3, perfectly matching the expected result. The test case passes without a hitch. So, our implementation is correct. The algorithm efficiently identifies the longest unique character substring in a single scan, clean and accurate. Now let's try another implement approach using solution 2. We begin by defining a class called solution, which simply acts as a container for our function. This function, count substrings, counts how many palindromic substrings exist inside the string S. It uses dynamic programming to build up results from smaller substrings to larger ones. Here we calculate the length of the input string and store it in n. We'll use this value repeatedly throughout the algorithm. We initialize a variable count to keep track of how many palindromic substrings we've found so far. This comment explains the structure of our dynamic programming table. dpij represents whether the substring from index I to index j is a palindrome. We create a 2D table, nxn, where every entry starts as false. This matrix will help us store results for all possible substrings. Space complexity, O(n) squared because we store results for every pair, I, j. Hash every single character is a palindrome. This comment reminds us that any one individual character is automatically a palindrome. We loop through every index in the string. We mark each single character SII+1 as a palindrome. This fills in the diagonal of our DP table. Each single character counts as one palindromic substring, so we increase our total count. Time complexity so far, O(n) for this loop. This comment indicates that we're now checking substrings of exactly 2 characters. We loop through each pair of adjacent characters. Here we check if the 2 characters match. If they're equal, that pair forms a palindrome like AA or BB. Line highlighted DPII+1 equals true. When we find such a pair, we mark it as true in our DP table. And we increase the count because we found another palindromic substring. This tells us that now we're analyzing longer substrings using previously computed results. This loop tries all possible substring lengths starting from 3 up to the full length of the string. For each length, we choose all valid starting positions I so the substring stays inside the string. We compute the ending index j of the substring we're checking. Here is the heart of the DP logic. A longer substring Sij+1 is a palindrome if the outer characters match, Si equals Sj, and the inner substring, Si+1:j, is already marked as a palindrome in DP. This lets us build larger palindromes from smaller ones. Time complexity. This nested loop is O(n) squared. If both conditions hold, we mark the substring as a palindrome, and we increment our total count because we just discovered another palindromic substring. After checking all substrings of all possible lengths, we return the total number of palindromic substrings found. And that's how this algorithm works. It first initializes a table marking single and double character palindromes, then builds up larger palindromes using dynamic programming by checking the outer characters and the inner substring. Efficient, simple, and elegant. Highlight input box, S equals ABC. Let's run our function with the input string, ABC. Here, each character is unique, so we're looking at a sequence with no repeats at all. Explain the logic briefly. Our algorithm slides a window across the string while tracking characters we've already seen. Since A, B, and C are all distinct and appear only once, the longest substring without repeating characters is simply the whole string itself, length 3. Highlight output box. Output, 3, expected, 3, and that's exactly what the program returns. 3, perfectly matching the expected result. The test case passes without a hitch. So, our implementation is correct. The algorithm efficiently identifies the longest unique character substring in a single scan, clean and accurate. Quick recap on palindromic substrings. This one's all about spotting every hidden mirror in a string, great for sharpening two-pointer intuition and careful counting. The task was to return how many palindromic substrings, contiguous, a string contains. Every single character counts as a palindrome, and we're tallying all of them. We called out the common pitfalls, missing even length centers, double counting, and overlooking that we must count every palindrome, not just the longest. Expanding around centers beats checking all substrings and keeps the logic clean. Our plan: consider all 2n-1 centers, each character, odd, and each gap, even. From each center, expand outward while the ends match, and increment the total for every successful expansion. We followed that plan exactly, expanding around each center and accumulating the count, and it ran cleanly on LeetCode with no errors. On examples like ABC, we counted 3 single-letter palindromes. On triple_A, expansions captured all singles, pairs, and the triple, totaling 6. Edge cases like empty strings and uniform strings behaved as expected. The key takeaway: think in centers and expansions. Once you're fluent with odd/even centers and careful counting, you're set for a whole class of substring and two-pointer problems.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Have you ever felt ambushed by string windows? Find all anagrams in a string is a PatternMastery 100 essential that exposes whether you truly own sliding windows and frequency counts. Phone interviewers love it because a brute force check is too slow, but with the right window math, we get linear time and clean, confident code. Let's nail it with basics. Let's break this down. We're given strings s and p. We must return all start indices in s where the substring is an anagram of p, only lowercase letters. The anagram condition means the character counts match. Now let's assess. Naively sorting each window is on middle.m log m, too slow. Instead, we maintain a fixed size sliding window of length len p over s and compare letter counts. 2 standard tactics. Keep 2 frequency arrays of size 26 and compare. Track a matches counter that says how many letters currently match p's count. We'll use arrays plus matches for O1 updates and ON time, O1 space. Here is the structure. Plan. Build need 26, from p. Sweep right over s, incrementing have c. Once window size exceeds len p, decrement the left char and move left plus plus. Maintain a match count. When have x, equals need x, increment. When it stops equaling after update, decrement. If match equals 26, push left to results. Line highlighted, class solution. We define the solution class that holds our function. Pause. Line highlighted, if len p greater than lens, if p is longer than s, an anagram can't exist, so we immediately return an empty list. Pause. Line highlighted, p_count equals 0, 26. We create a frequency array for p's characters. Line highlighted, window_count equals 0, 26. This array tracks character counts inside the sliding window in s. Line highlighted, result equals, we'll store starting indices of valid anagrams here. Line highlighted, for char in p, we count how often each letter appears in p. Line highlighted, p_count ord char, ord a, plus equals 1. Each character is mapped to a 0 to 25 index and incremented. Line highlighted, for I in range len p, we fill the initial window of size len p. Line highlighted, window_count ord si, ord a, plus equals 1. We count characters in that first window. Line highlighted, if p_count equals window_count. If the pattern and window match, we found an anagram. Line highlighted, result.append 0. So we record index 0. Line highlighted, for I in range len p, lens. Then we slide the window across the rest of s. Line highlighted, window_count ord si, len p, ord a, equals 1. We remove the character leaving the window. Line highlighted, window_count ord si, ord a, plus equals 1, and add the new character entering the window. Line highlighted, if p_count equals window_count, if counts match again, it's another anagram. Line highlighted, result.append I, len p plus 1. We store the current starting index. Line highlighted, return result. Finally, we return all the starting positions of anagrams. Highlight input box, s equals key b bobuct, p equals abc. Let's test our function with the string p b bobuct and the pattern abc. We're looking for all starting positions where an anagram of abc appears inside s. Explain logic briefly. The first 3 characters of s, kaba, contain exactly the same letters as abc, just in a different order. So index 0 is a valid match. Later in the string, the substring bok also matches the pattern, which starts at index 6. Highlight output box. Output, 0, 6. That's exactly what the program returns. 0, 6, matching the expected result. So the implementation works correctly. It finds every anagram of ABC by sliding a fixed size window across the string and comparing character frequencies. Now let's try another implement approach using solution 2. Shorter line-by-line narration, concise, clear, beginner-friendly. Line highlighted, class solution. We create a solution class to hold our method. Pause. Line highlighted, def find anagram self, s, p. This function finds all starting positions in s where an anagram of p appears. Pause. Line highlighted, if len p greater than lens, return. If p is longer than s, no anagrams are possible. Return empty. Pause. Line highlighted, p_count equals, window_count equals, result equals, we set up p_count to count chars in p. Window_count for the sliding window in s. Result to store valid starting indices. Pause. Line highlighted, for char in p, p_count char, equals p_count.get char, 0 plus 1. We build a frequency map of the pattern. Time. OP. Pause. Line highlighted, for I in range len p. This initializes the first window of size len p in S, pause. Line highlighted, window underscore count char, equals window underscore count dot get char, 0 plus 1. We count characters inside the first window, pause. Line highlighted, if p underscore count equals window underscore count, result dot append 0, if the initial window matches the pattern map, index 0 is an anagram, pause. Line highlighted, for I in range len p, lens, now we slide the window across S, one step at a time. Total, on, pause. Line highlighted, left underscore char equals si len p, window underscore count left underscore char equals 1. We remove the leftmost char as it slides out of the window, pause. Line highlighted, if window underscore count left underscore char equals 0, del window underscore count left underscore char, if its count hits 0, remove it for clean comparison, pause. Line highlighted, right underscore char equals si, window underscore count right underscore char, equals window underscore count dot get right underscore char, 0 plus 1. We add the new character sliding into the window, pause. Line highlighted, if p underscore count equals window underscore count, result dot append I len p plus 1. If frequency maps match, we found another anagram, add its start index, pause. Line highlighted, return result. We return all indices where anagrams of p appear in S, pause. Final wrap-up. And that's how this algorithm works. It first builds frequency maps, then slides a fixed size window across the string, updating counts efficiently in 0.1 time per move. Efficient, simple, and elegant. Highlight input box, S equals key b bobuct, p equals abc. Let's test our function with the string p b bobuct and the pattern abc. We're looking for all starting positions where an anagram of abc appears inside S. Explain logic briefly. The first 3 characters of S, kaba, contain exactly the same letters as abc, just in a different order. So index 0 is a valid match. Later in the string, the substring block also matches the pattern, which starts at index 6. Highlight output box. Output, 0, 6, that's exactly what the program returns, 0, 6, matching the expected result. So the implementation works correctly. It finds every anagram of ABC by sliding a fixed size window across the string and comparing character frequencies. Sliding windows can feel sneaky, until you see the pattern. Find all anagrams in a string turns chaotic substring checks into a calm, linear pass with tight frequency math. Let's do a recap. We're given S and P, and we need all start indices in S where a length vertical bar P vertical bar substring is an anagram of P. Conceptually, match character counts, not order. Sorting every window is too slow. The right idea is a fixed size sliding window plus frequency counts. Maintain counts as the window moves so each step is 0.1. A small matches tracker tells us when the window's counts align with P. Build the target frequency for P. Sweep a window of size vertical bar P vertical bar across S. Add the right char, and when the window exceeds size, remove the left char. After each update, adjust the matches counter. When all tracked letters match, record the window start. We executed that plan. Pre-computed counts, slid the window with constant time updates, and captured indices exactly when the counts aligned. The solution ran cleanly on LeetCode with no errors. LeetCode verification confirmed the approach. Indices were collected correctly and all test cases passed as expected. Bullseye emoji. The lesson: sliding windows shine when you trade rework for maintenance. Keep counts in sync as you move, and anagram detection becomes fast, simple, and reliable.
LeetCode says medium. Your nervous system says boss fight. That is your sign you need pattern training. PatternMastery.com.
String to integer, autoy, looks simple, until whitespace, signs, leading zeros, junk characters, and overflow crash your solution. This PatternMastery 100 classic shows up constantly because it tests careful parsing and boundary control. Today we'll turn chaos into clarity with basic and ship an interview-proof implementation that clamps to 32-bit signed range. Breakdown. Given a string S, convert it to a 32-bit signed integer with these rules. Ignore leading spaces. Read optional plus or. Read consecutive digits, stop at first non-digit. If no digits are read, return 0. Assess. We'll do a single left-to-right pass with index I. Track sign, plus or minus 1, and rees,
the number. For overflow safety, before adding a new digit d, check whether res greater than int underscore max / 10 or res equals int underscore max / 10 and d greater than 7, because int underscore max is 2,147,483,647. This runs in on time and o1 space. Structure. Skip spaces. Read sign if +/. While next char is digit, convert to d, pre-check overflow, update res equals res 10 plus d. Return sign res, already clamped. Let's try to implement it using solution 1. We begin by stripping the string of any leading spaces. Think of this like trimming off blank padding before reading a number written on paper. This ensures we start parsing exactly where the meaningful characters begin. Here we check if the string is now empty. If someone passed something like comma-only spaces, then after trimming, nothing remains. In that case, the correct return value is simply 0. Handling the sign. We set a default sign of +1, assuming the number is positive unless proven otherwise. This index will keep track of where we are in the string as we process it character by character. Next, we check if the first character is a plus or minus sign. This tells us whether the number is positive or negative. If the character is a minus sign, we update sign to -1. If it's a plus sign, we keep it as positive. This is just setting the correct direction for the final number. Since we've processed the sign character, we move the index forward so the next step reads the digits correctly. Preparing to build the number. Here we set up a result variable that will accumulate digits to form the final integer, like assembling the number one digit at a time. We define the limits of a 32-bit signed integer. These bounds are required by the problem. If the number goes beyond this range, we must clamp it. Processing digits. This loop runs as long as we still have characters to check and the current character is a digit. If a non-digit appears, like letters, we stop immediately. The loop runs at most on where n is the length of the string. We convert the character into its numeric digit value. For example, 7 becomes 7. This works by comparing ASCII values, a common trick in parsing. Checking overflow. Before we multiply or add anything, we check whether adding this digit would cause the number to overflow the 32-bit integer range. If result is already too large, adding another digit would break the limit, so we'd need to clamp the value. If adding this digit would cause overflow, we immediately return the appropriate limit. int underscore max if the number should be positive. int underscore min if the number should be negative. This satisfies the problem's constraints. Building the number. We safely shift existing digits left, multiply by 10, and append the new one. It's exactly how you'd form a number by hand. Write down the old number, then stick the new digit on the right. We move on to the next character so the loop can continue building the number. Finally, we apply the sign we detected earlier and return the completed integer. This gives us the correctly parsed number per the rules of the classic autoy conversion. Solution 1. Case 1. Let's test our function using this input, 42. This string represents a simple, clean, positive number with no leading spaces or signs, just digits. Here's why the solution works. The algorithm trims whitespace, sees no sign symbol, and begins converting each digit one by one. The characters 4 and 2 become the number 42, with no overflow issues. And that's exactly what our program outputs, 42. This confirms that our code is working correctly for a standard positive number. So, our implementation is correct. It successfully parses plain numeric strings, efficient, accurate, and reliable. Let's try to implement it using solution 2. We start by importing Python's re module, which stands for regular expressions. This gives us powerful pattern matching tools so we can scan the string and pick out the number part cleanly. This defines the solution class, just the standard wrapper many coding platforms use. Our function will live inside this class. Here we define the method myAutoy, which takes a string s and converts it to an integer, following the special autoy rules: skip spaces, handle sign, read digits, and clamp to 32-bit range. We first call lstrip on the string. This removes leading spaces from the left side,
kind of like trimming blank space before reading a number written on a page. Now we use a regular expression to grab the numeric part at the start of the string. Caret means start of the string. \+ means an optional plus or sign. \d+ means one or more digits. So this pattern says, from the very beginning, optionally read a sign, then read as many digits as you can. Re.match tries to match this pattern at the start of S and returns a match object if it succeeds. Here we check, did we actually find a number like pattern? If match is none, it means the string didn't start with a valid sign plus digits combination. In that case, no valid number at the front, we simply return 0, as the problem requires when there's nothing numeric to parse. Now we're in the case where the regex match something. Match.group0 returns the exact substring that matched the pattern, for example -42 or +7 or 4193. We store this in num_str. This is our clean number string, ready to convert. Here we let Python do the heavy lifting. We convert the match string directly into an integer using int num_str. So if num_str is -42, num becomes the integer -42. This comment explains the next section. We'll make sure the number stays within the 32-bit signed integer limits defined by the problem. We define the upper and lower bounds. int_max equals 231 to 12,147,483,647. int_min equals -231 -2,147,483,648. If our parse number goes beyond these, we'll clamp it. We first check for underflow. Is the number smaller than the minimum allowed 32-bit sign value? If it is, we return int_min directly. We don't let it go any lower. This guarantees the result stays in range. Next, we check the other side. Is the number larger than the maximum allowed value? If it's too large, we clamp it down to int_max and return that instead. If the number is safely within the 32-bit range, we just return it as is. No clamping needed, it's already valid. Solution 2. Now we try the input, 042. This string has leading spaces, a negative sign, and digits with a leading 0, a very common real-world format. First, we strip the spaces, so we're effectively looking at 042. The regex matches the longest prefix that looks like an integer, 042. We convert that to the integer -42, then clamp it if necessary. It's safely within range, so we return -42. And that's exactly what our program outputs, -42. So the trimming, sign handling, and leading 0 logic are all behaving as expected. So, our implementation is correct. The algorithm successfully parses the longest valid signed integer prefix from each string, then safely clamps it to 32-bit range, efficient, accurate, and reliable. So that's our deep dive into string to integer, or the famous Autoy challenge, a classic test of precision and control under pressure. Breakdown recap. We started by understanding the task, turning a messy string into a clean 32-bit integer while handling whitespace, optional signs, random junk, and possible overflow. It's all about disciplined parsing and staying within boundaries. Assess recap. We looked at how a single left-to-right scan can get the job done efficiently, keeping track of sign and digits while staying mindful of integer limits. No fancy tools, just logic and order. Structure recap. Our plan was simple. Skip spaces, catch the sign, read the digits, and carefully check for overflow before updating the result. Each step built naturally on the last, leading to a clean, predictable flow. Implement recap. We coded it up, ran it on LeetCode, and everything executed perfectly, no errors, no surprises. Check recap. After running through all the test cases, the logic held up across edge inputs, from empty strings to overflows, confirming our approach works end to end. The big takeaway? Even simple-looking problems can hide layers of complexity. The key is calm, structured thinking, step by step, just like parsing this string into a solid integer.
The interviewer smiled. Not because you were right, because they knew you were lost. Learn to spot the pattern before they spot the panic. PatternMastery.com
Here's a sneaky screen classic, ransom note. It looks trivial. Just letters. But interviewers use it to test whether you instantly reach for frequency counting instead of slow searches. Master this PatternMastery 100 problem and you'll crush dozens of can I build X from Y problems in linear time. Let's knock it out with basic. Breakdown. We're given two strings, ransom note and magazine. We must return true if ransom note can be constructed by cut and pasting letters from magazine. Each magazine character can be used at most once, only lowercase letters. Assess. The right tool is frequency counts. Count letters in magazine, then scan ransom note and check we never request more than we have. With only lowercase letters, a 26-slot array is faster than a dict. Complexity, O(n plus m). Time, O1 space. Structure. Make an array CNT26 equals 0. For each char in magazine, CNT IDSC plus equals 1. For each char in ransom note decrement, if any goes negative, return false. If we finish, return true. Let's try to implement it using solution 1. First, we import Python's collections module. This gives us access to counter, a super handy tool that counts how many times each character appears. Think of it like a built-in character inventory system. Now we define our solution class. This is our main function. It receives two strings. Ransom note, the letters we need. Magazine, the letters we have available. Our job is to check if the magazine provides enough characters. Here, we count how many of each character the ransom note requires. If the ransom note is AA, this counter becomes A2. It's like saying, we need 2 of these. And now we count the letters in the magazine. This tells us what resources we have available, basically the inventory we can pull from. Next, we loop through every character the ransom note needs and how many of each it requires. So for OB, we get a 2, B1. This is the key check. We compare how many of this character the ransom note needs with how many the magazine actually has. If the magazine doesn't have enough, we immediately know the answer is false. And if at any point we find a character shortage, we return false right away, because we can't build the ransom note. If the loop finishes with no shortages, that means every required character exists in enough quantity. So we return true. Yes, we can construct the ransom note. Solution 1. Test case 1. Let's test our function using this input. Ransom note equals A and magazine equals B. These two strings represent the letter we want to construct, and the pool of letters we are allowed to use. Here's why the solution works. The algorithm counts how many times each character appears in the ransom note, and then checks if the magazine contains at least the same number of each character. In this case, the ransom note needs 1A, but the magazine only has B. And that's exactly what our program outputs, false. That means we cannot build the ransom note with the letters provided. So, our implementation is correct. The algorithm successfully compares character frequencies between the ransom note and the magazine. Simple, efficient, and completely reliable. Let's try to implement it using solution 2. We start by defining a solution class. This is just the wrapper LeetCode expects. All our logic will live inside a method of this class. Here's our main function. Can construct. It takes two strings. Ransom note, the text we want to build. Magazine, the pool of letters we're allowed to use. We'll return true if the note can be formed, and false otherwise. First, we create an empty dictionary called count. Think of this as a frequency table or a little letter warehouse. It will store how many times each character appears in the magazine. Now we loop over every character CH in the magazine string. We're walking through the warehouse and tallying how many of each letter we have available. Inside the loop, we update our dictionary. Count.getCH, 0, says, give me the current count for this character, or 0 if it's not there yet. Then we add 1 to that value and store it back. So if the magazine is OB, after this loop, count becomes A2, B1. Next, we start a second loop, this time over each character CH in the ransom note. Now we're on the spending side. For every character the note needs, we'll try to take one from the dictionary. This loop runs once per character in ransom note, so this part is ON where N is the length of ransom note. This if checks whether we can spend a character. Two failure cases. The character doesn't exist in count at all, ch not in count, meaning the magazine never had it. Or it exists, but its count has dropped to 0, count ch equals 0, meaning we already used them all. If either is true, we can't build the ransom note, so we'll return false. If we hit this line, it means we tried to use a character that the magazine can't supply. So we immediately stop and say false, the ransom note cannot be constructed. If we do have that character available, we spend 1 by subtracting 1 from its count. It's like taking 1 copy of that letter off the shelf in our warehouse. We keep doing this for each character in ransom note. If we finish the entire loop over ransom note without running out of any character, that means the magazine has supplied every letter we needed. So we return true. Yes, the ransom note can be constructed successfully. Solution 2. Test case 2. Next, we test with ransom note equals AA and magazine equals AB. The ransom note needs 2 A characters, but the magazine only provides 1 A and 1 B. Our algorithm checks the magazine count and quickly notices that after using the first A, the count drops to 0, meaning the second needed A is not available. And once again, our program outputs, false, perfect. This matches the expected behavior. So, our implementation is correct. The algorithm successfully checks whether every character in the ransom note can be matched using the magazine's letter supply, simple, efficient, and reliable. So, let's wrap up what we learned from this classic ransom note problem. It's a simple yet clever test of understanding how to use counts efficiently. Breakdown recap. We started by looking at what the task really means. We need to see if we can build one string entirely from another, using each letter only once. It's all about matching letter availability between the two. Assess recap. We compared possible approaches and realized that counting each letter's frequency was the cleanest way. Since we're dealing with lowercase letters, a fixed-size array made it both fast and memory-friendly. Structure recap. Our plan was simple. Count every letter in the magazine, then spend those counts as we check through the ransom note. If we ever need more letters than available, we stop right there. Otherwise, we're good. Implement recap. We put this logic into code, ran it on LeetCode, and the implementation worked without any errors. Check recap. After running multiple test cases, we confirmed that the logic holds up. Every check passed successfully. The key takeaway here is how powerful simple frequency counting can be. When faced with problems about matching or availability, thinking in terms of counts often leads straight to the most efficient solution.
It is 1:12 a.m. You are solving problem 417, and somehow you still do not know where to start. That is not discipline. That is chaos. PatternMastery.com.
Did you know one of the most famous dynamic programming questions is inspired by a staircase? Climbing stairs is a PatternMastery 100 classic and a favorite at Google, Microsoft, and Facebook. This deceptively simple problem shows if you truly understand recursion, DP, and how small problems build up to big solutions. Master it, and you'll unlock the core of Fibonacci-style thinking used everywhere in interviews. Let's break down the challenge. You're standing at the bottom of a staircase with n steps. Each time, you can climb either 1 or 2 steps. How many distinct ways can you reach the top? For example, to reach step 4, you could go 1, 1, 1, 1, or 1, 2, 1, or 2, 1, 1, or 2, 2, etc. Now let's assess our approach. A brute force way is to try every path recursively, exponential time. Instead, notice the pattern. To get to step n, you must have come from n1 or n2. So, the number of ways to reach step n is the sum of the ways to reach n1 and n2. This is classic dynamic programming, the Fibonacci sequence in disguise. We can use bottom-up DP or just 2 variables to keep it on time and o1 space. Let's structure our DP approach. If n is 0 or 1, return 1. Set 2 variables. First, ways to reach previous step. Second, ways to reach 2 steps before. For each step from 2 to n, update the number of ways. Current equals first plus second. Move the window forward. Set second equals first, first equals current. Return first. Let's try to implement it using solution 1. We start by defining a class named solution. This is just a container for our method. Think of it like a folder where our stair climbing logic will live. Inside this class, we declare a function called climbStairs. It receives a single number n, which represents the number of steps in the staircase. Our goal is to find out how many distinct ways someone can climb to the top by taking either 1 or 2 steps at a time. We create an empty dictionary called memo. This will act as a memory box where we store results we've already computed. Memoization helps us avoid repeating the same calculations, keeping our runtime efficient. Here we define an inner helper function called DFS, short for depth first search. This function calculates the number of ways to reach step I. It works recursively, building the answer from smaller subproblems. We check a base case, if I is 1 or 2. For 1 step, there is only 1 way to climb. For 2 steps, there are 2 ways, 1 plus 1 or 2. So for I less than or equal to 2, we return I directly. This prevents unnecessary recursion. Before computing anything expensive, we check whether we've already solved this subproblem. If I is already in our memo dictionary, we can reuse the stored result, instant retrieval. If we've solved this step before, we return the saved answer immediately. This saves time and keeps the recursion efficient. This is the core recurrence, the Fibonacci-like relation. To reach step I, you could have come from step I minus 1, taking a 1 step, or step I minus 2, taking a 2 step. So we compute both, add them together, and store the result in our memo dictionary. This ensures we only ever compute each step once. Now we return the computed and stored value for step I. From here on, any future call for the same step will reuse the cached answer. Finally, we kick things off by calling dfsn, asking, how many ways can we reach step n? The recursive function, powered by memoization, handles the rest efficiently. Test case explanation, climbing stairs, memoize DFS case 1, n equals 2. Let's test our function using this input, 2. This number represents the total number of steps in the staircase, and we're trying to find how many distinct ways we can reach the top. Here's why the solution works. When n equals 2, there are only 2 possible ways to climb. Take 2 single steps, or take 1 double step, so the answer is simply 2. And that's exactly what our program outputs, 2. The base case is working perfectly, so our implementation is correct. The algorithm successfully calculates the number of distinct stair climbing paths using memoized recursion, efficient, accurate, and reliable across all test cases. Now we're walking through solution 2. We start by defining a class called solution. This is just the container where our stair climbing method will live, like putting all our logic into one labeled box. Inside the class, we define a function named climbStairs. It takes an integer n, which represents how many steps there are in the staircase. Our task is to figure out how many different ways we can reach step n if we're allowed to climb either 1 step or 2 steps at a time. First, we handle a simple base case, when the staircase is very small. If there are 1 or 2 steps, we don't need any fancy logic, we already know the answer. For 1 step, there's only 1 way to climb it. For 2 steps, there are 2 ways, 1 plus 1 or 2. So if n is 1 or 2, we just return n directly and skip the rest of the function. Now we handle larger staircases using dynamic programming. We create a list called dp with n plus 1 elements, all starting at 0. The idea, dpi, will store the number of distinct ways to climb to step I. Creating this array takes on space. We fill in the base values. dp1 equals 1, there's 1 way to reach step 1. dp2 equals 2, there are 2 ways to reach step 2. These match the logic from our earlier base case and give us a solid starting point for building bigger answers. Next, we loop from step 3 all the way up to step n. For each step I, we'll compute how many ways there are to reach it based on the previous 2 steps. This loop runs n-2 times, so the time complexity of the main work is on. This is the heart of the algorithm. To reach step I, you can come from step I-1 by taking 1 step, or come from step I-2 by taking 2 steps. So the total number of ways to get to step I is the sum of the ways to get to I-1 and I-2. This is why this problem behaves like a Fibonacci sequence. After we filled the whole dp array, dpn now holds the answer to our original question. How many distinct ways can we climb n steps? We return that value as our final result. And that's how this algorithm works. It first sets up a dp array with base cases for the first 2 steps, then builds the answer iteratively by adding the ways from the previous 2 steps for each position. Efficient, simple, and elegant. Solution 2. Test case explanation, climbing stairs, DP array method. Case 2, n equals 3. Now let's test with 3 steps. Again, the input represents the number of steps we need to climb. Here's the logic. After initializing our DP array, dp1 equals 1, dp2 equals 2. We compute dp3 using the recurrence. dp3 equals dp2 plus dp1. dp3 equals 2 plus 1. dp3 equals 3. This represents the 3 valid climbing sequences. 1 plus 1 plus 1, 1 plus 2, and 2 plus 1. And that's exactly what the program outputs, 3. The DP transition is working flawlessly. So, our implementation is correct. The algorithm successfully computes the number of distinct ways to climb a staircase using bottom-up dynamic programming, efficient, accurate, and reliable. Breakdown recap. We started by understanding that each step can be reached by taking either 1 or 2 steps from below. So, the problem is really about counting how many unique sequences of 1s and 2s can add up to reach the top, essentially, finding all possible combinations to climb n steps. Assess recap. We compared different approaches and noticed that brute force recursion tries every possible path, which grows exponentially. Instead, we discovered a pattern. The number of ways to reach step n is the sum of ways to reach steps n1 and n2, just like the Fibonacci sequence. Structure recap. We structured a simple dynamic programming solution by building from the ground up. Starting from the base cases, we iteratively calculated the total ways for each step, storing only the last 2 results for efficiency. Implement recap. Once we coded it up in LeetCode, the implementation ran smoothly without any issues, efficient, clean, and easy to read. Check recap. We tested the logic using LeetCode's built-in cases, confirming that every input passed successfully and the results matched our expectations. The key takeaway is that many complex problems simplify beautifully once you recognize the recurrence pattern. In this case, climbing stairs wasn't just about movement, it was about understanding how smaller subproblems build up to the complete solution.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
What if you could make any amount of money with the fewest coins possible, no matter how weird the denominations? CoinChange is a PatternMastery 100 legend and a favorite at Apple, Facebook, Microsoft, Salesforce, and Amazon interviews. This dynamic programming classic tests not just your DP chops, but your ability to break a tough problem into smaller, reusable subproblems. Let's crack the pattern that unlocks hundreds of interview questions. Let's break it down. You're given a set of coin denominations and an amount. Return the minimum number of coins needed to make that amount. If you can't make it, return -1. You can use as many coins of each denomination as you want. Now let's assess our approach. Brute force would try all combinations, exponential time. Instead, this is a perfect fit for dynamic programming. For every amount from 1 to the target, we'll keep track of the minimum coins needed. At each step, we look back at the best answer for current amount, each coin. This bottom-up DP builds the answer efficiently, and we only need a simple array. Here's the plan. Create a DP array of size, filled with amount +1, a value bigger than possible. Set DP0 equals 0, 0 coins to make amount 0. For each amount from 1 to the target. For each coin, if coin less than or equal to current amount. DP amount equals min DP amount coin, +1. If DP amount is still amount +1, return -1, else, return DP amount. Let's try to implement it using solution 1. We begin by defining a class called solution. This simply organizes our method neatly, like putting the entire approach inside one toolbox. Inside the class, we define a method named CoinChange. It takes 2 inputs. Coins, a list of coin denominations. Amount, the target we want to reach using the fewest coins. Our goal is to compute the minimum number of coins needed to make that amount. Here we create a DP array of size amount +1. Each position represents the minimum coins needed to reach that exact amount. We fill it with infinity to indicate that we haven't calculated anything yet. Think of it as starting with all values set to impossible. Time complexity for this initialization is O amount. We set the base case. To make amount 0, we need 0 coins. This is the foundation that all other answers build upon. We begin looping through every amount from 1 up to the target amount. For each amount A, we want to determine the minimum number of coins needed. This loops amount times, so O amount. For each amount, we iterate through every coin denomination. We ask, can this coin contribute to building amount A? This inner loop runs len coins times, giving us an overall time complexity of O amount times number underscore of underscore coins. We check if the coin is usable. If a coin is at least 0, it means this coin can help form amount A. Otherwise, it's too large and we skip it. This is the heart of the algorithm. To form amount A, we look at amount A, coin. If we already know the best way to form a coin, then adding one more coin forms amount A. So we update DPA with the minimum between its current value and the new calculated value. This fills in the table using previously solved subproblems, classic dynamic programming. Finally, after completing the DP table, if DP amount is not infinity, we return it, meaning the amount is reachable. Otherwise, we return -1, indicating it's impossible to form the target using the given coins. Test case explanation, coin change, dynamic programming case 1, coins equals 1, 2, 5, amount equals 11. Let's test our function using this input, 1, 2, 5, with an amount of 11. These values represent the available coin denominations, and the total amount we want to make using the fewest number of coins. Here's why the solution works. We build a DP array where DPA stores the minimum coins needed to form amount A. Starting from 1 up to 11, we test each coin and update the table. For amount 11, the optimal combination is 5 plus 5 plus 1, which uses 3 coins, the fewest possible. And that's exactly what our program outputs, 3. The DP transitions work perfectly. So, our implementation is correct. The algorithm successfully determines the minimum number of coins needed for any given amount using bottom-up dynamic programming, efficient, accurate, and reliable across all test cases. Let's try to implement it using solution 2. We begin by defining a class called solution, just our container for the coin change method. Think of it as the toolbox where all the logic will live. Inside the class, we create a function named coinChange. It receives 2 things. Coins, the list of coin denominations. Amount, the total we want to make. Our goal is to find the fewest number of coins needed to reach that amount. We set up a dictionary called memo. This is our memory box. Whenever we compute the minimum coins for some remaining amount, we'll store that result here. This prevents repeating expensive work and brings our time complexity down to roughly O amount times number underscore of underscore coins. Here we define an inner helper function called DFS, short for depth first search. This function tries to compute the fewest coins needed to reach a remaining value rem. We check if the remaining amount is 0. If we've reached 0, we've successfully formed the amount. So in that case, we return 0 coins, because no more coins are needed to finish the amount. This acts as a base case for our recursion. If the remaining amount becomes negative, that means we overshot. We used too many coins. This isn't a valid path. We return infinity here to mark this path as unusable. In our comparisons later, infinity signals, don't pick this route. Before doing any work, we check if we've already computed the best answer for this remaining value. If it's in our memo dictionary, no need to repeat the calculation. If we've solved it earlier, we return that saved result immediately. This is what makes this approach efficient. We start with a variable min underscore coins, initially set to infinity. As we explore different coin choices, we'll update this to the best, smallest value we find. Now we iterate through every coin denomination. For each coin, we try subtracting it from the remaining amount and see if that leads to a solution. This branching process is where the DFS explores multiple paths. We recursively call DFS with the updated remaining amount. This asks, if I use this coin, how many coins would I need to finish the rest? If the recursive result is an infinity, it means the remainder was solvable. So this is a valid path. We update min underscore coins by taking the minimum between the current answer and res plus 1, where plus 1 represents the coin we just used. This is the key dynamic decision step. After checking all coin choices, we store the best result for this remaining amount in our memo dictionary. This prevents recalculating it later and dramatically speeds up the overall process. We return the best, smallest number of coins we found for this remaining amount. The recursive stack will now work its way back upward. Now we initiate the whole process by calling DFS amount, asking, what's the minimum number of coins needed to reach the full target? Finally, If the result is an infinity, we return it. That means the amount is achievable. Otherwise, if it's still infinity, we return -1, meaning it's impossible to form the given amount with the provided coins. And that's how this algorithm works. It first initializes memoization to avoid repeated subproblems, then uses a depth-first search to explore all coin combinations, caching results as it goes. Efficient, simple, and elegant. Solution 2. Case 2. Now let's test this input, 2, with an amount of 3. This means the only coin we have is of value 2, so we can only form even amounts. Here's why the solution works. DFS checks all possibilities, but subtracting 2 from 3 gives a remainder of 1, and subtracting 2 again goes negative. Because no combination ever reaches exactly 0, the algorithm returns infinity, which we convert to -1. And that's exactly what our program outputs, -1. Perfect. The solution correctly identifies that amount 3 cannot be formed. So, overall, our implementation is correct. The algorithm successfully computes the minimum number of coins, handling valid cases, impossible cases, and base cases with reliability and efficiency. Let's wrap up with a quick recap of the coin change problem, one of the most classic examples of dynamic programming in action. Breakdown recap. We began by understanding the task. Given different coin denominations and a target amount, we needed to find the fewest coins required to reach that amount, or decide it's impossible if no combination works. Assess recap. We compared potential strategies and realized that brute force recursion would try every combination, quickly becoming inefficient. Instead, we chose a bottom-up dynamic programming approach, where we build up solutions for smaller amounts and use them to solve larger ones efficiently. Structure recap. We structured our logic around a DP array, where each index represents the minimum number of coins needed for that specific amount. By iterating through all coin values and all subamounts, we continuously updated the array with the smallest count possible. Implement recap. After setting up the DP logic in LeetCode, our implementation ran smoothly, efficient, clean, and easy to follow. Check recap. We tested it using multiple inputs on LeetCode, confirming that the solution handled all cases correctly, including the ones where no valid combination exists. The key takeaway here is that dynamic programming shines when problems can be broken into overlapping subproblems. By building up from smaller results, we turn a seemingly complex challenge into a simple, systematic solution.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Longest increasing subsequence. How do you find order in chaos? Longest increasing subsequence is a PatternMastery 100 and interview favorite. Regularly asked at Amazon, Microsoft, and Google, because it tests whether you can spot patterns and optimize solutions. Most candidates start with brute force and get stuck. But if you learn the right DP or binary search trick here, you'll be ready for any sequence challenge interviewers throw your way. Let's break it down. Given an array of integers, find the length of the longest subsequence where each number is strictly greater than the one before it. Remember, a subsequence can skip elements, but order matters. Let's assess the options. The brute force approach tries all possible subsequences. Exponential time. That's not scalable. The classic DP approach is O(n)². For each element, look at all previous elements to find the longest subsequence ending there. But with patience, you can improve to O(n) log n. Using binary search, maintaining a tails array where each value represents the smallest possible tail of an increasing subsequence of that length. Let's start with a DP approach for clarity. Create a DP array of the same length as nums, filled with ones. Each element is an lease of at least 1. For each I from 1 to n1. For each j from 0 to i1. If nums I greater than nums j, set dpi equals max dpi, dpj, plus 1. The answer is max dp. Solution 1. Dynamic programming, O(n)², time complexity, O(n)². Here we're simply defining a class named solution. Think of it like a container that holds our function. This line defines a function called length_, which means length of the longest increasing subsequence. It takes a list of numbers called nums and will return the longest increasing sequence inside it. Here we count how many numbers are in the list. It's like checking how many items we have before starting our work. This creates a list called DP, filled with ones, 1 for each number. Why 1? because every number by itself is a subsequence of length 1. So DPI means the longest increasing subsequence ending exactly at position I. This setup will help us build longer sequences later. Time complexity note. Initializing this is ON. We start tracking the overall longest increasing subsequence found so far. Right now, we assume the minimum length is 1. We begin a loop that walks through each number in the list, one by one, from left to right. This is our main pass through the numbers. Inside the first loop, we start another loop that checks all numbers before the current number. This is how we compare the current number with every previous one to see if we can build an increasing sequence. This inner loop is why the algorithm has a time complexity of ON squared. This line asks two questions. Is the previous number smaller than the current one? So the sequence can keep increasing. If we attach the current number to the sequence ending at J, does it create a longer sequence than what we already stored for I? If both answers are yes, then we update DPI. We update the DP value because we just discovered a longer increasing subsequence ending at index I. It's like saying, hey, we found a better path, let's record it. After finishing the inner comparisons for this position, we check whether the best sequence ending here is the longest overall. If it is the longest, we update max_len to keep track of the global best. Finally, after checking all numbers, we return the length of the longest increasing subsequence we found. Final wrap-up. And that's how this algorithm works. It first sets up a DP array where each number starts with a subsequence length of 1, then compares each number with all earlier numbers to build longer sequences whenever possible. Efficient, simple, and elegant. Test case check, Lee's using dynamic programming. Let's test our function using this input. 10, 9, 2, 5, 3, 7, 101, 18. These numbers represent a sequence of values, and our goal is to find the length of the longest strictly increasing subsequence hidden inside the array. Here's why the solution works. Our DP array, DPI, represents the length of the longest increasing subsequence ending at index I. For each number, we look back at all previous numbers. If a previous number is smaller, and extending its subsequence makes ours longer, we update our DPI value. This way, we gradually build up all possible increasing subsequences. In this specific example, one valid longest increasing subsequence is 23718, which has a length of 4. The DP computation captures this perfectly as it iterates. And that's exactly what our program outputs, 4. The result matches the expected value, confirming that our DP logic is working correctly. Wrap up. So, our implementation is correct. The algorithm successfully computes the longest increasing subsequence using dynamic programming, efficient and accurate. Solution 2, patience sorting, binary search, ON log n, time complexity, ON log n. We start by importing the bisect module. This gives us a built-in binary search tool, super fast, helping us find the correct position to place numbers. Binary search operations here run in O log n time. We're defining a class called solution. It's just a container for our function. This line defines the function that will compute the longest increasing subsequence, or lease, from the list of numbers given. We create an empty list called subsec. Here's the big idea. This list represents the smallest possible ending number, the tail, for increasing subsequences of different lengths. It doesn't store the full subsequence, just the best possible endings. This is what allows the algorithm to stay efficient. ON log n. We loop through each number in the input list, one by one. This outer loop runs n times, contributing the ON part of the total runtime. This line is the magic. We use bisect_left, a binary search, to find where the current number x should go inside subsec. It finds the first position where x can be inserted while still keeping subsec sorted. This runs in O log n time. Now we check if the binary search told us to place x at the very end of the subsec list. That means x is bigger than everything we've seen so far. Great! It extends the longest increasing subsequence. If x belongs at the end, we simply add it to subsec. This means we found a longer increasing subsequence than before. If x doesn't go at the end, then it needs to replace something in subsec. Here we replace the number at index I with x. This might feel strange at first, but it's clever. We aren't storing the actual lease. We're keeping the best possible tails for subsequences of each length. Replacing a larger tail with a smaller x gives us better chances to build longer subsequences later. Still O log n. Because of the earlier binary search, at the end, the length of subsec equals the length of the longest increasing subsequence. We return that number. Final wrap-up. And that's how this algorithm works. It first sets up a list that tracks the smallest possible tail values, then uses binary search to efficiently place or replace numbers to build longer subsequences without ever storing the full sequences. Efficient, simple, and elegant. Test case check, optimal lease, binary search plus patient sorting. Let's test our function using this input, 0, 1, 0, 3, 2, 3. These numbers represent a sequence where we want to find the longest strictly increasing subsequence hidden inside the array. Here's why the solution works. We maintain a subseq-array that stores the smallest possible tail for an increasing subsequence of each length. Using bisect_left, we either append a new number when it extends the sequence, or replace an existing tail with a smaller one, keeping future options open. And that's exactly what our program outputs, 4. This confirms that the optimal patient sorting method calculates the least correctly for this test case. So, our implementation is correct. The algorithm successfully computes the longest increasing subsequence using binary search and a compact tail array, efficient, accurate, and reliable. Longest increasing subsequence. Let's do a recap. We started by understanding the goal. Find the length of the longest subsequence where each number is greater than the previous one. The key detail, it's a subsequence, not a subarray, meaning we can skip elements, but must keep the order intact. Assess recap. We compared different approaches. The brute force method checks all combinations but quickly becomes impractical. The dynamic programming approach, with O(n)² complexity, gave us a structured and efficient way to build solutions step by step. And we discussed how an advanced binary search technique can push that to O(n) log n, for even larger inputs. Structure recap. Our DP plan was simple. For each element, look back at all previous ones and track the length of the longest subsequence that could end there. Each number starts as a sequence of length 1, and we update those lengths as we find valid increases. Implement recap. We implemented this logic cleanly in code, ensuring each element's least length was computed correctly and ran the function on LeetCode without any syntax or logic errors. Check recap. After running the test case, 0, 1, 0, 3, 2, 3, we confirmed our output was 4, matching the expected result. Our approach passed all test cases successfully. Closing insight. The big takeaway? Pattern problems like this reward structure over guessing. Once you understand how to build solutions incrementally, or even optimize them with binary search, you'll start to see order emerge from the chaos every time.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Longest common subsequence. What's the longest hidden pattern toString share? Longest common subsequence is a PatternMastery 100 staple and a classic in dynamic programming, beloved by Google, Facebook, and top tech interviewers. This problem tests your ability to break down problems into overlapping sub-problems and optimize with DP, a must-have skill for tough interviews and real-world software challenges. Let's break it down. Given two strings, return the length of their longest subsequence, not substring, that appears in both. A subsequence can skip letters, but the order must stay the same. Now, let's assess. Brute force would try all possible subsequences, exponential time. Dynamic programming is the standard and optimal solution here. By building a DP table where each cell dpij represents the length of the LCS for text 1, I, and text 2, j, we can reuse previous results and solve the problem in OM times n, time and space. Here's the plan. Create a DP table of size, len text 1 plus 1, times, len text 2 plus 1, filled with zeros. For each index I in text 1 and j in text 2. If text 1i minus 1 is equal to text 2j minus 1, then set dpij to dpi minus 1j minus 1 plus 1. Else, set dpij to max dpi minus 1j and dpij minus 1. The answer is in dp minus 1 minus 1. Solution 1. Recursion with memoization time complexity, OMN. We begin by creating a class named solution. Think of it like a toolbox that will hold our function. This line defines our main function. Its job: find the longest common subsequence, LCS, between two strings, the longest sequence of characters that appear in the same order in both strings. We measure the lengths of both strings and store them as m and n. This helps us set boundaries for our recursion. Time complexity note: getting lengths is O1 for Python strings. We set up a dictionary called memo. This serves as our memory, a place where we store answers we've already computed so we don't repeat expensive work. This memoization keeps our overall complexity at OM times n, instead of exponential. Here we define a helper function called DFS, short for depth first search. This function will recursively explore the two strings starting from positions I and j. This checks whether we've reached the end of either string. If we run out of characters, there can't be any more matching subsequences. In that case, we return 0, meaning no characters left to match. This line checks our memo dictionary to see if we've already solved the LCS problem starting at positions I, J. If we have, no need to redo the work, we simply reuse the stored answer. And if we did store it earlier, we return that value immediately. This saves us a huge amount of time, avoiding repeated recursive calls. Now we check if the current characters match. If the characters at positions I and J are the same, that means this character is part of the LCS. If the characters match, we record in memo that the LCS length at I, J, is 1 plus whatever we find when moving both pointers forward. It's like saying, we found a matching character, now keep searching the rest. If the characters don't match, we have to try both options. Option 1, move forward in the first string. Option 2, move forward in the second string. Here we choose whichever option gives a longer subsequence. We compare the results of two recursive calls and store the best result in memo. This also ensures we don't recompute the same overlaps again. Before finishing this recursive call, we return the value we just stored. This ensures every step bubbles its result upward until we reach the final answer. Finally, we start the recursion from the beginning of both strings, positions 0 and 0. The result of that call is the full length of the longest common subsequence. Final wrap-up. And that's how this algorithm works. It first sets up the string lengths and a memo to avoid repeating work, then uses a recursive search to explore matches and mismatches while storing results for speed. Efficient, simple, and elegant. Test case check. Longest common subsequence, recursion plus memo. Let's test our function using this input. Text1 equals ABAT and text2 equals ACE. These strings represent two sequences, and our goal is to find the longest ordered subsequence that appears in both of them. Here's why the solution works. Our recursive function compares characters at positions I, J. If the characters match, we include that character and move diagonally forward. If they don't match, we explore both possibilities, skipping a character from text1 or from text2, and take the better result. And that's exactly what our program outputs. 3. The result matches the expected value, confirming that the memoized recursion is functioning correctly. Wrap up. So, our implementation is correct. The algorithm successfully computes the longest common subsequence using recursion with memoization, efficient and accurate. Solution 2. Bottom-up DP table time complexity. OMN. We begin by defining a class called solution. Think of it as the container that holds our optimized LCS method. This defines our main function. Its job: compute the longest common subsequence between text1 and text2. We measure the lengths of both strings and store them as m and n. This helps us build a DP table of the right size. This step is constant time, O1. We create a 2D grid called DP, filled with zeros. The table has m+1 rows and n+1 columns. We start looping backward through text1, from the last character toward the first. This ensures the cells we depend on, the ones below and to the right, are already filled. Inside the first loop, we loop backward through text2 as well. So we fill the DP table from bottom right to top left. This ensures our subproblems are solved before we need them. We check whether the characters at positions I and J match. If they do match, this character contributes to the LCS. When the characters match, we add 1 to the LCS length found in the diagonal cell, DPI plus 1 J plus 1. That diagonal cell represents the result of comparing the rest of the strings. So this is like saying, these two characters match, count them, then continue checking the rest. If the characters don't match, we have to choose the best option. We look at two possibilities. Skip a character from text1 DPI plus 1J. Skip a character from text2 DPI J plus 1. Whichever gives the longer subsequence is the correct value for DPI J. This comparison is constant time, O1. But it happens inside two nested loops, resulting in an overall complexity of OM times n. Finally, we return DP00, the cell representing the LCS length of both full strings starting at index 0. That's our final answer. Final wrap-up. And that's how this algorithm works. It first sets up a DP table for storing the answers to all smaller subproblems, then fills that table bottom-up by comparing characters and building the answers step by step. Efficient, simple, and elegant. Test case check, bottom-up dynamic programming, LCS. Let's test our function using this input. Text1 equals ABAT and text2 equals ACE. These two strings represent sequences of characters, and we want to find the longest subsequence that appears in both strings in the same order. Here's why the solution works. We fill a 2D DP table starting from the bottom right corner, working our way up to dp00. At each position, I, j. If the characters match, we take 1 plus the diagonal value. If they don't, we take the maximum of skipping a character from either string. And that's exactly what our program outputs. 3. This confirms that the bottom-up DP logic is functioning correctly and matches the expected value. Wrap up. So, our implementation is correct. The algorithm successfully computes the longest common subsequence using a complete DP table, efficient, accurate, and reliable. Longest common subsequence. Let's do a recap. We started by defining the goal. Find the longest sequence of characters that appear in both strings in order, though not necessarily contiguously. It's all about preserving order while skipping unnecessary characters. That's what makes it a subsequence, not a substring. Assess recap. We discussed how brute force would explore every possible combination. Far too slow. Instead, we chose a dynamic programming approach that builds up results from smaller subproblems. By reusing what we've already computed, we reduced an exponential problem down to efficient OM times N time. Structure recap. Our logical plan was to create a DP grid where each cell represents the LCS length for prefixes of the two strings. If the characters match, we extend the sequence. If not, we carry over the best length found so far. The final answer rests in the last cell. Simple and elegant. Implement recap. We implemented the logic cleanly and ran it through LeetCode. The code executed without any issues, efficiently computing the correct subsequence length. Check recap. After running our test cases, we confirmed that the solution produced the right results and passed all validations, a solid confirmation that our DP structure worked perfectly. Closing insight. The key takeaway? Dynamic programming isn't just about memorizing patterns, it's about recognizing overlapping subproblems and using structure to turn complexity into clarity. Master this mindset, and you'll start seeing DP problems as puzzles that naturally fit together.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Word break problem. Have you ever faced the word break problem in a tech interview? This is one of the most popular Pattern Mastery 100 LeetCode questions, appearing everywhere from Google to Facebook. More than 35% of candidates stumble here because it tests your ability to combine dynamic programming and hashing under pressure. Mastering word break is not just about solving one problem, it's about unlocking a core interview skill. So, let's break it down together and ensure you never trip over this one again. Let's break down the word break problem. We're given a string S and a list of words, word dict. The challenge is, can we split S into a sequence of dictionary words? For example, if S equals cat, sand, dog and word dict equals cats, dog, sand, and cat, can we build S using just these words, without reordering or skipping letters? We want a Boolean answer, yes or no. Now, let's assess the complexity. The brute force approach would check all possible splits. Exponentially slow. But we can do better. If we use dynamic programming, we can store subproblem results. For every index in S, we ask, can I split up to here using the dictionary? A hash set gives us O1 lookups for dictionary words. Edge cases, empty string, should return true. And if word dict is empty, we should return false. Next, let's structure our solution. We'll build a DP array, DP, where DPI is true if S, I, can be broken into dictionary words. Set DP0 equals true as the base case, empty string is always breakable. For each position I, check all possible partition points j before I. If DPJ is true and SJI is in word dict, set DPI equals true. Finally, return DP lens. Solution 1. Dynamic Programming Time Complexity. ON squared. We start by defining a class named solution. Think of it as a simple box that will hold our method. This defines a function named wordBreak. Its job: determine whether the string S can be split into valid words found in worddict. We grab the length of the input string S and store it in N. We'll use this to size our DP table. This step is constant time, O1. We convert the list of words into a set. Why? Because checking whether a word is inside a set is super fast, O1 on average. This will help us test substrings efficiently. We create a DP list called DP with n+1 positions, all starting as false. Each DPI will tell us, is it possible to break the string up to index I into valid words? We mark DP0 as true. This means, an empty string is always breakable. It requires no words. This becomes our starting point. We begin a loop from the start of the string to the end. Here, I represents a position where the string might be breakable. This outer loop runs n times on. We check, is the string breakable up to index I? If dpi is true, it means we successfully reached position I using valid words, so we're allowed to explore further from here. Now we explore every possible substring starting at I and ending at j. We check all possible n positions j, from I plus 1 to n. This nested loop gives us the overall time complexity of on squared. We extract the substring from index I to j, and check if it's a valid word in our dictionary. Because word set is a set, this lookup is very fast, 1 on average. If the substring is valid, we mark dpj as true. This means, the string up to index j can also be broken into words successfully. We are basically marking reachable checkpoints along the string. Finally, we return dpn, which tells us whether the entire string can be segmented into valid words. Final wrap-up. And that's how this algorithm works. It first initializes a DP array and sets up fast word lookups, then walks through the string, checking every possible substring and marking reachable positions. Efficient, simple, and elegant. Test case check. Word break using dynamic programming. Let's test our function using this input. S equals LeetCode and word dict equals LeetCode. The string represents the full word we want to break apart, and the list contains the valid dictionary words we're allowed to form. Here's why the solution works. Our DP array dpi tells us whether the substring s0:i can be segmented using the dictionary. We start with dp0 equals true, meaning the empty prefix is always valid. Then, for every index I where a valid segmentation exists, we try expanding forward to every j greater than I. If the substring sij is a dictionary word, we mark dpj equals true. And that's exactly what our program outputs, true. The result matches the expected output, confirming that the DP logic is functioning correctly. Wrap up. So, our implementation is correct. The algorithm successfully checks whether the entire string can be segmented into valid dictionary words, efficient, accurate, and reliable. Solution 2. Recursion plus memo, DFS, time complexity. On squared, we begin by defining a class called solution. This keeps our function nicely organized. This defines our main function, wordBreak, which answers the big question, can the string S be split into valid dictionary words? We convert the list of words into a set. Why a set? Because checking if something is inside a set is extremely fast, 1 on average. This little optimization makes substring checks much quicker. We create a dictionary called memo. This will store results for starting positions we've already computed. Now we define a helper function named canBreak, which will recursively check, is the substring starting at index start breakable into valid words? We check whether we've reached the end of the string. If we've made it all the way through, it means we've successfully broken the entire string. So if we've reached the end, we return true, mission accomplished. We check if we've already solved this exact subproblem earlier. If so, no need to compute again, we just grab the stored answer. If the answer exists in memo, we return it instantly. This is where most of our time savings come from. We now try every possible split between start and the rest of the string. This loop checks substrings like start plus 1, start plus 2, all the way to the end. Trying all these ranges contributes to the on squared time complexity. We check two conditions. Is the substring from start to end a valid word in the dictionary? If so, can the rest of the string, starting from end, be broken successfully? If both are true, then we found a valid segmentation. We save the result, marking that starting from this index, the string is breakable. And since we found at least one valid split, we immediately return true. No need to test more endings. If none of the possible splits worked, we record that starting from this index does not lead to a successful segmentation. So we return false, meaning the string from this starting point cannot be broken into valid dictionary words. Finally, we start the recursion from index 0, asking, can the entire string, starting from the first character, be broken successfully? That answer becomes our final output, final wrap-up. And that's how this algorithm works. It first sets up fast dictionary lookup and a memo table, then uses depth-first recursion to test every possible split while remembering past results to avoid redundant work. Efficient, simple, and elegant. Test case check, word break using DFS plus memoization. Let's test our function using this input. S equals apple pen apple and word dict equals apple pen. This string represents the full sentence we want to break apart, and the dictionary contains the valid words we're allowed to use. Here's why the solution works. We explore the string from left to right using recursion. At each position, we try every possible substring as start end. If that substring is a valid dictionary word, we recursively check whether the rest of the string can also be segmented. And that's exactly what our program outputs, true. This confirms that our memoized DFS logic correctly identifies valid splits and handles repeated patterns efficiently. Wrap up. So, our implementation is correct. The algorithm successfully determines whether the string can be segmented using recursive search with memoization, efficient, accurate, and reliable. Word break problem. Let's do a recap. Ever hit the word break problem in an interview? It's one of those dynamic programming classics that separates good candidates from great ones. This challenge isn't just about splitting a string. It's about recognizing patterns, using efficient lookups, and proving you can think dynamically under pressure. Breakdown recap. We began with the goal. Given a string and a dictionary of valid words, can we split the string into a sequence of dictionary words without reordering or skipping any letters? Essentially, we're checking if the entire string can be built piece by piece using only the given words. Assess recap. We compared brute force and dynamic programming approaches. Brute force tries every possible split, exponential and inefficient. The DP method, on the other hand, reuses previously computed results to make smarter decisions, while hashing gives us instant dictionary lookups. Together, they form an elegant O(n)² solution. Structure recap. The plan was simple but powerful. We used a DP array where each index represents whether the substring up to that point can be segmented into valid words. Starting from an empty base case, we built our solution step by step, checking all possible word boundaries along the way. Implement recap. We implemented the DP logic with efficient hashing and ran it on LeetCode. The code executed smoothly without any errors, correctly determining whether the string can be segmented. Check recap. We verified the logic by testing with sample inputs and confirmed that the output matched expectations. The algorithm passed all test cases successfully, confirming the DP table and logic worked exactly as intended. Closing insight. The big takeaway? Mastering WordBreak teaches you how to merge dynamic programming and hashing, two of the most important tools in problem solving. Once you see how they work together, you'll not only solve this problem with confidence but also spot the same pattern in dozens of future challenges.
This is not another random playlist. It is a roadmap, patterns, structure, repetition. The stuff that actually sticks. PatternMastery.com.
Combination sum. Have you ever hit a roadblock in interviews with problems like combination sum? This is one of the most common PatternMastery 100 LeetCode questions, frequently popping up in Google, Facebook, and Amazon interviews. Did you know over 40% of candidates stumble here, not because the algorithm is hard, but because backtracking can be intimidating at first glance? Today, we're going to master combination sum step by step, so you can ace this must-know coding pattern and never freeze up again. Let's break down combination sum. We're given an array of unique positive integers called candidates and a target number. Our goal? Find all unique combinations where the numbers sum up to the target. Each number in candidate test can be chosen unlimited times, and combinations must not be duplicated or rearranged. We need to return a list of all possible combinations, with each combination as a list. What are the challenges? A brute force approach would be to try every subset, but that's exponential time, way too slow. We need a smart strategy. This is a textbook backtracking problem. We'll build combinations incrementally, backtracking whenever we overshoot the target. Space complexity can grow quickly with all those combinations, so be mindful of input size. Duplicates are avoided naturally if we always build from the current index forward. Here's our plan. Sort the candidates, optional, but helps with optimization. Use a recursive helper function to build combinations. Track the current combination, sum, and position. If the sum matches the target, save the current combination. If the sum exceeds the target, backtrack. Otherwise, recursively try adding each candidate, starting from current index. This way, we explore all valid paths without repeating or rearranging numbers. Solution 1. Backtracking, on_middle.2n. We begin by defining a class named solution. This keeps our method neatly organized. This function, combination sum, finds all unique combinations of numbers from the list candidates that add up exactly to target. We're allowed to reuse the same number multiple times. We initialize res, the list that will store all valid combinations we discover. We define our helper function DFS, short for depth first search. It tries out choices step by step and backtracks when a path doesn't work. Its parameters: I current index in candidates. Cur the current combination we're building. Total the running sum of numbers in cur. We check whether our running total matches the target exactly. If so, we've found a valid combination. We add a copy of the current combination to Rees. This is one successful answer. Then we return because there's no need to explore further from here. Adding more numbers would exceed the target. If the total has already gone over the target or we've run out of numbers to try, there's no valid combination down this path. So we stop exploring this branch and backtrack. This is the choose step. We choose the number at index I and include it in our combination. Because we can reuse the same number multiple times, we call DFS again on the same index I, adding that candidate to the total. This is the skip step. We skip the current candidate entirely and move on to the next index. This explores combinations that do not include candidates I. We start our depth-first search from index 0, with an empty combination, and a total of 0. Finally, we return the list of all valid combinations discovered. Final wrap-up. And that's how this algorithm works. It first sets up a recursive DFS function, then explores all possible include/skip decisions for each number, collecting combinations that reach the exact target. Efficient, simple, and elegant. Test case check, combination sum using backtracking. Let's test our function using this input. Candidates equals 2, 3, 6, 7, and target equals 7. These numbers represent the values we're allowed to use. Each can be chosen multiple times, and the target is the total sum we want to reach. Here's why the solution works. The backtracking function DFS tries to build combinations step by step. At each step, we can either include the current candidate again, stay at the same index, or skip it and move on to the next candidate. We keep track of the current combination, cur, and its total sum, total. If total becomes exactly equal to target, we record that combination. If total goes over the target, or we run out of candidates, we stop exploring that path. And that's exactly what our program outputs, 2, 2, 3, 7. This confirms that our backtracking logic is correctly exploring all valid paths and collecting every combination that reaches the target. Wrap up. So, our implementation is correct. The algorithm successfully finds all unique combinations that sum to the target using backtracking, efficient, accurate, and reliable. Solution 2. Bottom-up dynamic programming, ON target C. Time complexity, ON target C. We start by defining a class called solution, which keeps our dynamic programming method nicely organized. This defines our function combination sum, which will now solve the problem using a bottom-up DP approach instead of backtracking. We sort the list of candidate numbers. This isn't required for correctness, but it helps generate combinations in a consistent, ascending order. We create a list called DP, where each index T will store all combinations that sum up to T. So, DP0 will store combinations that sum to 0. DP target will eventually hold the final answer. This makes the DP table size target plus 1, giving us part of the ON target C complexity. We initialize DP0 with a single empty combination. Why? Because there is exactly one way to make a sum of 0, by choosing nothing. This is our DP base case. We iterate through each candidate number C. This loop runs n times, where n is the number of candidates. For each candidate, we iterate through all target sums from C to target. This ensures that when we try to build a sum T, we only use combinations that can legally include C. This loop contributes the target factor to our time complexity. We now look at every combination that sums to T, C. Because if we know how to form T, C, we can form T by adding C. The number of combinations stored here is the C factor mentioned in the time complexity. For each combination that sums to T, C, we add C to that combination and store it in DPT, meaning we have found a valid way to make sum T. This gradually builds all combinations bottom up. Finally, we return the list of all combinations that sum exactly to target. That list is stored in DP target, after the DP table is fully filled. Final wrap-up. And that's how this algorithm works. It first builds a DP table where each entry collects combinations for a specific sum, then constructs larger sums by extending previously computed combinations. Efficient, simple, and elegant. Test case check, combination sum using bottom-up dynamic programming. Let's test our function using this input. Candidates equals 2, 3, 5, and target equals 8. These numbers represent the values we're allowed to pick from. Each candidate can be used multiple times, and the target is the total sum we want our combinations to reach. Here's why the solution works. We build a DP table DP where DPT stores all combinations of candidates that sum up to T. We start with DP0 equals, meaning there's exactly one way to make sum 0, by choosing nothing. For each candidate C, we iterate through all target sums T from C up to 8. For every combination already in DPT C, We create a new combination by appending C and store it in DPT. And that's exactly what our program outputs: 2, 2, 2, 2, 2, 3, 3, 3, 5. This confirms that our DP table is building combinations correctly and capturing every valid way to reach the target. Wrap up. So, our implementation is correct. The algorithm successfully finds all unique combinations that sum to the target using bottom-up dynamic programming, efficient, accurate, and reliable. Recap script, combination sum. Let's do a recap. Ever felt stuck on backtracking problems like combination sum? You're not alone. This one trips up tons of candidates because it looks more complex than it really is. But once you understand the pattern behind it, you'll see it's just structured exploration. And suddenly, backtracking becomes your best friend in interviews. Breakdown recap. We started by defining the goal. Find all unique combinations of numbers that add up exactly to a target. Each number can be used multiple times, and order doesn't matter, only the sum does. It's a search problem wrapped in logic and structure. Assess recap. We compared brute force to backtracking. Brute force tries every subset, chaotic and slow. Backtracking, however, builds combinations piece by piece and abandons paths that overshoot the target. It's efficient because it prunes impossible options early, focusing only on meaningful candidates. Structure recap. The plan was clear. Start from the smallest combination, add numbers one at a time, and backtrack whenever the total exceeds the target. When the total hits the target exactly, record the combination. This recursive structure ensures every valid path is explored. No duplicates, no missed possibilities. Implement recap. We implemented this plan cleanly using recursion and ran it on LeetCode. The code executed smoothly, no errors, and efficiently generated all unique combinations that sum to the target. Check recap. After testing, we confirmed that the solution returned all valid results and passed every LeetCode test case successfully. It performed exactly as expected, even on trickier inputs. Closing insight. The key takeaway? Backtracking is just organized trial and error. Once you master how to control and prune your search space, problems like combination sum, and many others, become clear, logical, and even fun to solve.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
House robber. Here's a classic interview scenario. You're asked to solve the house robber problem, a dynamic programming staple and PatternMastery 100 favorite that shows up at companies like Google, Amazon, and Apple. Did you know that nearly 40% of candidates get tripped up here, not because the math is hard, but because they miss the optimal substructure? Mastering House Robber will instantly level up your dynamic programming skills and give you an edge in any coding interview. Ready to break into this problem like a pro? Let's dive in. Let's break down the problem. You're given a row of houses, each with a certain amount of money. If you rob two adjacent houses, the alarm goes off. The challenge: find the maximum amount of money you can rob tonight without robbing two directly next to each other. For example, given nums equals 2, 1, 1, 2. What's the maximum you can take? Now, let's assess our approach. Brute force. Sure, you could try every possible combination, but that's 2 to the power of n time, way too slow. Instead, we'll use dynamic programming. The key insight: for each house, you have two choices: rob it and skip the previous one, or skip it and take whatever you got before. So, our recurrence becomes rob n equals max rob n2 plus nums n, rob n1. This breaks the problem into smaller, overlapping subproblems, perfect for memoization or DP. Let's structure the solution. Step 1. Handle base cases. If there are no houses, return 0. If one house, take it. No houses? Nothing to rob. One house? Rob it. Step 2. Use a DP array, DPI, where each entry stores the max money that can be robbed up to house I. The first house is always robbable. The second? Pick the bigger of house 0 or house 1. Step 3. For each house, decide to rob it or skip it. If we rob, add the current house's money to DPI 2. If we skip, carry forward DPI 1. Step 4. At the end, return DPN 1, the answer for all houses. The last entry holds the max money you can rob. Solution 1. Recursion with memoization time complexity. ON. We begin by defining a class called solution. This just serves as a container for our function. This defines the method rob, which solves the classic house robber problem. You want to steal the most money, but you can't rob two adjacent houses. We store the number of houses, or how many values are in the list. We'll use this to know when we've gone past the end. This operation is constant time, O1. We create a dictionary called memo. This stores answers we've already computed so we don't repeat work, reducing our time to ON instead of exponential. We define a helper function named DFS, short for depth first search. This function will compute the maximum money we can rob starting from house I. This checks whether we've gone past the last house. If we have, there's nothing left to rob. So in that case, we return 0 because no money is available beyond this point. We check whether we've already solved the problem starting from this house index I. If yes, we can skip computation and reuse the saved result. If we've already computed it, we return the stored value immediately, instant answer. This is the key decision step. We choose the better of two options. Skip the current house and move to house I plus 1. Rob the current house, add its money, nums I, and jump to house I plus 2, because we can't rob adjacent houses. We take the maximum of these two choices and save it in memo I. This step ensures each index is solved once, giving us ON total time. We return the best possible amount starting from this house and store it for reuse. And finally, we kick off the recursion by starting at house 0, the very first house. Final wrap-up. And that's how this algorithm works. It first stores the number of houses and sets up memoization, then recursively explores two choices at each house while remembering past results for speed. Efficient, simple, and elegant. Test case check. House robber using recursion plus memo. Let's test our function using this input. 1, 2, 3, 1. These numbers represent the amount of money stored in each house along the street, and the goal is to steal the maximum amount without robbing two neighboring houses. Here's why the solution works. At each index I, our recursive function chooses between skipping the house, take whatever profit comes from DFS I plus 1. Robbing the house, take nums I plus DFS I plus 2. We store each result in memo so we never solve the same subproblem twice. And that's exactly what our program outputs. 4. The value matches the expected result, showing that our memoized recursion is functioning correctly. Wrap up. So, our implementation is correct. The algorithm successfully determines the maximum amount of money that can be stolen without triggering alarms, efficient, accurate, and reliable. Solution 2. Iterative DP, space optimized, time complexity, ON. We begin by defining a class named solution. Nothing fancy here, just a container for our method. This defines our main function rob, which solves the house robber problem using a clean, space-optimized dynamic programming approach. We create a variable called prev. This will store the best result from two houses ago. You can imagine it as the amount we'd have if we last robbed the house before the previous one. We also create a variable called cur. This will store the best result from the previous house. Together, prev and cur help us track the rolling DP values without needing an entire array. This keeps space usage at O1, very efficient. We loop through each house one by one. Each house has a certain amount of money, represented by num. This loop runs n times, ON. We temporarily store the current best amount in temp. Why? Because we're about to update cur, and we still need the old value to update prev later. This is the heart of the logic. We choose between two possibilities. Skip this house, keep the current best total, cur rob this house, add the house's money, num, to the total from two houses ago. Prev, whichever choice gives more money becomes the new cur. Now we update pre to be the old value of cur, which we stored in temp. This shifts our sliding window of decisions forward by one house. And finally, we return cur, which now holds the maximum money we can rob without ever taking two adjacent houses. Final wrap-up. And that's how this algorithm works. It first sets up two running totals to track the best choices, then walks through each house, deciding whether to rob or skip using a simple max comparison. Efficient, simple, and elegant. Test case check. Optimal iterative DP, house robber. Let's test our function using this input. 2, 7, 9, 3, 1. These numbers represent the amount of money stored in each house along the street, and we want to steal the maximum amount without ever robbing two neighboring houses. Here's why the solution works. We maintain two running values. Prev, the best total we can get if we skip the current house. Cur, the best total we can get up to the current house. For each value num, the algorithm updates cur to be the maximum of the old cur, skipping this house, or prev plus num, robbing this house. And that's exactly what our program outputs. 12. This confirms the optimized DP logic is working correctly and matches the expected value. Wrap up. So, our implementation is correct. The algorithm successfully computes the maximum non-adjacent sum using constant space, efficient, accurate, and reliable. Recap script, house robber. Let's do a recap. Ever been asked the house robber in an interview? It's a dynamic programming classic, simple at first glance, but packed with logic that tests whether you truly understand optimal substructure. Once you master it, you'll see why it's a must-know for every top-tier interview. Breakdown recap. We began by defining the goal. Given a row of houses with money, find the maximum you can rob without hitting two adjacent ones. The key is balance. Rob too close together, and the alarm goes off. Spread out your choices, and you maximize your loot. Assess recap. We compared brute force and dynamic programming. Brute force explores every combination. Too slow. DP, on the other hand, breaks the problem into smaller overlapping decisions. Rob this house and skip the previous, or skip it and keep what you've already earned. That structure makes it efficient and scalable. Structure recap. We planned our solution around this simple recurrence. The best choice at each step is the maximum between robbing the current house, plus what was earned two houses back, or skipping it to keep the previous total. Building this logic from left to right gives us the optimal result at the end. Implement recap. We coded it cleanly, handled edge cases, and ran it on LeetCode. The implementation executed smoothly. No errors, clear logic, and efficient use of dynamic programming principles. Check recap. After testing, the solution passed all test cases and confirmed that our DP setup works perfectly, calculating the maximum amount that can be robbed without breaking the rules. Closing insight. The takeaway? Dynamic programming is about choices and consequences. Once you see how each decision depends on past results, like in House Robber, you unlock a powerful way of thinking that applies to dozens of problems beyond this one.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
House Robber 2. Let's talk about a true interview curveball. House Robber 2. This is one of the most notorious PatternMastery 100 problems, and it's a favorite at companies like Google and Facebook. Did you know that over 45% of candidates fail this problem in interviews simply because they overlook the circular constraint? It's a common trap, even for those who've practiced DP extensively. If you can master House Robber 2, you'll gain a serious edge in coding interviews that involve dynamic programming, adjacency constraints, or interval-based logic. Ready to level up your problem-solving game? Let's break in. Let's break the problem into its core. You have a list of houses, each with some money. If you rob two adjacent houses, the alarm goes off. And here's the twist. The houses form a circle, so the first and last are also neighbors. Our goal? Find the maximum amount you can rob without tripping the alarm. Sounds like a job for dynamic programming. But how do we handle the circle? Let's assess our options. If the houses were in a straight line, it's classic House Robber, LeetCode 198. But with a circle, robbing the first house blocks you from robbing the last. So, what if we split the circle into two scenarios? Exclude the first house. Rob from house 2 to the end. Exclude the last house. Rob from house 1 to the second to last. Here's the structure. If there's only one house, return its value, no circle worries. Otherwise, solve the two scenarios. Rob houses 0 to n2. Rob houses 1 to n1. For each, use a helper function that applies dynamic programming to find the max loot. Solution 1. Split into two linear subproblems, time complexity, ON. We begin by defining a class named solution. This is just a clean container to hold our method. This defines our main function rob, which solves the House Robber 2 problem, where houses are arranged in a circle instead of a line. We first check if the list is empty. If there are no houses, there's nothing to rob. In that case, we simply return 0. Next, we check if there is only one house. In a circle, robbing that one house is always allowed. So we return the value inside that single house. Here we define a helper function called rob_linear. This solves the regular House Robber problem, the one where houses are in a straight line. We'll use this trick because the circular problem can be reduced to two linear ones. We initialize two rolling variables. Prev the best result 2 houses ago. Cur the best result from the previous house. This setup gives us O1 space complexity. We loop through each house in this linear arrangement. This loop runs n times On. This single line contains the DP logic. We shift cur into prev, moving one house forward. We calculate a new cur, choosing the better of. Skipping this house keep cur. Robbing this house add num to prev. It's the classic DP decision, rob or skip. When we finish the loop, cur holds the maximum money we can rob in this linear scenario. This is the key insight for circular houses. If you rob the first house, you can't rob the last house. If you rob the last house, You can't rob the first house. So we solve two cases. Rob houses 0 to n2, exclude last. Rob houses 1 to n1, exclude first. Then we return the maximum of these two results. Final wrap-up. And that's how this algorithm works. It first handles simple edge cases and defines a helper function for linear robbing, then splits the circular problem into two linear subproblems and chooses the better outcome. Efficient, simple, and elegant. Test case check. House robber 2, circular houses. Let's test our function using this input. 2, 3, 2. These numbers represent the amount of money in each house, but this time the houses are arranged in a circle, which means the first and last houses are neighbors. Here's why the solution works. Because house 0 and house 2 are adjacent, we can't rob them both, so we split the problem into two linear scenarios. Rob houses 0 through n2 that considers 2, 3. Rob houses 1 through n1 that considers 3, 2. We run the optimized rob linear DP on both segments and take the maximum. And that's exactly what our program outputs, 3. This matches the expected result and confirms the circular robbery logic is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully handles the circular constraint by evaluating two linear robbery paths, efficient, accurate, and reliable. Solution 2. DP with two scenarios time complexity. We begin by defining a class called solution. Nothing complicated here, just the container for our method. This defines our main function rob, which solves the circular house robber problem using two dynamic programming arrays. We calculate how many houses are in the list. This helps us handle edge cases and size our DP arrays correctly. We check the simplest case. If there are no houses, there's nothing to rob. So we return 0 when the list is empty. Another special case. If there's only one house, then that's the only house we can rob. The circular rule doesn't matter. So we return the value inside that one house. We now create our first DP array, DP1. This will track the best robbery plan when we do rob the first house, meaning the last house must be excluded. We create a second DP array, DP2. This tracks the best plan when we do not rob the first house, so we are free to rob the last one. In the first scenario, we do rob the first house, so DP1's first entry is the value of house 0. For the second house in scenario 1, we make a choice. Either we keep robbing house 0, or we rob house 1 instead. We choose whichever gives more money. In scenario 2, we are not allowed to rob the first house, so DP20 must start at 0. Since we skipped house 0 in scenario 2, the first house we may rob is house 1, so DP21 becomes the value of nums 1. We now loop through the rest of the houses, starting from index 2. This loop runs n times on. This is the tricky part for scenario 1, the case where we rob the first house. We choose the best between DP1i1, skipping this house, DP1i2, plus nums I, robbing this house. But if we're at the last house, I equals n1, we cannot rob it in scenario 1, because we already robbed the first one. So in that special case, we simply copy DP1i1, meaning, skip the last house entirely. In scenario 2, things are simpler. Since we did not rob the first house, we are allowed to rob the last house. So we use the classic house robber recurrence, take the max of skipping this house, DP2i1, or robbing it, DP2i2, plus nums I. And finally, we return the better of the two completed scenarios. Robbing the first house, DP1 not robbing the first house, DP2 whichever scenario gives more money is our final answer. Final wrap-up. And that's how this algorithm works. It first handles edge cases and builds two dynamic programming scenarios, then computes the best possible loot by considering whether the first house is robbed or skipped. Efficient, simple, and elegant. Test case check. House robber 2 using two DP tables. Let's test our function using this input. 1, 2, 3, 1. These values represent the money stored in each house, but since the houses are arranged in a circle, the first and last houses are considered neighbors. Here's why the solution works. Because we can't rob both the first and last house in a circular street, we build two separate DP arrays. DP1 considers robbing from house 0 to n2, first house included, last excluded. DP2 considers robbing from house 1 to n1, first house excluded, last included. Each DP table follows the standard house robber recurrence. DPI equals max DPI1, DPI2, plus nums I. And that's exactly what our program outputs, 4. This confirms that the DP table approach correctly handles the circular constraint and finds the optimal solution. Wrap up. So, our implementation is correct. The algorithm successfully computes the maximum money that can be robbed in a circular arrangement by evaluating two DP paths: efficient, accurate, and reliable. House Robber 2. Let's do a recap. Ever faced the House Robber 2 problem and thought, wait, why isn't my DP working anymore? This one's a true interview curveball because it adds a circular twist to a classic. Once you learn how to handle that constraint, though, it becomes one of the most elegant dynamic programming problems out there. Breakdown recap. We started by restating the challenge: rob houses arranged in a circle, where the first and last houses are also neighbors. That means you can't rob both ends, so the problem becomes figuring out the maximum money you can take without setting off the alarm, even in this circular setup. Assess recap. We compared our options. The brute force approach would fail quickly with exponential time. Instead, we leaned on dynamic programming, but with a twist. Since the first and last houses can't both be robbed, we split the problem into two simple linear cases. 1 keycap emoji, exclude the first house. 2 keycap emoji, exclude the last house. Then we solve each one just like the regular house robbery problem and take the higher result. Structure recap. The plan was clear. Handle the edge case for a single house, define a helper function to calculate the best loot in a straight line, and apply it twice, once for each scenario. Finally, return the maximum of the two outcomes. Implement recap. We implemented this step by step, ran it on LeetCode, and everything worked flawlessly. The code executed efficiently with no errors, running in ON time and O1 space, fast and optimized for interviews. Check recap. After testing with multiple inputs, the solution passed all test cases. It handled the circular constraint perfectly and returned the expected results every time. Closing insight. The key takeaway? Complex problems often hide simple patterns. By recognizing that the circle could be broken into two linear cases, we turned a tricky DP puzzle into a clean, logical solution. Master this one, and circular constraints will never trip you up again.
LeetCode says medium. Your nervous system says boss fight. That is your sign you need pattern training. PatternMastery.com.
Decode ways. Imagine this. You're in a high-pressure tech interview, and you're handed one of the trickiest DP string problems out there: decode ways. This PatternMastery 100 staple isn't just a test of coding, but of true problem breakdown and logic. Did you know that over 40% of candidates get tripped up by edge cases with leading zeros or multi-digit decodings? If you can master decode ways, you'll be ready for any string or DP problem thrown your way. So let's crack it together. Here's the breakdown. You're given a string of digits, like 102,213, and each digit or pair of digits can map to a letter: 1 to A, 2 to B, 26 to Z. Your job? Count how many ways you can decode the string, following those rules. A 0 on its own is invalid, but 10 is valid since it maps to J. What are all the possible decoding paths? Now, let's assess the challenge. A brute force recursion would explore every way to split the string, but it's way too slow. We need dynamic programming. For each position in the string, we'll store how many ways we can decode up to there. Key edge cases? Zeros. 0 isn't a letter, but 10 is valid. We need to handle both single-digit and two-digit decodings. Here's how we'll structure it. Set up a DP array where dpi is the number of ways to decode the first I characters. Initialize dp0 equals 1, empty string is one way. For each position I from 1 to n. If si1 is valid, not 0, add dpi1. If si2:i is between 10 and 26, add dpi2. Solution 1. Recursion with memoization time complexity. ON. We begin by defining a class called solution. This is just a neat container for our decoding method. This defines our function numDecodings, which computes how many different ways we can decode a digit string into letters. Remember, 1a, 2b, 26z. We store the length of the string in n. This lets us know when we've reached the end during recursion. We create a dictionary called memo, which will store results for already visited positions. Memoization helps us avoid recomputing, giving us a time complexity of ON. We define a recursive helper function called DFS, which tells us how many valid decodings exist starting from index I. This checks if we've reached the end of the string. If so, that means the entire path leading here was valid. So we return 1, representing one valid decoding path. If the current character is 0, it cannot be decoded by itself. There is no letter that maps to 0. So we return 0, meaning no valid decoding from this point. If we're at the last character and it's not 0, it must be valid by itself. So there is exactly one way to decode that last character. Thus, we return 1. We check whether we've already computed the number of decodings starting from index I. If we have, we can reuse that answer immediately. So if the memo contains it, we return the saved value, instant lookup. We initialize our result by first decoding one character. This represents the scenario where we treat SI as a single-digit letter. We now check whether the next two digits form a valid letter, from 10 to 26. If so, there is another decoding option available. Decode two digits together. If the two-digit number is valid, we add the number of ways to decode the rest of the string starting from I plus 2. This is like branching the decision tree. One branch for single-digit decoding. One branch for double-digit decoding. We store the result for index I in memo so future calls don't repeat the work. We return the total number of decoding paths starting from index I. Finally, we start the entire decoding process from index 0, the beginning of the string. Final wrap-up. And that's how this algorithm works. It first sets up memoization and a recursive helper, then explores both single-digit and double-digit decoding options while saving results to avoid repeated work. Efficient, simple, and elegant. Test case check. Decode ways using recursion plus memo. Let's test our function using this input. 12. This string represents an encoded message where each digit or pair of digits maps to a letter. 1a, 2b, 26z. Here's why the solution works. We use recursion to explore every valid way to decode the string. First, we try decoding one digit at a time. Then, if the next two digits form a valid number between 1 and 26, we explore decoding them as a pair as well. Memoization ensures we don't recompute results for the same index more than once. And that's exactly what our program outputs, too. This confirms that the recursive plus memoized approach is working correctly and matches the expected result. Wrap up. So, our implementation is correct. The algorithm successfully counts all valid decoding paths by exploring single-digit and double-digit options, efficient, accurate, and reliable. Solution 2. Bottom-up DP time complexity, ON. We begin by defining a class called solution, which simply groups our decoding method neatly. This is our main decoding function. It tells us how many ways we can convert a digit string into letters, where 1a, 2b, 26z. We store the length of the string in n so we can build our DP table. We check whether the input is empty. No digits means no decodings. So for an empty string, the answer is simply 0. We create a DP array of size n plus 1, all initialized to 0. Each DPI will represent the number of ways to decode the substring starting at position I. This array gives us our bottom-up dynamic programming structure. We set the base case, dpn equals 1 means that when we reach the end of the string, there is exactly one valid way to decode, by doing nothing. This is a common trick in DP for decoding problems. Now we set the value for the last real character. If the last character is 0, it cannot be decoded, so dpn 1 equals 0. Otherwise, it's valid as a single letter, so dpn 1 equals 1. We now fill the DP table backwards, from right to left. Each index I represents a subproblem. How many ways to decode starting at position I? This loop runs n times on. If the current character is 0, it cannot be decoded on its own, so dpi must be 0. Thus, there are 0 ways to decode starting from index I if si is 0. If the digit is not 0, it can be decoded as a single letter mapping. So first, we count the ways to decode by treating si as a single-digit letter. That's why we copy dpi plus 1. This represents the one-step decoding path. Now we check whether the next two digits form a valid letter between 10 and 26. If they do, we have a second decoding option, decode two digits together. If the two-digit number is valid, we add the number of ways to decode the substring starting at I plus 2. This adds in the two-step decoding path. Finally, dp0 contains the answer for the entire string, the total number of ways to decode from the beginning. Final wrap-up. And that's how this algorithm works. It first builds a DP table from right to left, starting with simple base cases, then adds the number of one-digit and two-digit decoding paths for each position. Efficient, simple, and elegant. Test case check. Decode ways using bottom-up dynamic programming. Let's test our function using this input. 226. This string represents an encoded message, where each digit or pair of digits corresponds to a letter from 1a through 26z. Here's why the solution works. We fill a DP array from right to left, where dpi represents the number of ways to decode the substring starting at index I. If the current digit is 0, it contributes 0 decodings. Otherwise, we add DPI plus 1. Decoding the current digit alone. DPI plus 2. Decoding the current two digits together if they form a number less than or equal to 26. And that's exactly what our program outputs. 3. This confirms that our bottom-up DP approach is computing the decoding count correctly. Wrap up. So, our implementation is correct. The algorithm successfully counts all valid decoding paths using an efficient DP table, reliable, accurate, and performant decode ways. Let's do a recap. So, how do you turn a string of numbers into letters, and how many ways can you do it? Decode ways is one of those deceptively simple dynamic programming problems that really tests your logic under pressure. Once you understand its structure, though, it becomes one of the most elegant DP challenges out there. Breakdown recap. We started by understanding the core problem. Given a string of digits, each single or double-digit number can represent a letter from A to Z. The goal is to count how many valid ways you can decode the entire string. But there's a catch: zeros can't stand alone, which makes handling combinations like 10 or 20 critical to getting the logic right. Assess recap. We compared the brute force recursion with dynamic programming. Recursion explores every possible split but grows exponentially. DP, on the other hand, builds the solution step by step by remembering how many ways we can decode each prefix. That's the key to handling overlapping subproblems efficiently. Structure recap. Our plan was clear. We used a DP array where each position represents the number of ways to decode up to that point. For each digit, if it's valid, not zero, we carry forward previous counts. If the last two digits form a valid pair between 10 and 26, we add in the count from 2 steps back. By the end, the final value tells us the total decoding count. Implement recap. We implemented this logic in Python and ran it on LeetCode without any errors. The DP solution worked efficiently in ON time and space, and we even noted that it could be optimized to O1 by using just 2 variables. Check recap. After running our test cases, the output matched perfectly with expectations. The DP table captured every valid decoding path, confirming that the logic worked for both regular digits and tricky zero cases. Closing insight. The big takeaway? Decode Ways teaches the heart of dynamic programming, breaking big problems into smaller overlapping parts. Once you master that pattern, you'll recognize it everywhere, from strings to sequences to any problem that builds on past results.
The interviewer smiled. Not because you were right, because they knew you were lost. Learn to spot the pattern before they spot the panic. PatternMastery.com.
How many different ways can you reach your destination in a grid, no matter the twists and turns? Unique Paths is a Pattern Mastery 100 dynamic programming classic and a favorite at Google, Meta, and Amazon. Over 30% of candidates make mistakes with state transitions or grid boundaries. Master this and you'll unlock the foundation for nearly every grid-based DP problem in interviews. Let's solve unique paths using the basic approach, so you'll confidently tackle any path-counting DP challenge. Given an MXN grid, count the number of unique paths from the top left corner to the bottom right corner. You can only move right or down at each step. Integers m, n, grid dimensions. Integer, number of unique paths. Picture planning a robot's moves through a warehouse, or a delivery drone's flight plan over a grid city. Interviewers might ask, how would you count all possible routes if movement is restricted to right and down? What's tricky? You can't move diagonally or backward. Many candidates overcomplicate or forget edge cases for the first row/column. Dynamic programming and combinatorics both provide solutions. The robot can only arrive at a cell from above or left. For any cell, I, j, the number of ways to reach it is the sum of the ways to reach I1, j, and I, j1. Initialize the first row and first column to 1, only one way to reach each cell along the edge. Initialize a DP table of size MXN, fill first row and column with 1. For each cell not on the edge, dpij equals dpi1j plus dpij1. Return dpm1n1. Solution 1. 2D DP Grid Time Complexity, OMN. We begin by defining a class named Solution. This simply organizes our method neatly in one place. This defines our function unique paths, which calculates how many different ways a robot can move from the top left corner to the bottom right corner of an m by n grid. The robot is only allowed to move right or down. Here we create a 2D grid called DP with m rows and n columns, and we fill every cell with 1. Why 1? Because the entire first row and first column each have only one way to reach them. The robot can only come straight from one direction. This grid will store the number of unique paths to reach every square. Creating this grid takes om times n time. We now loop through the grid starting from the second row. The first row already has correct values, so we skip it. Inside that loop, we loop through each column starting from the second column. Again, the first column is already handled automatically, so we begin from j equals 1. This is the heart of the algorithm. The number of ways to reach cell I, j, is the sum of the number of ways to reach the cell above it, dpi, 1j. The number of ways to reach the cell to the left of it, dpij, 1. Because the robot can only move down or right, these are the only two ways to arrive at I, j. Finally, we return the value in the bottom right corner of the grid. That cell contains the total number of unique paths from start to finish. Final wrap-up. And that's how this algorithm works. It first initializes a grid where the first row and column represent paths with only one direction, then fills in the rest of the grid using the idea that each cell combines paths from above and from the left. Efficient, simple, and elegant. Test case check. Unique paths using dynamic programming. Let's test our function using this input. M equals 3 and n equals 7. These numbers represent a grid with 3 rows and 7 columns, and we want to count how many unique ways a robot can move from the top left corner to the bottom right corner, moving only right or down. Here's why the solution works. We create a DP table where each cell dpij represents the number of unique paths to reach that position. The first row is all ones because you can only move right. The first column is all ones because you can only move down. Every other cell is the sum of the paths from the top and from the left. And that's exactly what our program outputs, 28. This matches the expected result, confirming that the DP grid was built correctly. Wrap up. So, our implementation is correct. The algorithm successfully counts all unique paths through the grid using dynamic programming, efficient, accurate, and reliable. Solution 2. Combinatorial formula time complexity, OM plus n. We start by defining a class called solution, which simply organizes our method nicely. This defines the function unique paths, which calculates how many different ways a robot can travel from the top left to the bottom right of an m by n grid. Here we compute the total number of moves the robot must make. To reach the bottom right corner, it must move m, 1 steps down, n, 1 steps right. Adding them together gives us m plus n, 2 total moves. We choose the smaller of the two required directions. Either the number of downward moves or rightward moves. Why the smaller one? Because when computing combinations, C total, K, is symmetrical. Choosing fewer items keeps our loop fast and efficient. This optimization helps keep the time complexity OM plus n. We set up a variable res to store the running result of our combination formula. Think of it as our accumulator. We now enter a loop to compute the combination formula C total, K, using a multiplicative approach. This avoids calculating giant factorials and prevents overflow issues. The loop runs K times, which is at most min m, n, keeping things very efficient. This line applies the combination formula step by step. We multiply by the next numerator term, then divide by the current denominator term. In simpler terms, we're gradually building C total, K, equals total K, total K, without ever computing the full factorials. This keeps things fast and safe in Python. And finally, we return res, which now contains the total number of unique paths the robot can take. Final wrap-up. And that's how this algorithm works. It first converts the grid walking problem into a simple combination formula, then builds that combination efficiently using a short loop. Efficient, simple, and elegant. Test case check. Unique paths using combinatorics. Let's test our function using this input. M equals 3 and n equals 2. These numbers represent a grid with 3 rows and 2 columns, and we want to know how many unique paths lead from the top left corner to the bottom right corner, moving only down or right. Here's why the solution works. To reach the bottom right cell, the robot must make m, 1 equals 2 downward moves, n, 1 equals 1 rightward move. So the path is simply a combination of these moves. In total, the robot makes 2 plus 1 equals 3 moves, and we choose where the downward moves occur. And that's exactly what our program outputs, 3. This confirms that the combinatorial formula is computed correctly and matches the expected answer. Wrap up. So, our implementation is correct. The algorithm successfully uses combinations to calculate the number of unique grid paths, efficient, accurate, and reliable. Unique paths. Let's do a recap. So, we've just solved one of the most foundational dynamic programming challenges, unique paths. This problem isn't just about counting roots in a grid, it's about understanding how small decisions stack up into bigger patterns, a key skill that powers most grid-based DP problems you'll see in interviews. Breakdown recap. Conceptually, the task is simple. Find how many ways a robot can travel from the top left to the bottom right corner of a grid, moving only right or down. Every path you count builds from these two possible moves, and our goal is to track them systematically. Assess recap. We realized brute force would explode in complexity, so dynamic programming was the smart approach. The key insight was that every one cell's number of paths depends on just two previous cells, the one above it and the one to its left. Once we got that recurrence relation down, the problem became straightforward. Structure recap. We planned it like this. Start with a grid of path counts, initialize the first row and first column to 1 since there's only one way to move along the edges, and then fill the rest by summing the top and left cells. That pattern continues until the destination cell gives us the total number of paths. Implement recap. We implemented the logic cleanly, ran the solution on LeetCode, and everything executed perfectly. No syntax issues, no boundary errors. The DP table built up exactly as expected, and the output matched every test case. Check recap. After running multiple scenarios, all test cases passed successfully. The results lined up perfectly, even for edge cases like single row or single column grids. The logic worked efficiently and consistently. Closing insight. The big takeaway? Unique paths teaches the foundation of dynamic programming, breaking big problems into overlapping subproblems. Once you master this pattern, you'll start seeing the same logic in everything from grid traversal to robot movement to advanced combinatorial DP questions.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Can you make it across the finish line when every step depends on your last? Jump Game is a Pattern Mastery 100 favorite and a classic at Google, Facebook, and Amazon, testing your greedy algorithms and array reasoning. 30% of candidates trip over edge cases or inefficient DP. Master this, and you'll breeze through reachability and greedy interview problems. Let's solve Jump Game using the basic approach, your step-by-step strategy for any reachability or greedy challenge. Given an array of non-negative integers, where each element represents your maximum jump length from that position, determine if you can reach the last index. List of integers nums, max jump at each index. Boolean. True if you can reach the end, else false. Picture crossing stepping stones in a river, where each stone tells you how far you can jump ahead. Interviewers might ask, how would you check if a player can always reach the end in a game with varying step sizes? What's tricky? DP is possible but unnecessary. Greedy works better. Watch out for zeros in the array, they can block progress if you can't jump past them. Must always keep track of the farthest reachable index. Initialize a variable farthest to 0. Iterate through the array. If the current index is greater than farthest, you're stuck. Return false. At each index, update farthest equals max farthest, I plus nums I. If farthest ever reaches or exceeds the last index, return true. Initialize farthest equals 0. Loop over nums with index I. If I greater than farthest, return false. Update farthest equals max farthest, I plus nums I. If farthest greater than equals len nums, 1. Return true. If loop ends, return false. Solution 1. Greedy, furthest reach, time complexity. ON. We begin by defining a class called solution. This just gives us a clean place to store our method. This defines our function canJump, which determines whether we can reach the last index of a list by jumping forward using the rules given in the problem. We set reachable to 0. This variable represents the furthest index we can currently reach. Think of it like the maximum distance your character can jump so far. We store the length of the array in n, which tells us how many positions exist in total. We loop through the array from index 0 to index n-1. This loop runs n times on. We check if our current position I is beyond what we can reach. If we've ever landed on an index that we cannot physically jump to, then we're stuck. So if we're standing at an unreachable index, the answer is false, we cannot reach the end. Otherwise, we update our furthest reach. I plus nums I represents how far we can jump from this position. We compare it with our current reachable distance and keep the maximum. This is the greedy step. always track the best possible reach. We check if our furthest reach has already reached, or passed, the last index. If yes, we don't need to continue, we know we can win. So if we can reach the last index at any point, we immediately return true. And if we finish the loop without getting stuck, that means we can always reach the end, so we return true. Final wrap-up. And that's how this algorithm works. It first tracks the furthest index we can reach, then walks through the array, updating that reach until either we get stuck or reach the end. Efficient, simple, and elegant. Test case check, jump game using greedy reachability. Let's test our function using this input. 2, 3, 1, 1, 4. These numbers represent how far you can jump from each position, and our goal is to determine whether we can reach the last index. Here's why the solution works. We track the farthest position we can reach as we move through the array. If at any point our current index goes beyond this reachable range, we know we're stuck. Otherwise, we keep expanding the reach by taking the maximum of the current reachable distance, and the new jump range from the current index, I plus nums I. And that's exactly what our program outputs, true. The result matches the expected value, confirming that the greedy reachability method is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully checks whether we can reach the final index by tracking the maximum reachable position, efficient, accurate, and reliable. Solution 2. BFS Traversal Time Complexity, O(n)(, worst case. We import dec, a fast double-ended queue. This structure allows us to pop from the front efficiently, perfect for BFS, breadth first search. We define a class called solution to neatly hold our method. This defines our function canJump, which determines whether we can reach the last index of the array using BFS exploration. We store the length of the input list in n. This tells us how many positions exist. We create a set called visited containing index 0. This ensures we don't revisit the same index twice, preventing infinite loops and reducing extra work. We initialize a queue for BFS and start by adding index 0. This means our BFS exploration begins at the very first position. We begin a BFS loop. As long as there are positions left to explore, the loop continues. This BFS may explore up to O(n)(, positions in the worst case if every index can jump many steps. We remove the next position from the front of the queue. This is the current index we will explore. We check if this index is the last one in the array, the finish line. If we reach the last index, we've succeeded. We can jump to the end, so we return true immediately. We try all possible jump lengths from this position, from 1 up to the maximum allowed by nums I. This inner loop is where the worst case O(n)(, behavior comes from. We calculate the next index we'd land on after taking this specific jump. We only consider this next index if it's inside the array bounds and we haven't visited it before. This prevents wasting time revisiting old positions. We mark the new index as visited so we don't process it again later. And we add this new index to the BFS queue so we can explore its possible jumps next. If we exit the BFS loop without ever reaching the last index, that means there's no valid path to the end. So we return false. Final wrap-up. And that's how this algorithm works. It first sets up a BFS queue and tracks visited positions, then explores every possible jump from each reachable index until either we reach the end or run out of options. Efficient, simple, and elegant. Test case check, jump game using BFS search. Let's test our function using this input. 3, 2, 1, 0, 4. These numbers represent how far you can jump from each index, and our goal is to see whether we can reach the last position in the array. Here's why the solution works. We treat each index like a node and perform a BFS search. Starting from index 0, we explore every reachable next position using all valid jump distances. We also track a visited set so we never recheck the same index. And that's exactly what our program outputs, false. This matches the expected value, confirming that our BFS exploration correctly detects when the last index cannot be reached. Wrap up. So, our implementation is correct. The algorithm successfully checks all reachable paths using BFS and accurately identifies when the end cannot be reached. Efficient, accurate, and reliable. Jump game. Let's do a recap. So, we've just tackled one of the most popular reachability problems in interviews, jump game. It's fast-paced, logical, and a great way to show that you understand how to balance dynamic programming ideas with greedy reasoning. Once you grasp this, you'll spot the same pattern in dozens of real-world and interview problems. Breakdown recap. At its core, the problem asks, can you reach the end of an array if each element tells you how far you can jump? It's like stepping across stones. Every number tells you how many stones ahead you can move, and your goal is to make it to the last one without getting stuck. Assess recap. We compared two approaches, dynamic programming and greedy. While DP works, it's unnecessary here. Greedy logic is more efficient. The key insight was simple. Keep track of the farthest point you can reach. If at any point your current index goes beyond that limit, you're stuck. Otherwise, you keep pushing that boundary forward. Structure recap. We structured it around one core loop, moving through the array while tracking the farthest reachable index. If the current position is ever out of reach, we stop. If we extend the farthest reach to or beyond the final index, we've made it. It's clean, linear, and effective. Implement recap. We ran the greedy logic step by step on LeetCode. The code executed perfectly, no runtime errors, no boundary issues, confirming that the logic holds even with tricky cases like zeros and single-element arrays. Check recap. All test cases passed. The algorithm successfully determined when the end was reachable, and when it wasn't. It handled small, large, and edge cases exactly as expected, efficient, reliable, and consistent. Closing insight. The key takeaway? Jump Game teaches you how to think ahead, literally. It's not about every step, but how far you can go from each one. Mastering this greedy mindset will help you tackle a whole class of problems built around reachability, optimization, and forward-thinking logic.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Partition equals subset sum. This problem looks innocent. And then Rex timelines. Partition equals subset sum is a PatternMastery 100 star, because it tests whether you can recognize a hidden subset sum dynamic programming problem and reason about time-space trade-offs on the fly. Good news! With a basic framework and a slick 1D DP, you'll narrate and code this confidently, no brute force backtracking meltdown. Breakdown. We get an array of positive integers called nums. Can we split it into two subsets with equal total? If the total sum is odd, the answer is immediately false. Otherwise, we just need to know whether some subset sums to total divided by 2, classic subset sum. Assess. Backtracking is exponential. Instead, we use dynamic programming. Define dp of s as can we make sum s using the numbers we've seen so far? Initialize dp of 0 as true. For each number x, update dp of s by checking dp of s minus x, going backward from target down to x, so we don't reuse x multiple times. The complexity is O of n times target in time, and O of target in space, where target equals total divided by 2. A neat alternative is a bit set that shifts reachable sums with bits OR equals bits shifted left by x. Structure. Compute the total. If it's odd, return false. Set target to total divided by 2, and create dp of length target plus 1 with dp of 0 set to true. For each x in nums, iterate s from target down to x, and set dp of s to dp of s or dp of s minus x. Return dp of target.
Let's try to implement it using solution 1. Here we are defining a function called canPartition. It takes a list of numbers, nums, and we are going to check whether we can split that list into two groups with equal sums. Think of it like balancing two sides of a scale. This line adds up all the numbers in the list and stores the result in total. We are calculating the full weight of the scale before deciding how to split it. Time complexity of sum, O of n. Here we are checking if the total is odd. If the total weight is odd, there is no way to split it into two equal halves. So if the sum is odd, we immediately return false because an equal partition is impossible. No need to do more work. Now we compute the sum we want each group to reach. If the full total is like a pie, we are calculating the size of exactly half the pie. This line creates a list called DP, short for Dynamic Programming Table. It has target plus 1 slots, all starting as false. Each position dp of s will later represent whether it is possible to make a sum of s using some of the numbers. Space complexity, O of target. We mark dp of 0 as true because we can always make a sum of 0 by choosing nothing. It is our base case, the foundation of the whole strategy. Now we loop through each number in the list. For every number, we update the dp table to show which sums become possible with that number included. This outer loop runs n times. This inner loop tries all possible sums, from the largest value which is target down to the current number. We are checking whether we can make the sum s by using this number. This loop runs at most target times, Combined with the outer loop, the time complexity is O of n times target. Here is the key logic. We look at dp of s minus num, which means that before adding this number, was it possible to make a smaller sum that is exactly num away from s? If yes, then adding num now makes some s possible. So if the condition is true, we mark dp of s as true. It is like saying that we found a way to make this sum using the numbers we have processed so far. This gradually fills up the table with achievable sums. And finally, we return whether dp of target is true. If it is, then we can form exactly half the total sum, meaning the list can be partitioned into two equal subsets. If not, we return false. And that is how this algorithm works. It first checks whether an equal split is possible, then uses a dynamic programming table to build up all reachable sums step by step. Efficient, simple, and clean. Check. Let's walk through this test case for the partition equal subset sum problem and confirm why the output is true. Input. Nums equals 1, 5, 11, 5. What the input means. We want to determine whether the array can be split into two subsets whose sums are equal. First, compute the total sum. 1 plus 5 plus 11 plus 5 equals 22. Since 22 is even, there is a possibility to split it into two subsets of sum. 22 divided by 2 equals 11. So the target we are trying to build using a subset is 11. Why the output is true. We look for a combination of numbers in nums that totals to 11. One such subset is 11. Another valid combination could be 551, which equals 11. As long as any subset sums to 11, a valid partition exists. A dynamic programming or subset sum approach confirms that 11 is reachable. Thus, we can split the array into two subsets. Subset A equals 11. Subset B equals 155. Both have a sum of 11. So the correct answer is true. The output true matches the expected true. This confirms that the solution correctly determines the array can be partitioned into two equal sum subsets. Now let's try another implement approach using solution 2. We begin by defining our main function canPartition, which receives a list of numbers called nums. Think of this function as our control room where the whole decision-making process starts. Here we are adding up all the numbers in nums. This gives us the total sum of everything we are trying to split into two equal halves, like checking the total weight before dividing it between two bags. Time complexity of sum, O of n. We check whether the total is odd. If the total number is odd, then it is impossible to split it into two equal halves. Think of trying to split 15 apples evenly between two people. One will always get more. So if the sum is odd, we instantly return false, ending the function early because no partition will ever work. We calculate our goal, the exact sum we want each side of the partition to have. If the total is 20, then each group needs to sum to 10. This creates an empty dictionary called memo. We will use it to remember results we have already computed so we do not repeat unnecessary work. This transforms our recursion into memoized depth-first search, which reduces repeated calculations. Now we define an inner function named DFS, short for depth-first search. This function tries to build up a sum using numbers starting at index I, and cur keeps track of the current sum we have built so far. Think of it like exploring branching paths. Include the number or skip it. First check inside DFS. If our current sum equals the target, then we have successfully formed one half of the partition. Mission accomplished. We return true here because we found a valid solution path. There is no need to explore further down this branch. This line checks two failure conditions. If our current sum goes beyond the target, we overshot. If we have run out of numbers to try, meaning I is past the length of the list, we cannot go any further. Either way, this path will not work. So we return false to signal that this particular route cannot form a valid partition. Here we check if we have already solved this exact situation, with the same index I and the same current sum cur. Memoization saves us from repeating work and dramatically reduces the time. In the worst case, time complexity drops from O of 2 to the n for raw recursion to roughly O of n times target. If we have stored an answer before, we immediately return it. This is like checking your notes so you do not redo the same math problem twice. This is the core of the algorithm. We explore two recursive paths. Path 1. Include nums at index I, so we add it to our current sum. Path 2. skip nums at index I, and move on without changing the sum. If either path returns true, then we have found a valid partition. We save the result in our memo dictionary. This way, if we ever revisit the same index with the same sum, we can instantly reuse this answer. We return the result of the two depth-first search attempts, either true if any path led to success or false if both failed. Finally, we start the depth-first search process from the very beginning, at index 0, with the current sum of 0. Then the exploration begins, including or skipping numbers until we either hit the target or exhaust all options. And that is how this algorithm works. It first checks whether splitting is mathematically possible, then uses a memoized depth-first search to explore different combinations without repeating work. Efficient, simple, and elegant. Check. Let us walk through this test case for the partition equals subset sum problem, and see why the output is false. Input. Nums equals 1, 2, 3, 5. We are checking if this array can be split into two subsets whose sums are exactly equal. First, compute the total sum. 1 plus 2 plus 3 plus 5 equals 11. The total sum is 11, which is odd. To split an array into two equal sum subsets, the total sum must be even, because we need total sum divided by 2 equals target sum for each subset. But here, 11 divided by 2 equals 5.5, which is not an integer, so it is mathematically impossible to divide the array into two subsets with the same sum. No matter how we group the numbers, the two sides cannot both reach the same integer total. Therefore, the correct result is false. The output false matches the expected false, confirming that the implementation correctly detects that this array cannot be partitioned into two equal sum subsets.
Let's have a quick recap. Breakdown recap. So, wrapping this up, partition equals subset sum asks whether we can split an array into two subsets with the same total. It sounds simple, but the key is recognizing that it is actually a subset sum problem in disguise. If the overall sum is odd, the answer is immediately impossible. If the sum is even, the real question becomes whether there is a subset that adds up to half of the total. Assess recap. We compared approaches and saw why brute force fails. Backtracking grows exponentially and becomes unmanageable very quickly. Dynamic programming, on the other hand, gives us structure and efficiency. By tracking which sums are reachable as we process each number, we convert the problem into a predictable O of n times target solution. There is also a bit set trick that accomplishes the same idea using fast bit shifts. Structure recap. The plan was straightforward. First, handle the odd sum rejection. Next, set the target to total divided by 2, create a DP array, and for each number, update reachable sums from right to left. This backward update prevents reusing the same number twice and ensures that our DP remains correct. Implement recap. During implementation, we built a one-dimensional DP table that expanded as we processed each number. The logic stayed clean. Start with DP of 0 set to true, then mark all newly achievable sums. Memory usage stayed low, and execution remained tight, which fits interview constraints very well. Check recap. When tested on multiple arrays, every case behaved exactly as expected. Valid partitions returned true, and impossible ones returned false. Both the DP and the bitset variants produced matching results, confirming that the algorithm is both efficient and reliable. The key takeaway is that many problems that ask you to divide or split arrays are actually subset sum patterns in disguise. Recognizing that structure early turns what looks like a complicated recursive challenge into a simple and elegant DP. This problem is a great reminder that understanding patterns is more powerful than memorizing solutions.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Can you make it across the finish line when every step depends on your last? Jump Game is a Pattern Mastery 100 favorite and a classic at Google, Facebook, and Amazon, testing your greedy algorithms and array reasoning. 30% of candidates trip over edge cases or inefficient DP. Master this, and you'll breeze through reachability and greedy interview problems. Let's solve Jump Game using the basic approach, your step-by-step strategy for any reachability or greedy challenge. Given an array of non-negative integers, where each element represents your maximum jump length from that position. Determine if you can reach the last index. List of integers nums, max jump at each index. Boolean. True if you can reach the end, else false. Picture crossing stepping stones in a river, where each stone tells you how far you can jump ahead. Interviewers might ask, how would you check if a player can always reach the end in a game with varying step sizes? What's tricky? DP is possible but unnecessary. Greedy works better. Watch out for zeros in the array, they can block progress if you can't jump past them. Must always keep track of the farthest reachable index. Initialize a variable farthest to 0. Iterate through the array. If the current index is greater than farthest, you're stuck. Return false. At each index, update farthest equals max farthest, I plus nums I. If farthest ever reaches or exceeds the last index, return true. Initialize farthest equals 0. Loop over nums with index I. If I greater than farthest, return false. Update farthest equals max farthest, I plus nums I. If farthest greater than equals len nums, 1, return true. If loop ends, return false. Solution 1. Greedy, furthest reach, time complexity. ON. We begin by defining a class called solution. This just gives us a clean place to store our method. This defines our function canJump, which determines whether we can reach the last index of a list by jumping forward using the rules given in the problem. We set reachable to 0. This variable represents the furthest index we can currently reach. Think of it like the maximum distance your character can jump so far. We store the length of the array in n, which tells us how many positions exist in total. We loop through the array from index 0 to index n-1. This loop runs n times on. We check if our current position I is beyond what we can reach. If we've ever landed on an index that we cannot physically jump to, then we're stuck. So if we're standing at an unreachable index, the answer is false, we cannot reach the end. Otherwise, we update our furthest reach. I plus nums I represents how far we can jump from this position. We compare it with our current reachable distance and keep the maximum. This is the greedy step, always track the best possible reach. We check if our furthest reach has already reached, or passed, the last index. If yes, we don't need to continue, we know we can win. So if we can reach the last index at any point, we immediately return true. And if we finish the loop without getting stuck, that means we can always reach the end, so we return true. Final wrap-up. And that's how this algorithm works. It first tracks the furthest index we can reach, then walks through the array, updating that reach until either we get stuck or reach the end. Efficient, simple, and elegant. Test case check, jump game using greedy reachability. Let's test our function using this input. 2, 3, 1, 1, 4. These numbers represent how far you can jump from each position, and our goal is to determine whether we can reach the last index. Here's why the solution works. We track the farthest position we can reach as we move through the array. If at any point our current index goes beyond this reachable range, we know we're stuck. Otherwise, we keep expanding the reach by taking the maximum of the current reachable distance, and the new jump range from the current index, I plus nums I. And that's exactly what our program outputs, true. The result matches the expected value, confirming that the greedy reachability method is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully checks whether we can reach the final index by tracking the maximum reachable position, efficient, accurate, and reliable. Solution 2. BFS Traversal Time Complexity. ON squared, worst case. We import dec, a fast double-ended queue. This structure allows us to pop from the front efficiently, perfect for BFS, breadth first search. We define a class called solution to neatly hold our method. This defines our function canJump, which determines whether we can reach the last index of the array using BFS exploration. We store the length of the input list in n. This tells us how many positions exist. We create a set called visited containing index 0. This ensures we don't revisit the same index twice, preventing infinite loops and reducing extra work. We initialize a queue for BFS and start by adding index 0. This means our BFS exploration begins at the very first position. We begin a BFS loop. As long as there are positions left to explore, the loop continues. This BFS may explore up to ON squared positions in the worst case if every index can jump many steps. We remove the next position from the front of the queue. This is the current index we will explore. We check if this index is the last one in the array, the finish line. If we reach the last index, we've succeeded. We can jump to the end, so we return true immediately. We try all possible jump lengths from this position. from 1 up to the maximum allowed by num's I. This inner loop is where the worst case O(n)² behavior comes from. We calculate the next index we'd land on after taking this specific jump. We only consider this next index if it's inside the array bounds and we haven't visited it before. This prevents wasting time revisiting old positions. We mark the new index as visited so we don't process it again later. And we add this new index to the BFS queue so we can explore its possible jumps next. If we exit the BFS loop without ever reaching the last index, that means there's no valid path to the end. So we return false. Final wrap-up. And that's how this algorithm works. It first sets up a BFS queue and tracks visited positions, then explores every possible jump from each reachable index until either we reach the end or run out of options. Efficient, simple, and elegant. Test case check, jump game using BFS search. Let's test our function using this input. 3, 2, 1, 0, 4. These numbers represent how far you can jump from each index, and our goal is to see whether we can reach the last position in the array. Here's why the solution works. We treat each index like a node and perform a BFS search. Starting from index 0, we explore every reachable next position using all valid jump distances. We also track a visited set so we never recheck the same index. And that's exactly what our program outputs, false. This matches the expected value, confirming that our BFS exploration correctly detects when the last index cannot be reached. Wrap-up. So, our implementation is correct. The algorithm successfully checks all reachable paths using BFS and accurately identifies when the end cannot be reached. Efficient, accurate, and reliable. Jump game. Let's do a recap. So, we've just tackled one of the most popular reachability problems in interviews, jump game. It's fast-paced, logical, and a great way to show that you understand how to balance dynamic programming ideas with greedy reasoning. Once you grasp this, you'll spot the same pattern in dozens of real-world and interview problems. Breakdown recap. At its core, the problem asks, can you reach the end of an array if each element tells you how far you can jump? It's like stepping across stones. Every number tells you how many stones ahead you can move, and your goal is to make it to the last one without getting stuck. Assess recap. We compared two approaches, dynamic programming and greedy. While DP works, it's unnecessary here. Greedy logic is more efficient. The key insight was simple. Keep track of the farthest point you can reach. If at any point your current index goes beyond that limit, you're stuck. Otherwise, you keep pushing that boundary forward. Structure recap. We structured it around one core loop, moving through the array while tracking the farthest reachable index. If the current position is ever out of reach, we stop. If we extend the farthest reach to or beyond the final index, we've made it. It's clean, linear, and effective. Implement recap. We ran the greedy logic step by step on LeetCode. The code executed perfectly, no runtime errors, no boundary issues, confirming that the logic holds even with tricky cases like zeros and single-element arrays. Check recap. All test cases passed. The algorithm successfully determined when the end was reachable, and when it wasn't. It handled small, large, and edge cases exactly as expected, efficient, reliable, and consistent. Closing insight. The key takeaway? Jump game teaches you how to think ahead, literally. It's not about every step, but how far you can go from each one. Mastering this greedy mindset will help you tackle a whole class of problems built around reachability, optimization, and forward-thinking logic.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
You made it this far. That already puts you ahead of most people. But remember, this was never about finishing 100 problems. It was about seeing the patterns behind them, because in a real interview, you will not get the same question. You will get something unfamiliar, but built from something you've already seen. And when that moment comes, you won't rely on memory. You'll rely on recognition, on structure, on the system, basics, and you trained it all in Python. So keep training, keep breaking problems down, keep looking for patterns, because the goal was never just to solve problems. It was to think like someone who can solve any of them. And that's the difference between practicing and being ready.